solution, but then the table would just give the initial values. There are, we say everything, but there are filters involved always, of course. An important one is on-board Gaia. There can be a detection in the sky map or CCD. If it's not confirmed in the following CCD, then the observation is just aborted, no telemetry generated, no trace, except for a counter of that observation. On ground, there is also a filtering. Everything that looks like a spurious detection is not included in the cross-match process I mentioned, so, and will therefore not be published. There will just be a detection record published. And the reason this is needed is, you can see here, this is a stack of detections around bright sources. And there are thousands of false detections around every bright source, and if they are not removed from the pipeline, then it will break down. So, and it's it's something like 10% of all detections that are filtered out on that. And then, as I said, for on ground in processing sources for the AGES solution, if it's very poor or there's only very few transits, then such a solution will not enter Gaia source, but it will enter the all source astrometry table. And epoch data will be published, and so on. And for the good solution, of course, it will enter Gaia source, so there will be epoch data and everything. One of the new things in DR4 will be the source environment analysis, where all observations for a given source are processed together to reconstruct a 2D image around the source, to look for companions or extended sources and so on. So there will be what they call an image segregation, and then an astrometric and photometric solution for each of these components. And that also leads to another new product, the residual image. So around brighter sources, in this case, we can look for any extension of the source, in this case a protoplanetary disk, which was shown in the Gaia Image of the Week last month. So this will be published for all sources brighter than 13. We also have the crowded field. Gaia has a limited capacity for how many observations it can process at the same time. And that's a problem when you get to galactic center, globular clusters, and so on. And for that reason, well, we have here the sky mapper CCDs, where the stars enter and are detected. These CCDs, by necessity, are read out in full. And this data is on board, but overwritten continuously. But for these special cases, by some clever engineering trick, the data is extracted and sent to ground. And therefore, we can make a more complete catalog for a number of very dense areas. It will, of course, have less precision, but it will give a very good idea about the completeness of the Gaia catalog in these areas. A very interesting new thing is the epoch astrometry and epoch image. I mean, for photometry, radial velocities, epoch data, that's a time series. So you have the epoch and you have the magnitude at each epoch, or the radial velocity at each epoch. For astrometry, we cannot give right ascension declination at every epoch because observations are one-dimensional. So instead, for a source, everything is referred for that source to some reference position, alpha 0, delta 0. And we have a scan direction and the observation. And so what we can say for this epoch is that the source is at such an angle from the reference point in this scan angle theta. It sounds maybe a little complicated to deal with, but it's actually not so bad once you start looking at it. And there's a very nice document by Leonard Lindegren explaining the principles, which is available in the ESA public Gaia DPAC documents folder. And similar, there is the epoch image, which are the raw data for each observation, if you want to make a even better model of the instrument. So this is a list of all the tables that will be in DR4. It's about I think there's 142 tables in this list. And it's also in the ESA web. And about half of them are new tables. So there's a lot of new things to look forward to for DR4. And I just mentioned a few of them, but there are also very bright sources, solar system, of course, spectra, epoch spectra, and so on. So, with that, I will finish.
Thank you, Klaus. There is time for questions. Thank you, Mark.
Thanks a lot. Probably the most informative talk I've been to in the last few years. Thank you. Can you go back to the one with the LMC fields?
This one?
No, one at the beginning.
This one?
That one. Okay. So I'm just curious. So is this? I mean, at this point, is a slide we can comment outside here? It's not completely, because my point is that, I mean, this, as you know, I've been working on this, and this is just extremely informative. The point is that what you're saying is that we're going to go from the one on the left to the one on the right? Mm-hmm. Okay. So the one on the left, for those of you who don't know, the amplitude of those oscillations is 10.3 microarc seconds. And that's what, basically, that's the main limitation for those of you who want to do precise Gaia astrometry. That was in DR3. So just by looking at those two, I mean, I would say that the amplitude goes from about 10 microarc seconds to about 3. Do you know the numbers? Does that sound right?
I don't have exact numbers,
yeah.
No, but I mean, the LMC is a nice field to study for this because basically all sources are at the same distance.
No, my point in this is that, I mean, of course, what you mentioned at the beginning about how much reduction we're going to get in the random uncertainties, I think it's even more important that we get a better reduction in the systematic uncertainties, right? Such as this one. And this is huge. I mean, this factor of 3, right? I mean, if my estimate is correct, that this is a reduction in the systematic uncertainty by a factor of 3, essentially means that for objects for which we have very good data, such as stellar clusters, we can expect an improvement in the distances by a factor of 3. It means that the distance to a cluster that is a 1 kiloparsec will go from being about plus or minus 10 parsecs to plus or minus 3. And again, that's a lot. So my point in this is that it may be true that for the random uncertainties in the parallaxes, you get a reduction by a factor of a square root of 2. But looking at this, if I interpret it correctly, the systematic uncertainties are improved even by a better factor.
Yes, at least in this field, it looks like that.
More questions?
The LMC is a bit special because it's near the ecliptic pole and has a very nice distribution of scans and so on. But
more questions? No?
Thank you very much for the talk. I'm curious to know what will happen with all these bright stars, because you mentioned bright stars, but there were like 49 really bright areas, but I understand that there is also other brighter stars that were not included in previous catalogs. Are they going to be included?
Not every bright star, but a lot more than in DR3. And these 49 is by a special processing.
Okay, but so there isn't the idea to have them at some point, I guess, but not necessarily for, or this is something that is not
That's
priority.
the ambition, of course, but well, obviously Sirius is extremely difficult to.
Okay.
Like magnitude 1 or 2?
Yeah.
Okay.
Thanks.
And of course, they will not have the same precision as normal stars.
More questions?
Hello, thank you for the overview. Can you go to the summary, the slide with the summary of the new tables? I think it's one of the last. So, yeah, I see that there are 6 new tables for non-single stars. So, do you notice is related to, say, new solution, new models, or the like variation of binary solution that we already have in DR3?
I mean, there are various types of models for binaries.
So there are new models that have been tested.
Yes, because, yeah, obviously. I think the full list is actually in the wiki page,
Okay.
mentioned on the top.
Okay, great. Thank you.
Okay, I guess we can thank Klaus again. Okay, next we have Michael Weiler, who is going to talk about computing magnitudes, distances, etc. Thank you.
Thank you. Yes, the first presentation has been a quite broad overview. This presentation is going into some particular detail, I guess. The title is Computing Magnitudes, Colors, and Distances, but according to my previous experiences, nobody cares about computing magnitudes. People are much more interested in computing distances, so this presentation, which doesn't have so much time, will focus on the computation of distances, and I will just go in the end and show you that computing magnitudes is basically the same than computing distances from a certain point of view. So the question we are dealing with is, having measured for a particular star, for example, the parallax and the uncertainty of the parallax, what is the distance of the star and the uncertainty of the distance? This is a very harmless and innocent-looking question, and in fact it is harmless and innocent, but one just has to take a few little details into account to get it right. The first detail is what we actually mean when we have said we have measured the value for the parallax and the uncertainty of the parallax. Well, just as this little sketch here, assume we have some values here, then we say that we have a measured value and the uncertainty, which we give as an error bar. But what we actually mean by this is that we have determined a probability density function for the measured value. And as usual, we assume that it is Gaussian distribution for this PDF, probability density function. Then having measured the parallax and the uncertainty just means we have determined a probability distribution that is a normal distribution with a mean of the value and the standard deviation of the uncertainty we are attributing to its mean value. Usually one ignores this kind of thing, and this has a good reason, because, well, if one deals with normal distributions and one applies linear transformations, normal distributions go to another normal distributions, and you can just compute with the mean and the standard deviation. You don't have to bother much about the probability density distribution itself. But here we have to do with nonlinear transformations, so we have to go back to the full probability density distribution to get the result right. And if we have probability density distributions, we can use Bayes' theorem in this case, which links conditional probabilities. For example, we have the probability of some true value, the true parallax or the true distance, depending on the measured value. We have the probability density distribution of the measured value giving the true value, which is linked by another probability distribution, which is referred to as a prior, and a normalization factor to get the normalization right in the end. Very often in practice one ignores this prior, which basically means one assumes that it's a constant function, because if you multiply something with a constant function and normalize it again, you get exactly back to the same function again. So a constant prior just doesn't do anything. And well, this usually makes the probability distribution of the true value identical to the one of the measured value. So say the width of this table is 60 centimeters plus minus 1 millimeter, then actually the true length of this table is the same value, 60 centimeters plus minus 1. But this only works very nicely if the constant prior is constant over the range where this measured probability distribution is significantly different from 0, which is usually the case, for example, if we talk about parallaxes for high signal-to-noise ratios. Because if you have a high signal-to-noise ratio, it just measures how far the mean, or many standard deviations, the mean is away from 0. And, well, normal distributions stop off very quickly if you go away from the mean, so it doesn't matter. We can just use the constant prior everywhere, and it will just basically not change anything here because there is no probability anymore here. But this is different if the signal-to-noise ratio gets low, because then the distribution shifts very much towards 0, and we have a significant part of the probability distribution which laps into the 0 part. But we know that the true parallax cannot be 0, smaller than 0, because by just its geometrical concept, it has to be positive. So it cannot be the case that the measured probability density distribution of the parallax is identical to the true probability density distribution of the parallax. We have to get away with this negative part, and this is where we have to take a non-constant prior into account. And the easiest thing we can do is just we say the probability is 0 for values for the parallax smaller than 0, and it's constant for positive values. This is the simplest approach, and it's a kind of all-purpose approach because it doesn't take anything into account about the particular physics, what else we are dealing with, but it's just taking into account the logical a priori knowledge we have here. And this is not new at all, actually, at least not for parallaxes. For magnitudes, as far as I know, it is new. Nobody has done it there before. But it's done frequently from converting parallaxes into distances. And actually, this is fine, except for two issues that are coming up with the way it's done currently. Currently, I refer to this what is called the EDSD estimators, which is exponential decaying or decreasing space density estimators, which try to do exactly what I'm talking about here. And the two issues we have here is first the presence of a distance square term in the prior for a constant space density of stars. And a problem is a change from the parallax to the distance in this prior. I mean, you see, I was talking about true parallax and true distance and measured parallax, so there is a transition between parallax and distance we have to take into account correctly. So going to issue 1, the distance square term, this is something that goes back, as far as I know, to a paper by Lutz and Kalker from the 1970s. And the argument basically goes like this. Assuming we have a constant density of stars in space as a basic first assumption, which means that the number of stars per volume is constant, and then we just express this in spherical coordinates, then the volume element becomes a radial element times the area element, and in spherical coordinates, the area element has a dependency on r square times some angle dependency here. If we put this in here, we just get the expression for the radial density of stars, which increases with the distance square, plus some terms depending on the two angles of the spherical coordinate system. So we can just integrate this thing over some, whatever it is, solid angle, to get away with this expression here, and we normalize it, it just disappears. And we have to make a cut somewhere, because otherwise it's increasing to infinity with this r square increase. So we can just make a truncation at some fixed value, then we get a normalized probability for the star like this. Or we can follow Baylor-Jones, who thinks it's nicer to have an exponential decay with some scale length L, then the expression becomes like this, but there's always this r square term here, which suggests that we have to use a prior which increases with the distance to the square. And while this computation in spherical coordinates is actually correct, it's not appropriate to apply to the kind of conversion from parallaxes to distances. Just a little sketch, assume the solar system is here in the center, and, well, there are homogeneously distributed stars over here, and we have a star over here. We have a measured parallax. We want to know the distance of this star. And the distance of the star is where along this line, running from the barycenter of the solar system to the star. Where on this line is this star, actually? And in spherical coordinates, the number of stars increase quadratically with distance because, well, in a fixed solid angle, the volume increases with distance and it contains more stars. But we are not interested in how many stars there are in some element at some certain distance, but we are interested where is the star along this line. And if you would use, for example, Cartesian coordinates, then there would be no increase. It's just the fact that we express this kind in spherical coordinates. And yes, in many applications in astronomy, using spherical coordinates is a very good idea, but not in this particular one. Here we just have a simple geometric problem. We have Earth's orbit around the sun, very sketchy, and we have a line running from the very center of the solar system to the star. We have measured this angle, and its uncertainty, we want to know where on this line here is the star. There's absolutely no solid angle involved anywhere here, and with this, there's also no R-square dependency in the prior. So we just have to take this R-square dependency out of the prior. The second issue was the change in variable from parallax to distance, actually. And this is little except from the paper with which all of this kind of thing started from 2015. It puts down here the probability distribution for the parallax given the two distance, which is basically a Gaussian term in here. This is an 1/2 distance is a 2 parallax over here. Then it does the same thing again. We set it to 0 for smaller than 0 distances, because distance like the parallax cannot be negative. And then we just change the dependency from the distance and the parallax in here, just basically what I said before. But here now it concludes that if you consider the limit of the distance towards infinity, this expression here, if you express it as a function of r, will go to infinity, will go to a constant value, because this goes to 0 here, so just a constant value remains. And this is concluded that such a posterior, so the distribution of the distances, has infinite area, because it gets to a constant value, and cannot be normalized, and then we get into all the kind of troubles we have to do here. However, the problem is simply that if you have a probability distribution that depends on one variable and change to another variable, you cannot just exchange variables inside here, because it will just not preserve the overall probability. It just becomes non-normalizable in the end. And actually what one just has to do is, one has to equalize not the probability densities, but the probabilities directly. So the probability of, depending on one variable, say the distance, times the distance element has to become, unmute, I don't know what it does. And you have to go to the probability depending on the parallax times the parallax element. Because in this case, the probability computed over the same interval expressed in distance on parallax remains the same. So you take this to the other side, and you just get another term here, which is the derivative of the parallax with respect to the distance. This is just one special case for the general transformation of probability density functions you find in textbooks on probability or so. If you have a random variable x, and you transform it with some function to the variable y, you have to get, well, the basic change of the variables, but the derivative term of the transformation function in here. And the absolute value that is missing here just comes from the change that also the integration limits change if this is negative, so we can just take the absolute value in here. So we have to have this derivative of the parallax with respect to the distance, and this gives another 1/r² term. And if you include that in the computation, everything is perfectly fine and normalized, and there's absolutely no issue whatsoever. We just get the correct probability distribution in the end. So the way is just we have a probability density function for the measured parallax, which we assume to be a normal distribution. Then the PDF for the true parallax becomes a truncated normal distribution, because you have to get away with the negative part. And then we just do the correct transformation to distance, and then this is a probability density function for the distance given the parallax and its error, and including the non-normal negativity of the distance and the parallax, which is the same in here. And now this is perfectly normalized, and everything works perfectly fine. And having this probability density function, we can integrate this to get the cumulative distribution function for the distance, and we can invert this to get the quantile function, because this is a nice thing we want to have if you want to compute any kind of estimator for this. You see the quantile function has a very similar structure than before. It's just 1 over the parallax, but it's just an additional term multiplied between the error we have on the parallax and the correction function. And the correction function is also a closed form. It's just given down here. This is how this looks like, a pretty harmless function, in fact. If we have the quantile function, we can just use an estimator, for example, the median, which is a good estimator for asymmetric functions. We just have to put in the value of 1/2 in this correction function. Over here, we get an expression for the median, the expected median here. And we can compute some error intervals as well, depending on which quantiles we are using. I like to use the one for the standard errors, but you can use anything you want in here. So just showing what this means in practice if you use the suggested and correctly computed estimator as compared to the previous ones. First, we can do some simulations, because simulations have the advantage that you know the true distance. You just put it in and then compute the parallax, add some error, and try to recover it in the end. And this is two examples for simulations. These are 5 million sources. In this case, the error on the parallax is just 10% of the two parallax plus an error flow of 0.1 milliarc seconds. This top figure here is using the EDSD estimator, and this one is the estimator just shown you before. It gets actually a broader distribution than before, but it's clearly a less biased one, because you see this blue line here is the running median, and the points here give the signal-to-noise ratio that decreases in this direction. Here you see already a systematic deviation in the median at about a signal-to-noise ratio of only 3, well here up to 2, it's actually quite well in agreement, then it only starts to deviate, and it deviates less, so it gets less biased in this case. This is another case taken from one of these papers I'm talking about. This takes a uniformly distributed fractional error on the parallax in this range, and no error floor. And here the differences are even more pronounced in this case. In this case, you get an overall bias all through the range. And this very strange thing here, which results from the fact that the EDSD estimator is just not continuous. At some point, it jumps to higher values. So these stars actually belong here and got up here. And this disappears here. You see no systematic deviation at all. The blue line is basically invisible here. You just get a little bit broader distribution, but it's not biased anywhere. Both of these things are quite artificial, admittedly, so we can use some real data to see what it does there. And this is one example taking a comparison between Cepheid distances derived from the light curve and the Gaia NIR, I think, distances, parallaxes transformed into distances. This is taken from this paper over here, how it looks like in the previous version, and this is how it looks like with the estimator suggested right here. It's not a shocking difference, I have to admit. The scatter of the data points just decreases a little bit, but it's clearly less biased. So the mean of this distribution of data points here goes from 16% to only 4%. In this version, it goes pretty much down. So it's not a dramatic, but a clear improvement. And another real data comparison is, for example, if you compare Hipparcos with Gaia, because we can take the parallaxes from the Hipparcos catalog and compare it with the Gaia parallaxes, which have a much higher signal-to-noise ratio. That's the point of Gaia, actually, to be much better than Hipparcos. So we can take this as a good estimate for the true parallax. Then we can compare how the conversion into distances works. And well, you see again that this estimator I'm talking about here gives a broader distribution, but it's clearly less biased. You see again that the running median stays closer, much closer to the expected value than in the case up here, which turns out very much earlier. This is just a simple comparison if you just compute the distances for the same sources with two different ways. So take 5 million random sources of distances published by the Baylor-Jones paper, and compare it with the ones used here. And you see in the over-distribution there is a strong effect, but most of this effect comes out from sources with negative parallaxes, and it just goes to different limit distributions, so this is not so dramatic as it seems. But even if you go to pretty higher signal-to-noise ratios, in this case signal-to-noise ratios of the parallax, observed parallax between 2 and 3, where you should get quite well values, you see a broad general deviation between the two results, and you see this very strong broad region over here, which is what I just mentioned before in the simulation. This is the part that start to jump in this EDSC estimator to much larger values. They actually put below here. And even at already pretty high signal-to-noise ratios between 3 and 4, you still see a systematic deviation, and you see still a cloud, which the EDSD estimator gets wrong because of some reasons. So it really makes a difference. It gets away some systematics basically everywhere, and it can, in some cases, give a significant improvement where the previous estimates are basically up to an order of magnitude or 2 wrong in distance. So to come to an end, the magnitudes are just the same. In a sense, we have the same problem. We have a quantity which cannot be negative, which in this case is the flux measured in, for example, photons or electrons per second per square meter. And noise can put the observed values into negative regions or tails into negative regions, and we compute a magnitude, which is also a nonlinear transformation. So we just have to apply the same kind of correction. The flux in electrons, for example, have to be added a correction term. It's the same correction function and the error on this thing, and then you get a magnitude which takes into account the non-negativity of the flux and nothing else. And you get error intervals in the same way as before, just replacing the reciprocal relationship, nonlinear transformation you have for the parallax to the distance to the minus 2.5 times log variations. You have to go from fluxes to magnitudes. And if you have this on magnitudes, in 2 magnitudes, you can go to fluxes. And I show this just for fun because I think it's probably the longest equation I'm ever going to publish. but this is all just normalization stuff you get right here. The very much distribution is actually quite simple function. And given some signal-to-noise ratio in the two filters, this is the exact solution for the probability density function of the color, taking non-negativity into account. And you can also combine one flux or magnitude with the distance, and you get to the absolute magnitude distribution, which gives also a very nice lengthy equation, but a full solution, and you can work on with this computing means or quantiles or whatever you want. So with this, I'll come to the end. To summarize, first of all, I just want in the end to highlight where possible, work with the parallaxes or the fluxes and not with the magnitudes or the distances. This is a recommendation that has been given a long time ago, and I'm not giving this presentation to go away from this. I still fully agree with this one. But if you go to distances or magnitudes, you better use this estimator over here, because it's not only correct, it gives also less biased and more accurate results. And it's easy to compute because it's just one simple equation you have to put down somewhere in your code. It's an all-purpose estimator in the sense it doesn't take any physical information into account, just basic logical a priori information, so it can be applied to any source or any situation. There might be better ones for a particular science case. You have to work it out yourself in this case, but this one can be applied everywhere and it can never go really wrong. And finally, this bias stuff, I think it has some kind of mystical air around it or so. It doesn't do any kind of wonders. If there is no more signal, it cannot give you a measurement anymore. So it will just go to a limit distribution, which will only depend on the noise. But the parallax will just go to a normal distribution centered on 0, and the width will depend on its noise. So the true parallax will go to a truncated normal distribution, and the distances will also go to a distribution which is fixed and will just depend on the noise. So you have to be aware of this, that if you go to faint values, you don't recover anything with any prior. And that's it. Thank you.
There is time for one question. Questions?
Will you publish this? Will you publish this and compute it for like large scale?
Yes, well, I'm going to publish it. There is already a manuscript available on the archive, so if you just Google the title, you will find it. And actually, the values have been computed, and this person over there has made them publicly available, so this is actually all there. The only problem is that the first manuscript has been rejected by the referee, and I totally disagree with the referee here. I will resubmit it to another journal, and hopefully I will have a bit more luck with that one, but I still fully stand by the manuscript you will find on the archive, except that there is a typo on the last equation in the normalization, but I think it will not matter much for any practical purposes. Thank you.
We can thank Kyle again. Now we start the marathon time of the short talks. So I would ask people to, oh yeah, thank you, Mark, to stick to the time because we are already half an hour late, so otherwise this will explode. And we will finish.
Oh, la batería se está agotando.
Oh, batería.
Pues no sé.
Okay. Well, we start with Francisco Paco Garzón from the IAC. Okay, who's gonna talk about the bar?
Tantotas, ¿no?
Yes. And if I may ask, just when the talk is finished, if the next speaker can come by so we are ready to go like...
I'll try to be fast.
Thank you.
Good morning. Thank you for being there, and thank you to the organizer for giving me this opportunity. I'd like to show you, or to give a very brief overview of our recent work that, well, I would say Martin and I think we've missed the authors. Most of the work, if not all, has been done by Martín López, Corredoira, and I made a very short contribution on that. We just submitted the paper to the journal, so if accepted, will be public in weeks or if not months. Okay, so the idea behind this work is to study the morphology of the long galactic bar. We have made some several publications on that topic, studying the distribution of stars in the inner part of the galaxy, and we have also made use extensively of Gaia data in terms of distances coming from parallaxes. We have just learned about the way we should do with this. Now we were interested in revisiting the data with new approaches to check whether we can say something different from the extent of the long galactic bar and in particular of the position angle. Also, we tried to say something about the morphology of the 3 kiloparsec ring. We followed several methods. We selected M giants from WISE in 4.6 micron band, cross-correlated with 2 mass to get colors. We use apogee with distances derived indirectly from Gaia. So most of the value-added catalogs in apogee which contains distances have used different methods, polynomial neural network that have been trained with Gaia data. The cross-correlation, so the number of the coverage of apogee sources with Gaia is rather low, in particular in this inner region. So we do expect that if Gaia NIR comes to reality, that will change. Also, we have used O-rich mirror variables in the galactic plane and revisited the red clamp distribution versus distances and several things. So I will not go through all the topics because of time. As I said, the paper has been submitted, so you can, if interested, you should have the opportunity to study it. So originally, going very quickly, if we use we have selected the 4.6 micron band in the WISE data, which contains in this region in longitude from plus 40 to minus 40 and in latitude from plus or minus 5 to go through the inner region. We go here something like 700,000 stars. We selected a cut at M46 brighter than 8 to avoid saturation and also to get good coverage with 2 mass cross correlation, so we can make cuts in colors. So also we made some quick estimate of the extension. To the extension at this wavelength is small but not negligible, in particular in the inner region. So we made some numbers on how can we make an easy model of the extension. We cannot use 3D maps because we don't know distances of these objects. So we have to make some kind of estimate of each individual object extension based on colors in this case. So we made we appointed to a low extension area, and we make some mathematics, and we derive an easy model for the extension, and we can correct the maps for the extension. You can see, or in the original map, you can also see this asymmetry between the positive and negative side, which is very well known. It's interesting to know that we have also this maxima in L-24, which seems not to be connected with the bar. So if this asymmetry is due to the bar, this peak is not connected with the bar. So in the extinction corrected map, this is a bit more clear. So from here, we are making some assumptions about the extent of the bar. We can derive some numbers for the position angle of the bar, but also for the extension. You see in these plots different cuts along the galactic plane and perpendicular to the galactic plane in the right panel. The asymmetry is quite clear. The extension of the width of the bar and let's not count the bar. The width of the bar in this geometry is also can be derived from here. And you can see that, for instance, here in the black curve, this asymmetry is extremely marked. And from here, we can derive an extension of the bar, a position angle of the bar of about 36 degrees with respect to the sun galactic center direction. There is many things behind that. I will not go through all of this. If we move to the apogee, in the apogee we jump from several 100,000 stars to a few tenths of a star. The coverage of apogee is quite low in this area. The advantage of this, in this case, we can get distances from each object. The distances, as I said already in the beginning, has been derived from in the set that we use from Delworth that has been trained using Gaia data, but are not distances from Gaia. So the coverage is not full, but also due to the selection strategy at apogee bigger for target observation, we have this very sparse coverage in this area, but with the good point that the number of star per magnitude bin is constant with distance. Making some numbers with color cards, we can get a very clear feature, which is very well aligned. You can see this curve, this trace in black is curved because of we are plotting here longitude versus distances. So that corresponds in the XY plane, that corresponds to a straight line. In particular, we're using distances, maximum of the density instead of maximum of the counts. So the projection in this diagram is curved, but now the angle is about 25.6. Jumping from that to the end, just because of time constraint, the model distribution of the morphology of the different components in the inner galaxy that we are proposing in this paper is depicted here. So we have a more or less well-aligned bar and inner bolts with a position angle close to between 25 to 27. We use also the oxygen-rich Major variables in the ogle, which gives basically the same numbers. I'm not quoting the errors here, but the errors are all the errors in the different numbers are compatible with each other. So we are all together in the same line. But still, distances are needed. So this is what we are expecting from Gaia NIR. I'm sure that David Hobbs will tell us many things about the expectation from this mission, but we can jump from the milliarc second to the microarc second and possibly nanoarc second in position, and also in parallaxes because of the double epoch and also the new capacities of this mission. We will do much better. So the distance error, which is essential for this type of work, will be smaller than they are now. I will stop here because I'll give time for the presentation.
Maybe we can have one question, and the next speaker, I think it's Judith.
Just a question. When you show the WISE data at the far side of the bar at L equal to -20, -30, are there other tracers like mirrors that shows what is this beautiful feature at the other side of the bar?
You mean
is the mirror
in the mirror is also visible in the mirror distribution.
Is the mirror distribution?
So we are attributing this to the 3 kiloparsec ring.
Okay. Thank you. We will read the paper.
Okay. Next speaker is Judith Ardèvol from the University of Barcelona, who will talk about spiral arms.
So thanks. As most of you would know, the spiral arms in the Milky Way have been studied like long since long time ago with several tracers, but the question is still open. So in my PhD, I'm trying to get a little bit of more analysis about the spiral arms in general and also Milky Way spiral arms. So I will present the two papers we have already published with my PhD, and one is about simulations, the other one about observational data. Let's start with simulations. We used a simulation, a high-resolution hydrodynamical simulation of an isolated galaxy that has also star formation. And here you have on the left the XY plot together with the corresponding log polar projection. They are colored by the local dimension, D, which is a new parameter that we define in an article that it's already accepted and will be published very soon. And briefly, this parameter, what allows is to highlight filamentary structures, so to delineate where the spiral arms are. In these maps, they are these like orangish regions, which are like with half contours in dashed and solid lines. Let's now focus on the log polar plots because they are like commonly used for spiral arms. And now let's split the stellar particles by stellar populations. So we have very young ages on the top left plot and going to older populations. And we see that even the oldest ones present spiral arms. So the morphology between different stellar ages is not exactly the same. Old arms are straight lines in this projection, which means that they are logarithmic arms, while young arms are deviating from this morphology. And indeed, we are working on a new paper about this difference in morphologies across stellar ages. So let's go back to the amplitudes. We can quantify the strength of the arm in the vertical axis across the stellar age, and even if young arms are stronger than old ones, we see again that all populations are showing spiral arms. So let's move on to the observations. On 2023, we published a catalog of A-type stars. A-type stars are tracers that are between 0.3 to 1 giga-year old, approximately, and that can be easily detected, detected, let's say, using only photometry, and you can obtain a sample with low contamination just from photometry. So we use IGAPs and also some data from Gaia NIR to obtain this sample. I added, just for completeness, the color magnitude diagram on the left, and on the right you see the surface density in galactocentric coordinates of this sample. So the galactic center would be at x equals 0. So here in dark we see the overdensities of this sample, which we can link with the local and the Perseus arm. And now, yes, if we add the literature arms, for instance, from Masers of Rate et al. 2019, or from upper main sequence stars from Peugeot 2021, we can see that despite the completeness effects and the selection function effects that every observational sample has, A-type stars align with the literature value. So, going to the kinematic point of view, this sample also shows us a kinetic signature of the galactic warp. Here we used the velocity in the direction of the galactic latitude as a proxy for the vertical velocity, and towards the anticenter, the left in this plot, we see that the warps more or less starts around 12 kiloparsecs from the galactic center, which mixed with some results with, for instance, Romero Gomez et al. 2019, we may conclude that the warp is starting at farther distances for younger than for older tracers. So to conclude, the take-home messages is that Milky Way, like hydrodynamical simulations that has called kinematically called stellar disk, presents stellar arms for all stellar populations, even the oldest ones. A-type stars are also have overdensity that are also aligned with the literature spirals, and then the spiral age is a variable that should be included when studying the galactic structure. So thanks. If you need any details, you can just go to the papers or ask me in any coffee break. Thanks.
Thank you, Judith. And there's time for questions. Yes, Alfonso.
Thanks for the fascinating talk. I have one question from my complete ignorance on the topic about the hydrodynamical simulations. Are you treating dark matter, gas, stars independently together? Can you expand on those, please?
So, well, let's just go to... So this simulation starts from a dark matter halo with also a hot gas corona. This hot gas cools down and settles into a gas disk, and then this gaseous disk starts forming stars. So it's, we include the 3 types of particles, or indeed the simulation includes these types of particles, but well, it's like forming the galaxy, like halfway from a completely isolated and a kind of a cosmological one.
So the simulation is 3D somehow.
Yes.
All
so
right,
we have
okay.
X, Y, and Z.
Okay.
If
yeah,
this is
it's
the
a
question,
3D,
yes.
Yes, it's a 3D simulation. And okay, cool, thanks.
Thanks.
I guess we can go to the next talk. Thank you, Judith.
Thank you.
We continue with a little bit with spiral arms. Now we've got a talk about the local arm by Carmen Sánchez Gil de la Universidad de Cádiz, ¿verdad? Okay, so yes.
Okay. Good morning, everybody. I'll discuss the vertical kinematics of young star clusters in 3 nearby spiral arms, actually, in the local, in Perseus and Sagittarius. Imagine a calm pond, you threw in a pebble, and ripples travel outward. Now think of our galaxy like that pond with young star clusters moving up and down with a similar rhythmic pattern. Drawing on Gaia data, I show how these motions can provide new scientific motivations for a fusion infrared astrometric mission like Gaia NIR. We start from Gaia astrometry combined with recent catalogs of young open clusters and star-forming regions, focusing on clusters younger than around 30 million years in the solar neighborhood, and we find that they lie on a very tight linear relation between the vertical velocity and the height from the galactic plane. Sorry. This linearity is what we expect from, for a vertical harmonic motion in the galactic plane, in the galactic potential, sorry. This is the younger objects oscillate vertically like springs with their vertical velocity directly proportional to the displacement from the galactic plane, leading into a straight line. This behavior also allows us to estimate the effective local mass density in this work, where we also see signatures of large-scale vertical perturbations in affecting these young tracers. Now we are extending this analysis beyond the immediate solar neighborhood, in particular to the analysis of the full structure or nature of the local arm. We are building homogeneous four-dimensional maps of young tracers for within 7 to 8 kiloparsecs around the Sun, and mainly associated with 3 nearby spiral arms, the Perseus, the local, and Sagittarius. We include not only clusters, but also OB associations and molecular clouds, and these maps show vertical waves and corrugations that appear linked to a spiral arm structure as well as nearby star-forming complexes. However, where this vertical structure is more interesting in dusty and crowded environments, near or within spiral arms, Gaia's limitations mean that we only see a part of the full picture. So the Gaia's limitations are very clear. In dusty crowded regions, especially along spiral arms, we just lose a large fraction of the youngest and most embedded objects. For example, in the inner disk, the key and young clusters are heavily affected by extinction and crowding. So many of their faint or embedded members are missing from Gaia's view. This incomplete sampling hiddens a full understanding of the dynamics and the formation of these critical regions. So, or therefore, neo-astrometric near-infrared astrometric mission like Gaia NIR will overcome these current observational limitations by enabling access to obscure regions, providing much better vertical tracers, and revealing the time evolution of the disk galactic or the disk corrugations. Actually, our project already provides realistic phase distributions, space phase distributions, and also identify specific objects where near-infrared astrometry is critical, thereby naturally feeding into science cases as well as simulation requirements for Gaia NIR. To conclude, we show that young cluster acts like vertical oscillators. We are mapping the vertical structure of the young disk in the solar neighborhood. Gaia NIR is essential to complete the picture in these dusty and embedded regions, so we must advocate for its realization to unlock this hidden stellar information. Looking ahead, a mission like Gaia NIR could reveal part of our galaxy's stellar nurseries where actually is hidden by dust, and giving us a much more complete view of the young disk. And this is all. Thank you for your attention.
Thank you, Carmen. Time for questions? One here? If not, I have also some.
Okay.
Judith, maybe to Frederick? Sorry, I didn't. Sorry.
So, can I ask how these lines that you fit in the ZVZ plane, how do they relate to the phase spiral that was
You mean
found
this picture?
No,
Which one?
in the beginning.
The beginning. Here?
Yes.
What we did is estimation we use Kriging methodology from the sample to estimate this four-dimensional map. The points are the sample, and we estimate with Kriging, and then we use those estimations to represent by dividing the data for different age classes, up to 7 in log age, up to 7, between 7 and 8, and these are two different samples. And I'm showing you that from different samples we still see more or less the same behavior, and even when we compare with other authors, we are seeing agreement in our results. I'm not sure if that's what you're asking.
Now the question is, how does it relate to the phase spiral that's seen in the young population of the disk in Teresa's paper, 2018, for example?
Sorry, I couldn't listen to the question.
How does it relate to the Gaia phase spiral?
To the Gaia phase, because these catalogs are from Gaia.
Okay.
Well, we can discuss later, yeah.
I also have questions, but I won't use my
for later.
This as a chair, so for
Okay.
later. Thank you, Carmen. Okay, and next speaker is Carmen Gallard from the ERC. Let's see.
PowerPoint.
Yeah, let's see if it opens. Because PowerPoint is not installed here. Okay, but it seems to be okay. What I don't know is how do I make it full screen.
Pase de diapositivas.
Yes. Iniciar presentación. Okay.
Seems to be working.
Okay. Okay, so thank you for letting me present what will be a very broad overview of the Chronogal project with the aims and the results. This project has got an ERC advanced grant recently, so we are starting with the ambitious part of the project, and so far we have done some early results. So basically the goal of Chronogal is to derive, to answer a number of questions regarding the history of the Milky Way that have the need for age information. And we try to do that with the same methodology for all the different galactic components. So for example, for the halo, we would like to answer what is the accretion history and properties of the halo building blocks. For the disk, for example, when did the Milky Way thick and thin disks formed, and what is the role of mergers in the star formation history of the disk? And we also would like to reach to the galactic center with data complementary from Gaia and answer some questions about the possible episodic star formation in the galactic center, or whether there are intermediate age and young populations in the bulge. So our main observable, let's say, what we derive are age metallicity distributions with, which really encode a lot of information about the evolution of a galaxy. This is a simulated age metallicity distribution from a simulation. And you can see that there are a number of features in the plane. And because it's a simulation, we can see what was happening to the galaxy when we have these overdensities in the age metallicity distribution. Do we have a pointer? No. The cursor. Okay, well, it's not quite useful. Anyway, so this is a simulated one. We have all the stars on the left, young stars on the right, and then the age metallicity evolution. And in this case, we see that when we have more stars, a higher density of star formation is in moments when there is an accretion of a galaxy to the main one. In observationally, in galactic archaeology, what is usually done, these are derived from individual stellar ages, and this is an example of a state-of-the-art age metallicity distribution obtained in this way. And this is compared with an age metallicity distribution for exactly the same volume of the galaxy obtained with our methodology, which shows much more detail. And this is thanks to the synergic use of both. Okay, thank you. Okay. To the synergic use not only of the photometry of the individual stars and distances, but of the synergic use of both the position and stellar density across the color magnitude diagram. And for this, only photometry and distances are needed. So here we have both again, and you see that they have things in common. While they look very different, they have things in common. In particular, for example, you see that we have this increase of metallicity early on in the galaxy, which appears everywhere, and this broad metallicity range at intermediate and young ages. But in our data, you see that we have really increased precision that allows us to see that this is actually the composed of many age metallicity parallel sequences. And another important thing is that for this, we only need photometry and distances. This we can obtain for Gaia for a large volume in the Milky Way. And this allows us to actually compute the actual number of stars and the mass involved in this star formation. However, the drawback is that individual ages are not derived, and in a complex system like the Milky Way, in which ages, kinematics, and chemistry are very much intertwined, this can be seen as a problem for an overall picture of the system. To solve this, our methodology to really combine the information on chemistry, kinematics, and age, what we do is basically that we use kinematics and chemistry to select the stellar samples first, according to particular scientific questions, and then we derive the age methodicity relations for them. And here I show an example, which is one of the works that we have already done, in which we have selected, using kinematic information, the kinematic selections of thin, thick disk, and halo. Then, once we have these samples, we have a color magnitude diagram for each of them, which you can see that they are already quite different. And then we derive the star formation history independently for each two. And you see that the star formation history is really different in both cases. In the case of the kinematic thick disk, the population is basically old, and we see some detail actually in the same metallurgy distribution, while the star formation history for the thin disk is younger and shows many different features as a function of time. And if we wanted to, one question that we can answer from this is, when did the kinematic transition occur in the Milky Way disk? And we see that very sharply it occurs 10 gigayears ago. So there is a very clear change in the stellar populations 10 gigayears ago. Then we plan to do also selections based on chemistry, for example, on the alpha-iron plane, and for that, weave and foremost would be essential because we would need, it would be great to use Gaia as well, but maybe the alphas are not good enough, or not for enough, a larger enough number of stars. For this, as I say, weave and foremost will be essential. And there are also a number of scientific questions that for which also a pure geometric dissection, so defining volumes in space, would be another approach to create samples. And if I have 1 minute more, okay. So I will show another science result, which is also comes from a kinematic dissection, let's say. In this case, we have, okay, let's see. There is some picture missing here, but anyway, these stars have been selected in the angular momentum energy plane, okay. We have selected the stars belonging to Gaia Enceladus, and we have derived the star formation history for this stellar sample. And what we have seen is that, this cannot be seen actually as the star formation history of Gaia Enceladus, is of the sample of stars which is close to the solar neighborhood, okay? But in any way, in this stellar sample, what we see is that there is some tail of old and metal poor stars here, and then an overdensity at a slightly larger metallicity and younger age. This is done with a relatively small number of stars, so we were a bit suspicious about the result. We didn't really trust it exceptionally. But the fact that in an independent result with a collaboration team, the crosses are ages and metallicities of clusters associated to Gaia Enceladus. And you can see that they also form two clumps in age and metallicity space. So this is interesting and gives us more faith that this actually can work. And we are looking forward to having data from Gaia NIR 4, which will give us many more stars for Gaia Enceladus and therefore a much more strong solution. Now, we could think that this burst of star formation may have happened in Gaia Enceladus when it was starting to interact with the Milky Way, while when we don't have any more stars, we would have the merger of Gaia Enceladus. And now, if we put the same lines in the thick disk star formation history, we could see that, in fact, at the time of the merger, there is a strong burst of star formation occurring in the Milky Way thick disk. So yeah, that's all. Thank you.
Questions?
Karma, because, for example, in the slide 7, when you compare your detailed distribution with the one of Riggs and collaborator, how to say to the people that these detailed filaments you have here are really that, or which is a kind of error estimation here? How to simulate that really they are real? Do you understand my question?
Yeah,
because
yeah,
it's
absolutely,
strong, because
absolutely.
it's from photometry, so it's very hard.
Yeah, we have made very extensive analysis of the precision that we have in the derivation of the ages and metallicities. And at those, I mean, basically we have a 5% in the dating of the stellar populations, not individual stars, but the stellar populations. And so they are really there. And the other, I think the other external information that we may have is that we have analyzed very many different volumes, selected in different ways, kinematically, spatially, etc. And the features are basically the same, always, in samples that don't have stars in common. But we also, I mean, the paper also includes a very strong error analysis in which we show that the precision in age and metallicity in age is about 5% at all ages, the worst case, and the metallicity is about less than 1x, 0.1x. I know it's quite unbelievable. That's why we made so many tests.
Can I ask a question about this picture on the lower upper left there? So these lines, they always decrease, and from chemical evolution, you would assume that the metallicity is growing in the star formation with time. So that would, it's a bit counterintuitive. Why these lines are always going down where they should go up.
Well, I mean, these are just to guide the eye. It doesn't mean that there is this sequence of evolution. I mean, in this case, we probably, no, I mean, we have migration as well, okay? I mean, we may have stellar migration, some parts of this line, some of them can be from the inner part, some could be from the outer part. I'm not saying this is the case. We are still investigating that. And on the other hand, we know that there is also accretion of gas in particular moments, and so this can also lead to a dilution. So there is these two effects, and of course, understanding this is not trivial at all. And well, I mean, in any case, so would you think then that this is a scatter?
Do you also see that in the simulation? If you go back to the grant thing, does it also decrease?
Okay, sorry. Well, there is a range. Yeah. It's a simulation. In the other case, it's a real observation. Okay.
We need to move forward. Thank you, Karma. Next speaker is Marc de Alcázar from the University of Barcelona. Això? Okay, let's try.
Can we use the pointer for the rest? Sergio? Oh, yeah, that's true. Okay.
This is not working very well. Now. Yes.
Okay. Hello, everyone. I am Marc de Alcázar Julià, and I'm a PhD candidate at the University of Barcelona under the supervision of Francesca Figueras and also working in collaboration with Anne Gobin and Frederick Anders. And my talk will talk about similar things of what Karma just presented, so I will skip a bit the context, but the idea is mainly to derive also the star formation history, and in this case also the initial mass function of the galactic disk in the solar neighborhood using Gaia NIR 3 and the future Gaia NIR 4. So a bit of a context very quickly. So we know that the star formation history describes the evolution of the number of stars created in the galaxy with as a function of time. There are very different methods to derive them. One of them is by using the color magnitude diagram fitting, which just Karma presented and is also our approach. Others are using galactic chemical evolution models, and now it's very popular to try to derive this star formation history or this evolution of the star formation rate as a function of radius, because we know that different things has happened in the galaxy in different radius, and also maybe the models don't account for things like radial migration, so we can find very different features in this kind of analysis. But on the other hand, we have the initial mass function, which is popularly described using this potential equation. So what we aim to derive is this alpha parameter, which we can describe in different ranges of masses as well. And then what we know from different studies is that there's a strong link between the star formation history and initial mass function. So the goal of this work is to derive simultaneously the SFH and the AMF in order to analyze the discrepancies and Docker relations between these two parameters. The method that we are using is the Besenson Galaxy Model Approximate Simulations, BGM-FAST. The way how it works very quickly, BGM-FAST can be understood as a function of two parameters. On one hand, we have the model simulation. The model simulation is basically a catalog of what we would observe, a simulated catalog of what we would observe that is generated with the standard BGN, the standard Besenson Galaxy Model, a well-known galaxy model that has been extensively used for the statistical analysis of our galaxy. This is the first element, the first ingredient, and the second one is a set of the parameters that we want to derive. In this case, the different points of the non-parametric star formation history and also two of the three slopes of the initial mass function. So we put these two ingredients in this BGM-FAST, it runs and it generates a pseudo simulation, which is basically a model simulation in which each one of the stars has a weight according to the set of parameters that we have as input. So then we can compare this pseudo simulation with our observed data. In this case, as I said, we are using the color magnitude diagram, but we can go to other magnitudes. We can use, for instance, kinematics, or we can use chemistry. So this has a potential to grow in this comparison. And if we do this process iteratively, using the approximate Bayesian computation, at the end we get the posterior distribution function of the different parameters and also their most probable values. So let's move to the results. This is the work that we have already published, which is the fit to the full sky data up to magnitude G13, which is around 7 million stars. We tried with two different star evolution models, Parsec and Starebol, and then we did the exercise, similar exercise, but going up not to magnitude G13, but to magnitude G14. So this is around 14 million stars. And as you can see here, we have found a compatible result for alpha 2 and alpha 3, the two slopes of the IMF that we are deriving, around 1.5 and 2.0 of values. And then for the star formation history, this is the comparison of what we get at G13 in blue and what we get in G14 in red. And then with circles, you have the thin disk. With crosses, you have the thick disk. And as you can see, again, there's a good enough compatibility between the two results. And there are some elements that we find also in different works, mainly this dip at 6-7 gigayears ago. Also this extended bump in the star formation history. There's an important compatibility of this last value, of this growth of the star formation history in the last gigayear. And then we still have some drawbacks, some caveats in our work, which is to define the old population, which is very difficult to do that with the CMD. So what we are doing right now is basically to do a new derivation of the star formation history in the initial mass function using this G14 magnitude, more than 14 million stars, and now comparing parsec and vast TIAC. As you know, the stellar evolutionary models are one of the key properties of any galactic model, so we want to have the best ones that compare with data. Then we are trying also to study the evolution of the star formation history with the galactocentric radius. And finally, for future work, we plan to increase the limiting magnitude. It is complex because it comes with more errors and uncertainties in the data, and also to include chemistry and kinematics to better characterize this old population, and this will clearly benefit from Gaia NIR4 proper motions and parallaxes and radial velocities, and also from WIF and Formos. So thank you very much.
Questions?
Thank you, Mark. Just a question about this diagram. From 13 to 14 magnitudes, you increase the number of sources significantly, but the error bars look more or less the same. Why is that?
That's a good question. What I can say is that if we take a look to the color magnitude diagrams, which is at the end what we are fitting, we see very similar features, so very similar problems when we do the fit at G13 and at G14, which is basically the red clamp. The red clamp is complicated in stellar evolution models, and then also the low mass main sequence, which we don't get to fit. But I don't know now exactly how this would relate to the uncertainties in the star formation history. So I don't have like a clear and straightforward answer for this question.
Okay, don't see no questions. We can continue. Thank you, Mark. Ahora el texto está aquí. Okay, yes. Next speaker is Tetsuro Asano from the University of Barcelona. If I can open the slides, yes.
Hi, thank you. So I'm Tetsuro Asano from Barcelona. So I would like to talk about, I would like to advertise my n-body simulations and my work on galactic dynamics. So basically, the n-body simulation is a very useful tool to study the galactic dynamics. We can study something like internal perturbation, like bar and spiral arms, and external perturbations, like Sagittarius stars, and also most importantly, of the roles of self-gravity in the galactic disk. So in my study, I'm trying to infer the dynamical structure of the Milky Way by comparing the n-body simulations and Gaia data, which is basically a local snapshot of our galaxy. Then in my study, I use a GPU-based n-body simulation code called Bonsai. So using the GPU computing, we can achieve the very high resolution and also wide range of the parameter surveys. So now we have the two types of the model. One is isolated case and other is a part of the model. Then in both cases, the disk as Milky Way consists of the stellar disk and classical Bargy and the dark matter halo. And also in the part of the case, we have the Sagittarius-like part of it. Then we performed a large parameter survey and find the best fit Milky Way-like model. The rotation curve, velocity dispersion, and something like other parameters like bar length is consistent with observations, and also we have the 200 million particles in the disk. So this is my previous study about spiral arms. In this study, we worked on the breathing motion caused by the spiral arm. Breathing motion is like coherent, symmetric vertical oscillation. So here, right figure is made from the Gaia data. In the color show the difference of the mean particle velocity below and above midplane. So the blue region is indicated some compressing motion, and red region indicates expanding motion. In this plot, the most striking feature is this compressing breathing motion along the local arm. Then we made the same plot from our isolated model. Then we found that these features in the spiral arm, similar to the local arm, we found that this same feature, compressing breathing motion inside the arm region. Then I studied the time evolution of these features. Top panel showed the evolution of the density in R5 plane, and the middle panel showed the same map, but colored by the breathing motion and breathing velocities. Then bottom panel showed the time evolution of the complex velocity and the normalized surface density. So we found that in the evolutionary stage of the transient arm, dynamic arm, we found spiral arms showed a strong compressing breathing motion. On the other hand, in the disruption phase, we don't find clear correlation between the breathing motion and spiral position. So from this knowledge, we can infer that the local arm, the compressing motion of the local arm indicates it's in the growing phase of the dynamic transient arm. The second study is about phase spiral. Here we use a part-out Milky Way model. Right, it's from Gaia data by 122. They divided the local Gaia sample by the guiding radius and also azimuthal angle. So they found that in the Milky Way, so each panel showed the ZVZ phase space map colored by the density contrast. So in the Gaia data, we see the two-arm phase spiral in the inner galaxy. On the other hand, in the solar neighborhood or outer galaxy, we found that one-arm phase spirals. We also made the same plot again from our model. Then we reproduced this feature, and we studied why this spatial separation appears. Then it's a bit complicated, but in both the one-arm, the two-arm phase spiral is correlated to the Sagittarius impact, but the mechanism is a bit different. In the one-arm case, it's a direct impact of the Sagittarius impact. It's related with bending motion or the colligation of the galactic disk. On the other hand, the two-arm phase spiral is caused by the associated with the breathing motion caused by the tidally induced bar. So it's also the impact of the related to the Sagittarius impact, but it's an indirect consequence of the Sagittarius. And finally, we now working on the studying about the role of the self-gravity in the phase spiral evolution. In this study with Teresa, we basically compare the phase spiral evolution in test particle simulation. So in this case, we do not include self-gravity. And the same plot, same things from in the N-body simulation, which includes self-gravity. So this plot it corresponds to the GVG velocity map, but in a different projection. Then in the test particle case, the Sagittarius dwarf or some other perturber excite the dipole moment in this phase space map. Then soon after this perturbation, this dipole pattern starts wind up and become more and more tight. On the other hand, in the N-body case, the initial condition is the same, but before the winding, there's some non-winding phase. This is indicate a coherent oscillation of the galactic disk. So then
So many previous studies assume that self-phase spirals is a wind up constant rate, so it indicates time information. But our study indicated that to use a phase spiral as some kind of dynamical clock, we need to take account this non-winding phase due to the self-gravity. Okay, this is a summary. So N-body simulation is very useful. We study about many things about Milky Way dynamics. I haven't had time to explain about, but we previously worked on bar resonances and moving groups, and also the simulation is all the simulation data available at this page. So yeah, that's it. Thank you.
Thank you, Tetsuro. There is one question over there.
Hi, thanks for a very nice talk. I'm just wondering how confident are we that Sagittarius is the origin of all the phase spiral structure? I mean, every impact you would imagine would make some contribution, and is it also possible that other things like bar perturbations and so on could cause it?
There are many possible scenarios of the bar phase spiral formation. So, but yeah, the important point of that, whatever the origin of the phase spiral is, the binding of the phase spiral is mostly governed by the self-gravity of the galactic disk. So yeah, it's important to take account the self-gravitating evolution of the galactic disk to infer the perturbation time by unwinding phase spiral. So we can maybe, yeah, if this unwinding time inferred from a phase spiral is coincident with the Sagittarius pericenter passage time, so we can strongly claim that it's probably related to the phase spiral. Sagittarius caused the phase spiral. So if it doesn't match, we need to more seriously think about other mechanisms.
Okay. Thank you, Tetsuro.
Thank you.
And next speaker is Guillaume Thomas. I guess that's yours. Yes, from the IFE, Universidad de La Laguna, and he's going to talk about creating mock catalogs of dwarf galaxies.
Hi everyone. So today I'm going to present you how we can forge a galaxy, take forging a galaxy as a smithing a galaxy, or maybe the definition I prefer, or you can make fake money, right? So first, the first thing is, what exactly is a dwarf galaxy and why is it interesting? So dwarf galaxy, you have a lot of examples here. It can be as wide as the LMC and as small as just containing a couple of stars. For example, in unions, one, we have only 13 or 20 stars, something like this. So you have a wide range of objects. And they're really useful because they are really useful to probe the nature of dark matter, because this is the most dark matter dominated object in the universe. And furthermore, they're also pristine galaxies, which means that there's a building block of larger galaxies as the Milky Way. And so if you're able to study their formation history and their dynamic, you're also able to understand our own galaxy. So why is it interesting to make realistic mock of galaxies? So here, I'm not speaking of simulation, I'm just speaking, how can we recreate realistic observation-like models? So the reason is because to try to analyze the dynamic of dwarf galaxies, we are trying to use several codes. We have some example here. You can use different methods, for example, either solving the Jeans equations, or you can directly find also what is the stellar distribution function. The problem is that you have a lot of difference between the codes. Some of them are using binning data, some of them are doing individual data, some are using assumption in the density distribution or in the anisotropy of the velocity of the stars. Some of them none. And so the question is, when we use a code, what is the precision and what is the bias of each code? And for that, it's really hard to do directly from the observation. And for that, you need to get realistic mocks in which you know what is a true answer. And so here you have, for example, you have an example of the density profile that you can have from a simulation, a realistic mock of observation using a perma profile, where you have here the true distribution, and each point here represents some of these different methods or codes that have been used for differences for 1,000 stars. But even when you increase the number of tracers, you see that still you have a lot of differences between individual data, and the errors are not consistent with one to another. And so here the reason is we really want to get extremely precise and realistic mocks of galaxies to be able to test these different codes and to know which one is the best, or at least to know what are the bias and the prior we have inside. So here we have an example for one of the galaxy for sculpture of the density profile of the dark matter that we have in a galaxy using these different codes. And you can see that in some of the cases for the galaxy, we have something which is relatively close to a core, some of them to the cusp, and people then interpret what is the nature of dark matter from it. So you see that the importance of using a code and using the correct codes can have a strong implication on what is your conclusion. So to make a realistic mock, what do you need? You need to introduce realistic error. And Gaia is a really nice example of a very complex survey and all the implications that it has inside. So here you have, for example, just for the photometry, how can we quantify the errors and uncertainties of a really complex survey like Gaia? And for the photometry, you have in an area of 5 square degrees, in that cases, and here you have the distribution of the error in the Gaia G-band as function of the magnitude. And what you can see is that obviously the fainter you go, the more uncertainties you have, but you have also a relation with the number of times Gaia have been observing this area, right? It's shown by the color code. And the thing, you have exactly the same thing if I use the different bands, the RP and the BP band. You see that the number of times you observed, the more you observe, lower is your uncertainties at a given magnitude. So it means that contrary to what is usually assumed, the uncertainty is not only related to the magnitude, but it's also related to other extra parameters, in particular in that case is the number of times you observe it. And that's a really good moment to, or a really nice example to use machine learning to be able to predict what is the uncertainties on this, with these different parameters. You can do the same for the astrometry. In the astrometry here, what I'm showing is again, the evolution of the parallaxis error as function of the magnitudes, and you see again that you have a scatter when you go at fainter magnitudes. In red here, this is the official uncertainties given by the Gaia uncertainties pipeline in Python. And one of the things you can see, first of all, is that the uncertainties in that case depend also on the color. It's a bit slight, but you can see that you have a small gradient. The bluer you are, the more precise you are in general. Another thing is that you can also see that you have a lot of correlation with other parameters. Here, for example, you have the number of periods used for the visibility, and here is the astrometric match transit. So the number of transits you are using is directly a strong involvement on it. On this, reminded is that it's in a really small area. It's in 5 square degrees. So imagine over the entire sky, all this variation is appearing. So again, you can use neural network to do so, and it's exactly what I've been doing for the Galaxy Forger, and I've been able to produce realistic mock of galaxies, and you have 2 cases here, and I will let you guess which is the observation, which is the simulation. It's not exactly in the same area. You can see that you have some area in this one which is more dense because it's closer to the galactic disk, but one is an observation of the realistic dwarf galaxies, another is a model. So which one do you think is the simulation? We think it's A. We think it's B. Okay. Well, maybe I can help if I highlight. Yeah, indeed, the B is a mock. It's not extremely trivial in terms of all the parameters that you can see. So for me, the real guess was with the CMD. In that case, it's a bit wider, but in general, they are really similar. And so this, we already have using it to try to test different methods to identify stars members in dwarf galaxies, which is extremely important. For example, if you want to study the stellar halo of dwarf galaxies. And now we are going to use it also to test these different codes that I'm being showing before. to try to understand what are the biases of each of these code and how can we improve also these different codes to get a realistic, a correct answer, and to be able to know if what is the slope of the dark matter profile of a dwarf galaxy. Is that more cuspy or is it more core? And then to be able to infer what is the nature of dark matter. Thank you.
Thank you, Guillaume. Questions? Friedrich?
Thank you, Guillaume, for talk. Can you give a bit more information about the neural network and which is the input that you provide and the training sample analysis?
Yeah, so there is two neural networks. There is one for the photometry. For the photometry, I just give the magnitudes and the number of times it's observed in each band. And for the astrometry, I'm giving again the magnitudes, and I'm also giving the number of time, the visibility period used, the astrometric transit used, and that's all. There is a bit more correlation, for example, with some correlation factors that you have inside, but it's more negligible than these two other parameters. So this one has the two most important ones. Then all I can infer when I give a given simulation to reproduce the mock is I'm just binning the area, and I'm inferring what is the number, for example, how many times Gaia have been observing. Again, here you can see it's really important because even it's a small area around the dwarf galaxy, you have some area where you have significant change in the number of times you have been observing, so you have significant change in your uncertainties locally, which means that you have a strong impact. Here, for example, you have a variation between an area that have been observed more than 500 times to an area that have been observed less than 100 times. So it's really significant.
Thank you.
We thank Guillaume again and our speakers. Okay, with this we finish this first part of the meeting. A couple of things. The plan is to put all the slides in the webpage of the meeting. So this would be like by default, but if you don't want to put it for any reason, then you can tell us. You can let us know, so we won't do it. And now it's coffee time, and I think this is planned. We go outside, right, to the cafeterias that are around, because there's no official coffee here, okay? I'm not sure. I think it was supposed to be better. We are very late, but we should stop, no? Or 15 minutes? 15 minutes? So we start at 12. Las charradas? Yo creo que sí. A ver, bueno, se han de organizar.
Vale, vale. Jordi.
If you can take your seats slowly. We're going to have two longer talks by Jody Potet, and the first one by Alfred Castro-Ginard about the Spacious project.
Okay, thank you very much. I'm Alfred Castro-Ginard. I'm talking today about Spacious. You probably received many emails the past couple months about this, and now I will present what it is, make a okay, I can talk in the meantime. I will present what it is from a very practical point of view and also keep it very introductory level. So if you are interested in further details, just contact me after, please. Drop me an email or just find me. Control L. Yeah. Okay, thank you very much. So what's a Spacious? I have this in the middle for some reason. Okay, I can read that. So the first thing is, Spacious is a GRUT acronym. That's the first thing I like. So it's a science platform cloud infrastructure for outside users scenarios. And what we are developing here is a platform that leverage big data and data mining techniques to enable this code to data paradigm, which is represented here, where in traditional approaches, you will have the data archive, download whatever you need from the archive and work locally in your computer, while in the Spacious framework, you just upload your code next to the data, so in a similar archive-like platform, and the code works there and does whatever it has to do while you do nothing, which is obviously a lie, but this is the idea, you get the idea. So I say here that the platform is portable and open because we are developing the platform itself, not necessarily the computational resources, although for the nets here we will be offering them as well. And this platform is cloud native, meaning it's deployable in many different environments. It's deployed at the BSC, also in some other private computing centers that I'll show you later, but also in commercial clouds. And we are working together with Google in this case, but can be deployed also in Amazon's or other cloud services. And so far, it supports data analysis for Gaia data and Euclid a little bit through internal scientific challenges that are specifically designed to showcase the platform capabilities, and also we open this to the external community, as you are aware of. Okay, so why do we need a platform like Spacious? So we all know that the astronomical data sets are rapidly increasing. So having the traditional approach, like downloading the data, analyzing, and then publish, becomes increasingly more difficult with time. And here I took this slide from Jos de Bruine that presented how the volume of different ESA missions, data missions, will increase over time. So we are now more or less here. We are about to jump for this tiny red one, which is Gaia. We are about to jump to the half petabyte, but this is only the beginning for big data astronomy, right? So check what happens with Euclid and check what happens with Plato after. So downloading all of this will be basically impossible. And this is just ESA missions. If we consider the Vera Rubin Observatory or the SKA, that would be 700 petabytes a year. This is just 30, right? And 700 would be well 5 beyond this. So the need for platforms like Spacious is mandatory in this case. Okay, so what is Spacious? So in plain terms, it's a Python interface to work on a big data engine, and it works over distributed data files on a cloud native environment. This is a bit of summary, but basically you have a Python environment as you used to, maybe the notebooks, Jupyter notebooks we support, but you can also work on plain Python if you want. And you have the usual packages that you can work with Python. I put here matplotlib to show one, but all of the installable things in Python can work in Spacious as well. And then this works on a big data engine. In this case, we have these two flavors. One would be Spark, the other one is more Python native, which is Dask. We so far support Spark and are developing Dask. Over distributed data managed with this Apache Hadoop, and the distributed data comes in the Parquet file format, which is very fast and efficient for columnar tables. And that works on a Kubernetes cluster, and it can be deployed on different things. So the current deployments that we have and that we are offering is, well, the main one would be in the Barcelona Supercomputing Center. This will have this many CPUs, about half a terabyte of RAM and 1 petabyte of disk. As I said, we are also working on Google Cloud. The technical details for the Google Cloud are flexible because basically you can make your own cluster. It's just limited by the budget, and for this project we are counting on a budget with 100,000 euros. And then we have these private data centers basically in the UK where we have much larger number of CPUs, around the same amount of storage, and I think RAM is about 8 to 9 teras of RAM, something like this. The problem is that this is not specific for Spacious, so it has to be shared with all the community. So the idea is that if you run things in Spacious, it will be, or we will choose in this case to which deployment we run your code, and that will depend basically on the specifications that you require. Okay, but for the user, when they land on Spacious, what they see is this. So it's basically here you can make your own Python notebook, or even the console, and many other things with the terminal and the explore the data system and stuff. Sorry. And then you can also have here a set of defined notebooks that showcase how to use the platform. They are like tutorials, and we can have like how to play with the data, basic sort counts over the sky, or having average values over the sky as well, and then some other more advanced that I will go through now. So one of them is the analysis of the X-mean spectra in Gaia. So for DR3, we have over 200 million of spectra. That's a total data volume of 2.7 terabytes. But for DR4, this will be for the entire catalog, basically, and you will have 25 terabytes. So this example here that's worked out on the example notebook is basically you have these spectra represented as a set of n basis coefficients, plus the uncertainties, plus the correlations. Usually these coefficients are 55. And then the science case here is, okay, you have an example of a spectra, and you want to find similar spectra over the whole, in DR3, 200 million spectra that are in the archive. So for this, you need to compute, you have the spectra, you need to compute the distance of the two spectra, and then if you want to take the covariance matrix into account, you have to reconstruct the covariance matrix with these 55 times 55 elements, and then do matrix and vector multiplications. So basically, this is the example that we did in Spacious. So this will be the example spectra. And once you do all of this, computing the distance plus taking into account the correlations, these are the best 3 hits, more similar to this spectra here. I put here the setup of the machine in case you want to replicate this. But basically, this notebook took around 15 to 20 minutes to run over the whole catalog. And this is not just computing this distance plus variance matrix and all of this, but is also, after this is computed, you need to group the data and sort the data, which is not trivial over petabyte scales. Okay, good. Then another example is use machine learning techniques for analyze your data. This one here is you have a random forest. Okay, so if you get sources, nearby sources, and you build a color-magnitude diagram, you can see this is a pretty well-defined sequence with the Wardorf sequence here, but then you have some data here that is probably a bad arithmetic solution, right? So basically, in this example here is you get a random forest, train a random forest to classify between these good and bad solutions and see, apply it over your data set. I put this here not because I want to go through all of these, but just because I want you to see that this is basically how we will work in Python. So if you're used to working in Python, then you need basically no time to transfer your codes into Spacious. And the key thing here is that, well, from this PySpark library, we get the random forest classifier. This is trying to mimic the scikit-learn library for machine learning analysis. So if you are familiar with scikit-learn, this will work the same. And basically what you do is just, you get a training for good sources, training for bad sources, and then you the usual split in test and validation, and then train the classifier, as you would do with scikit-learn, to end up with this. In blue would be the good solutions, and in orange would be the bad solutions here. The caveat here is that from PySpark, so they are trying to mimic whatever algorithm you have in scikit-learn, but none of them are present. So in this case, we are lucky that the random forest is present, but for instance, for clustering, there's only the k-means present there. So if you want to do another type of clustering, it's not that it's not possible, it's that you have to work out your own solution, which is not impossible either, and we can offer support and help. Okay, another example is the computation of distances. I'm aware of the talk in the first half that this is not how you should do it, but anyway. So this is not to highlight the science, but highlight how Spacious will lift your capacity to run this onto the whole catalog. So basically, one first approximation would be the naive 1 over parallax. So basically, this is how you will work with the data set in Spacious, and you get parallax over error, and your new computed distance as 1 over parallax in under 1 second. And this is two important things. One is a very fast evaluation because, for instance, in this case, as the computation is done next to the data and the data is already distributed, and this only takes like the information in one row, the level of parallelism is embarrassing here. And then the second and also important thing to take into account is the lazy evaluation. That means that Spark, in this case, will not do the computations that it doesn't need to do. So this is under 1 second, but only for these 20 top rows here. So it's not for the whole archive. Although this is also pretty fast for the whole archive and scales really good. It will be of the order of minutes. Okay, so if we want to do something more complicated, although may not be correct as we have seen, this is Bayesian distances with different priors. This would be we define the likelihood. I again show this here not for the sake of science, but to see or to show you that this is working on plain Python. We define the likelihood. We define two types of posteriors, and then two types of priors, and then compute the posteriors, two types of posteriors. And the only thing we need to do in Spacious, for instance, is decorate these functions that will work directly on the data, and this will provide for the distance estimates using, well, show parallax error, 1 over parallax for distance, and then the two distance estimations with the two priors. And this is done in 4 seconds as well. So, yeah, pretty fast. Okay, good. But then in Spacious, we have a set of challenges to, as I said, both drive the platform development and showcase the capabilities. These are divided in 2 different sets. One, internal challenge, that's the ones that we define that we think will show better the platform, and these are the ones here. So one would be the star formation history and the stellar initial mass functions for the Milky Way. This is the work that Mark presented earlier today. Basically, this Spacious will allow Mark to lift this computation to the whole catalog or to fainter magnitudes. That's one thing. But then the other thing is that Spark itself has a very clever way of binning data and counting data in bins and aggregating over different data partitions. So this is a two-fold win-win here. Then the second one would be completing and characterizing the open cluster census in the galaxy. This is well, running clustering algorithms onto the whole Gaia DR3 in this case. And I say Gaia DR3 because this has to be run during 2026. That is also an important thing. And Gaia DR4 doesn't come until not before the end of, you know, the usual. Yeah. Then the third one would be a cosmological challenge, a large-scale power spectrum analysis. This I'm not directly involved in this one. This is the Euclid side of Spacious, worked out in Edinburgh. And then the third one would be enhancing the Gaia, the Gaia data with enhanced data products. And I put here a specific case that I was working on, which is the Gaia selection function. I will not go into the details, one, because it's not important here, and two, because this model is already deprecated, but the comparison still works. So over the 2 billion sources in Gaia, if we run the same model in Spacious or the same model in a traditional HPC cluster, would be like Mare Nostrum, or would be like whatever cluster you have in your institutions. So downloading the data, running the MCMCs, and then producing the results in an HPC cluster, it will take about a week, and in Spacious it takes about 25 hours. And that is, well, that is on a similar level of number of cores and all of this. And this is basically because of the very smart optimization that Spark does, orchestrating the different executions. Then we have community science cases. As I said, you probably have received many emails from me encouraging you to participate in this call. We have received 5 participations that are currently being evaluated, both in terms of quality of science and in terms of technical feasibility. The results should be out soon. And then we probably have, well, not probably, we have more than enough resources to offer this to you, basically. So if you think Spacious can help in your science and can lift your analysis from limited proof of concept to production scale, then just talk to me, please, and we will figure it out. Thank you.
Hi, thank you for this overview. It's very useful. If it is possible to upload data there, I mean, for example, if I need the stellar evolution models, could I upload the data that I need to do the analysis?
Yes. Yes. The amount of data that you can upload, then we will have to evaluate that, but yeah, you can probably. Okay. Oh, there's one here.
There's one thing that perhaps can prevent people from asking for working with Spacious, which is oftentimes we are just used to run things on our laptop and whatever. So the idea of saying how many CPU hours you're going to require for your, are you considering giving series of tutorials, could be even a YouTube video, or just courses which could actually teach the community of using the platform and to ask for your resources? That would be awesome.
There is a set of tutorials that are already in the platform, so something I forgot, sorry. You are more than welcome more than welcome to go into the platform and register yourself, get the user, and then try it out. That is already can happen now. And there is a set of tutorials already in there that you can browse. We're also developing a little bit more advanced tutorials if you want to but then we don't have like courses and videos on this. This is mainly because we are now in the developing stage, right? But what we do offer is a massive support both from the engineers here and from the scientifics.
In the chat from Pedro Alonso.
He asked if you have, what are the estimates of the Bayesian distances, mean, mode, median, quantiles? Do you have that?
Well, that I didn't show here, but that they are they come directly from the computation. So yeah, as I said, I didn't want to go into the science itself, just to show how Spacious will lift anything into the whole platform, so whole catalog. So yeah, no, I don't know. Could have done a plot probably, but yeah, sorry about that. All right, thank you very much.
Thanks, Alfred. Let's.
right, good. So I will explain to you something that could be called a mini species, so to speak, as part of this talk. But the main focus will be an exercise that we did to show the kind of synergies that you can do with the Gaia data already in DR3 and of course in the coming DR4. So here, well, first of all, just a reminder that the spacecraft is over. The mission waved goodbye to us last March. It was a quite emotional day, a very nice one. But the mission is strongly going on until 2030, until we finish DR5. Before that, DR4 in this year, of course. But with all these, the kind of things that we can, even before reaching DR4 and DR5, we can do very nice experiments with the kind of tools that Alfred has explained. Like, for example, one of the things that we played with was what I call this machine learning for dummies, like myself. I don't consider myself an expert on machine learning at all. But nevertheless, I was able to upload the DR3 Gaia source, just this table, to the Google Compute Cloud, start them some AutoML, some automatic machine learning algorithms, ask him to estimate the absolute magnitude from some fields from Gaia source, just Gaia source, no spectra, nothing else. And here you can see the kind of HR diagram that we get just with the original Gaia source, with the absolute magnitude from CU8, if I recall right, and the ones estimated from these machine learning thingies. So I didn't enter into details. I'm not an expert neither on absolute magnitudes and profound science in Gaia and so on, but it was looking quite good to me. So it's food for thought that we can try this kind of experiments that Alfred also mentioned. But anyway, going into the R4, we are approaching even bigger data than what we have now, as stated already. As a reminder, versus the R3, we will move from 2.8 years of data to 5.5 years, and in the R5 it will be 10.5 years, so even much more. We will go towards 2.7 billion sources from the 1.8 that we have now, including low quality sources, as you will see. APOC data for all sources, this will be really a game changer in the R4. It's one of the most interesting things that we will get. These APOC tables will have over 100 billion records, and overall it will be close to 500, between 4 and 500 terabytes versus the 10 terabytes that we have now in the R3. And you will be able to see very nice things like, I don't know, this scene that you see here, two presumably binary stars, the trajectories that you see of them. You can very clearly see the effect of the parallax, the proper motion, even a bit of the orbit that we seem to have in these short period binary, resolved binaries. So very interesting things that can be done. So I will not insist anymore. Alfred said that very clearly, that the science interpretation approach must change. So there are these preparatory efforts towards what will come in the R4. But on our side, for now, at a smaller scale, and some toys or some tools that we're preparing for you to get used to those, we made this experiment of data fusion between the Gaia VR3 and the J plus DR3. We already have DR4, actually. Some of you may know the Javalambre survey. It is a very nice one. Here you have the photometric passbands of a Gaia, the broad band, the G band, and the blue and red bands. And here you have the several bands that we have in J+. It's, I think it was in your words, Seska, it's exquisite photometry, so it's pretty nice. So it's very interesting to do this kind of fusion of the tool catalogs. As a proof of concept, this is the number of sources that we took, just doing some pre-selection of the sky region that, of the sky region that J Plus is observing. It's just these regions here in the third release that they did, a bit more in the R4, of course. And then we cross-matched these 47 million sources, more or less, and to prove this concept, we aimed at improving the star-galaxy classification that we already have in Gaia DR3. So the method done by Elia Villar, a colleague at the UB, who is now working at ISAC for Gaia, it was based on this LSDB tool. You may have heard about that. It was originally devised for the Vera-Rubin telescope, I think, preparing the data in HATS format, and then just querying the J Plus archive to get the data, downloading actually the Gaia VR3 Gaia source, and then using Dask, as was mentioned already, with Python and so on, doing some cross-match with adequate margins, and so using 1 arcsecond radius. And we get this number of matches between the two catalogs, 23.3 million sources. It is worth mentioning that we cleaned up some boundary effects, because in J Plus we have images, and then from those images, it's like the old photographic plates that you have from old surveys. In the margins, in the edges of those plates or those images, there seemed to be some duplicate matches in the official cross-match of the J Plus people with Gaia, so it seems that we managed to improve and clean up some of the issues that we had there. These are the results. You cannot read that. This is the distance, 0.2 arcseconds here, 1 arcsecond here, so the median match distance is 1, 2, 3 milliarcseconds. And the most unmatched J Plus sources are, of course, at the faint end, because it goes a bit beyond the magnitude limit of Gaia. I think that it's these red sources here. And the matched sources have a quite nice distribution in magnitudes. Then we go to the galaxy classification results, because we took 3 classifiers in J Plus DR3 and the 2 classifiers that we have in Gaia DR3 from the extended objects unit and from the CU8 unit. So using these 3+2 classifiers, we get 285,000 galaxies, which we could consider bona fide galaxies from the both catalogs. And it may allow improving the work towards DR5 already in Gaia, because they are already starting to prepare the processing for the final release. And here you can see, for example, in green, this is magnitude, and these are counts. These are the sources that only J Plus, but the 3 classifiers of J Plus consider as galaxies, but known from Gaia. These are typically faint. It makes sense, because probably they are just too faint for the Gaia XP spectra, which are the ones more reliable to classify a source as a galaxy. So we have a very low signal-to-noise ratio there. The orange ones are those where everything coincides, and the blue ones are those that Gaia claims they are galaxies, but J Plus says not. So this perhaps could be cleaned up towards the R5. So now I present to you this Gaia Javalambre DR3 Plus catalog and service. I will explain you now. If you have any other name idea, it's a GJDR3 Plus. Suggestions welcome. So this is the overall view of the catalog. This is the source count, the source density on the sky that you are used to see from Gaia releases. And these colored ones are those where you have a match in J Plus and the J Plus catalog. Also here in this, we prepared a kind of Frankenstein of catalog, joining the Gaia source from DR3, the epoch photometry from DR3 as well, from Gaia DR3, so you have everything in the table, and also Michel's distance estimator determined, the talk that we had this morning, determined from the inflated parallaxes from the recipe, no, it was from the recipe of Lennart Lindegren in the VR3 papers, if I recall right, plus the inflated parallax error from L battery, if I recall right. So altogether you have these additional indications, these additional fields from Gaia, plus these J plus photometric bands and star galaxy classifications, as well as the match distance. You have all this here at the BSc in this URL. You can download the data. Despite having added all these extra fields and information, it's smaller than the official GaiaSource.csv.gz bulk download files from ESA, because we provide that as Parquet files, which are columnar, so it's more efficient. And for thermal using, beware with this Z standard compression in Parquet, which not all tools support. But it's good that you try this on your tools, because in principle DR4 from Gaia, the bulk download will be published like this, with Z standard compression in the Parquet file. So it's a good time to rehearse your tools here. Then I say that we also provide the service. This is based on what we call the Magic Duck. It is based on the DuckDB database. Really, really cool technology, quite recent. I really suggest that you give it a try. It's super efficient on, it's a very fast database, columnar based as well, like Parquet. So we prepared and ingested this GJDR3 Plus catalog in this database with Jupyter, offering Jupyter notebooks, deployed in Docker using OpenStack at the BSc and so on, these kind of technologies. Kindly provided by the Barcelona Supercomputing Center. We have these resources. It's not super, and it's just one single node, not several nodes as a Spatios. So this is why I was saying this is a mini Spatios. But in some use cases, if you just need source-based information, not all the full-fledged epoch information, and not the spectra, because the spectra are huge as well, for certain tables that you may need, you may consider downloading that and using it old school approach, so to speak, but using this, because this is really efficient and it would free you from running intense queries locally in your resources. And you can even ingest that in some fast NVMe disks and so on, which speeds up a lot all the process. So it allows you to run very fast queries and generate plots, as I said. Under a minute, you can get a full high-quality sky map in less than 1 minute in one PC nowadays. It is portable because you can just pick up this. It is available in GitHub. You can look for that. And you can just deploy this in your center, your server, your PC, and just run it there locally. And if you prefer, you can just register in this online service and give it a try. But just let us know at this mail address, because we have to approve your request, okay? Then just some quick examples of the usual magnitude distributions. This was done in 36 seconds on the full catalog. Density plots, the usual parallax error versus magnitude, 1 minute and a half. The full sky density plot in 33 seconds for the full catalog. If I may just going here, I think, yeah. This is just to show you that you can also rotate the sky map if you prefer to focus on the galactic anticenter. It's also nice to see for certain cases. You can also do another video, never mind. You can also do cuts in parallax and show like an MRI of the galaxy. The density plot of the sources with epoch photometry, where you can notice the Andromeda photometric survey here. Sources without any neighbor in a given radius, which is another indicator that you have in these extra columns from Gaia. And then the sources that have J plus match and epoch photometry from Gaia. So it opens you some additional science cases, perhaps. And just a curiosity, some light curves. This is the days in Gaia. And just by chance, we found a Seyfert galaxy when looking for some of these bona fide galaxies in the two catalogs. And an HR diagram, on the contrary, on the sources that all the classifiers consider that are stars. And given that the J+ catalog, the J+ survey aims at extragalactic sources, I presume that they target low extinction regions, and therefore you can see that the HR diagram is pretty nice here in this case. So yeah, just a summary that you have to get used to these new approaches, and that you have this new combined catalog and online service. Sorry. Thank you.
Hi, Jordi. I just noticed on some of the plots there you showed galaxies down to almost 22nd magnitude with Gaia. Where exactly do you get that data from? I might have missed it at the beginning of your talk. If you look at here.
It is the G magnitude.
Ah, okay, it's the J.
It is the G magnitude from Gaia DR3, from Gaia source.
The G magnitude?
Yep.
Yeah, but I thought Gaia only downloaded down to 20.7.
Yeah, this is the G magnitude from FODPipe, not from on board.
Ah, I see. Okay.
Yeah,
okay. Yeah.
You know.
But I mean, okay, sure. But what I'm wondering is there any way to do other combinations with the data that we have already? You know, kind of joint solutions to very faint magnitudes.
I didn't get the point.
Yeah, I was just wondering if we have all of the data that's been processed, is there any other data that we haven't really produced in the catalogs that we could use for joint catalogs later on?
Probably.
Where you couldn't get, for example, proper motion solutions?
Yeah. It also depends on the epoch of these other survey from Habalambre.
Okay, we can talk about it after.
But yes, some things could be done, perhaps. But they are more focused on specific epochs. It's not so. There is also JVAR for variability, but that's a much smaller scale, I think. But yeah, could be investigated.
Just now in the coffee break with Sergio Simon, Sergio asked me about the possibility that the students from the high schools, let's say, ask from some data from Gaia, take some examples and so on. The question is, this catalog of 23 million with J+ data, plus the distances, plus a lot of colors, plus can be an example of things that they can really pick up one student from with the teachers, or can we have some special tutorials to help them, the professors, as Sergio said in this morning? So just an idea.
Yeah, in principle, in this online service, there are also some example tutorials. So you may also use them. You may just follow the same examples that we have here. They are quite self-explanatory, as that we have just a couple of them, not so many as in spaceships, but they could be useful also. Yeah, could be useful for them, sure. Good. Thank you.
Thanks. So, I assume there's no question online. If there is, just speak up. Eh? And okay, now we're moving on back to some science talks, but I can only just encourage you to speak to Jordi and Alfred about if you have any problem with the sheer size of the Gaia data. Go talk to them, and they will help you. Okay, let me see. And we're gonna we're gonna start. Sorry, we have to start with Santi because he has to leave. Sorry about this. Vamos.
Vamos a ver cómo se pone esto. To put it in full screen. Control L? Oh, Control L. Oh, yes, perfect, good. Okay, so I will try to be fast. I am going to present a result that we got together with Oscar Jimenez Arranz that is related also with some science that can be done once you have the Gaia data with this very high precision on kinematics, and is related with the LMC. So first of all the work started with these very nice results that Oscar got with all the full kinematics of the LMC. And specifically from the central region in where you can already see here in these kinematic plots that you see clearly the quadrupole of the bar in the center of the galaxy. The important point here is that I have been studying spiral arms and bars most of my career using simulations, and with the simulations we have all the information, so we can get very nice data and very nice results for all the properties of the bars, but this never happened before with real data. We tried with the Milky Way, you tried with the Milky Way, several people here, but you know, for obvious reasons, we are not reaching very well the central part of the galaxy, and it's very difficult to get this information. But we have another this galaxy that also contains a bar, and that is a bit more accessible than the Milky Way, that is the LMC. So why not to try to start studying the LMC with both approaches, the observational one, but also with simulations. And this is what we started doing. The first part, whoops, I think that I should switch it slides, as you can see in the number below, no? Oh my God, it's not working. Anyway, there is the 2 somewhere? No, there is no 2. Okay, I will just say it loud. In the second slide that is not here in this presentation, we started studying from the data one of the main properties of the bar of the LMC, that is the pattern speed of the bar. And this was a very useful exercise because, again, in simulations you can get the pattern speeds of the bar with different techniques, like, for example, finite differences with the different snapshots of the simulation, or also applying other methods related with the analysis using Fourier modes, the A2 Fourier mode. But with real data, the observers mainly rely on what is called the Tremaine and Weinberg method. That has a lot of assumptions that may or may not be applicable with all galaxies. So what we saw, and is shown in the second slide, is that the Tremaine-Weinberg method really, it works in very few cases in external galaxies. And we check that because when you apply the Tremaine-Weinberg method with the LMC, but also you apply the techniques that we usually use in simulations, that now you can use them in the observations because you have all the data from individual stars, then you end up with very different results. The surprising case is that using a method to test the pattern speed that is called Dennett method that fits very well with what you can get with finite differences, the bar of the LMC looked to not be rotating. Then we wanted to know how you can stop a bar, not a bar that is stopped slowly like the bars that we see in the simulations, but one that you can get stopped somehow, maybe with a tidal interaction. And for testing that, with simulations, we did this very big suite of simulations with an AMR code called ART, in this case only N-body without gas, but I will talk fast later about the perspectives for a future project like this one. And using this very big suite of 28 simulations plus some other simulations to test the numerical convergence, we saw that in some cases we could also see a bar that is stopped. And in fact, you could see this here, if this was a video, that suddenly in some moments after the SMC crosses the disk of the LMC, in this simulation, the bar is completely stopped for several tens, hundreds of million years. And this is also coinciding more or less with the morphology that we see in the LMC, with a single bar in one side of the bar. So after analyzing that, we concluded that yes, with the tidal interaction you can stop a bar, and maybe this is also something that we can predict to see in galaxies that we observe, in external galaxies that we also observe, and that we have also pattern speed determinations. Of course, the details on the origin of how the tidal forces stop the bar are not clear, so it's something that we are studying. And as a summary, first of all, we are preparing this paper about claiming clearly when you cannot use the Tremaine-Weinberg method. The second one is about that we demonstrated that the tidal interactions can stop bars. And the third one is that we are also actively working, hopefully soon, to produce the Kratos hydro with a star formation to see how these things change or not when you have gas and a star formation in the models. And this is all. Yep.
Hi, Santi, really nice work. So you were showing that the bar is stopping, but is the bar restarting after, or is that just that you destroy the bar? What is the evolution?
It's the very, very good question. If you go to oscarjimenezarranz.com webpage, there is the movie. In the movie, you can clearly see that basically when the SMC comes, it starts more or less destroying the bar. The bar is never completely destroyed, although there is a weak moment with a very low A2 mode. But suddenly after that is when it regrows, but it regrows being stopped. And when the SMC is very far away, then it restarts the rotation. And it rotates regularly like if nothing happened. So there is a combination of almost destruction and rebuild and continuation of the rotation. Yeah. And it happens in 4 of the 28 models. It's not just in a single model.
Okay. Control L, no? Let's continue with Andres El Pino.
Thank you. Okay, now it's my turn. Also, I just realized that my talk should be 5+2 instead of 7, so buckle up because I'm in a hurry. So, speaking about synergies, I want to show you how the J surveys, before J Plus was just introduced, can have a very good match with Gaia. Okay, so just to introduce you a little bit these surveys, I know you are very aware about Gaia NIR infrared. So I'm going to spend some time explaining what J Plus and J Plus are. These are 2 multi-filter photometric surveys being carried out from the Javalambre Observatory in Teruel. J Plus is being observed from a relatively small telescope, 80 centimeters, and it was designed to be the pathfinder for his bigger sibling, J Plus, that is being observed with the T250, a 2.5 meter telescope. But at this point, you may be asking, what the heck is multi-filter photometry? Well, it's just a fancy word to say that we are observing with many filters, right? 56 in the case of JPass, which translate to have a very low resolution spectra in every single pixel of the image, right? So this is providing a lot of useful information, SED fitting, and everything, you name it, right? JPass is already being observed, it's happening. It's gonna cover more than 8,000 degrees in the Northern Hemisphere, but for the moment, the early data release only covers 17 degrees. So for the sake of statistics, I'm gonna stick to J Plus for this talk, okay? J Plus uses a more modest set of filters, 12, but 7 of them are narrow filters and are located in very specific region of the spectra that contains very useful information about the chemistry and stellar abundances of stars, right? J Plus DR4 is already out. It was made public just before Christmas, I think, and it covers 5,000 square degrees with roughly 100 million objects on them. So what we want is to derive stellar parameters and chemical abundances for the stars here, right? Sorry, I didn't introduce this because I'm in a hurry, as I said, but the main goal, the scientific goal here is to study the Milky Way halo and the mass accretion history of the Milky Way, right? So we are going to do that using what is called data-driven method or machine learning. And what we want is some method that goes from a very low resolution spectra with 12 points to your favorite set of chemical abundances, right? So for that, first we are going to focus on training. Luckily for us, we are lucky. We live in a time of wealth of information, and we have access to many surveys with spectroscopic information from the stars. We decided to go with Lamos and Apogee just because these are the 2 surveys with more stars in common with J+. And just by cross-matching them, we came out with a list of around 100K stars for which we have effective temperature, log G, iron, and alpha abundances of 8 different elements, but for which we also have the J+ photometry, right? And we are gonna, and this is important, we are gonna use the J plus photometry to train our model, right? In the dependence of this chemistry, these chemical abundances with the photometry, right? Now, what model should we use? Well, we're gonna use Banjos. Banjos was already introduced in some previous talk. Banjos is, it was developed as a classifier, but in reality, it's just, it was conceived as a general regressor. And it's called Banjos because it uses Bayesian artificial neural networks. And the difference with regular artificial neural networks is that it treats the weights between neurons as probability distribution functions. And this is important because this allows Banjos to model not only the nominal values, but also the uncertainties, the correlations, and everything, right? Banjos is not new. You have seen it already classifying all the sources in J plus DR3. And the most interesting thing about Banjos is that because it's Bayesian, it provides the full probability distribution function for each one of the classes that we were, trying to use. In this case, QSO, star, and galaxy, right? But you have to imagine this as a 3D cube of probability. And this enables us to select objects that are like in between several classes. Like, for example, this is an active galaxy that is partially resolved, and you can see this long tail of probability between galaxy and QSO. Okay, so now let's go to the results for the test samples of stars. These are stars that were never ever seen by the model, but are like a subsample from the training sample, right? And what you're gonna see here in the y-axis is the quantity predicted by, the average quantity predicted by Banjos with J+, and in the x-axis, the true or the spectroscopic quantity. This is effective temperature, log G, reddening, iron, alpha abundances, carbon, magnesium, silicon, you name it, we have everything. Even oxygen and whatnot. Anyway, so if we apply this model to the entire DR4 in J+, up to magnitude 19, that gives you all of these for 60 million stars. I'm gonna be brief here, but this is the comparison between the J+ HR diagram and the training sample. But bear in mind that here in the left, you have 60 million stars, right? The same for the chemistry with iron and alpha abundances. It looks reasonable. And just to show you some examples of what you can do, this is a map of extinction, right? And look at all this structure, all these filaments of dust. And here the interesting thing is that we never use positional information during the training. So this has been derived just using the colors of J+. Not only that, but because we have precise abundances, we can now see with our naked eye some structures, streams, and such that come from the infall of material with different chemical composition in the Milky Way. And now it's when it becomes interesting, because we did this in a completely independent way from Gaia. Now we can combine this with parallaxes and to obtain 3D maps of whichever one of these quantities we want to study. So just to take home ideas is that the combination between the J surveys and Gaia are very powerful. We can derive abundances and effective temperature and atmospheric parameters for all the stars in the footprint. We are going to reach around magnitude 19 or 20 with J+, but we expect to reach magnitudes of 21 magnitudes with J+. All the results are going to be publicly available for the community to use. And also, I just wanted to mention that Banjos is a general regressor, so it can be applied to any low-resolution spectra, including Gaia's. Okay? So, thank you.
Hi, thanks for the talk. Maybe it's a naive question, but when you showed in this last section the color magnitude diagram, in the left, you have like two different giant branches. Mm-hmm. Why is it this?
These are different populations. One is mostly coming from the halo and is more metal poor. This would be the branch that you see on the left side in the redder color. And then the other one is mostly attributed to the disk. So it's more metal rich, and then it's redder.
Okay, thanks.
Hey, Andres. So I have two questions. The first one is, what's happened if a stars from a given population is not present in your training sample?
Wait, say that again.
What happens if you have an array of your stellar population which is not in your training sample? Let's say like rare stars, I don't know, like carbon-enhanced metapoor stars that are not necessarily present in your data set. What's happened? Like, or is it classified with your method, or what will be the value you get?
So to be completely honest with you, this is not the entire sample. For example, here I'm rejecting stars that have large uncertainties, because BAN just provides you with that uncertainty. So what happens when you do what is called domain shift, you step out of your domain, what happens is that BAN just will give you an answer, but also with a very large uncertainty associated to.
Okay. And then to which magnitude is your parameters useful in terms of uncertainties? Like I know that you need to go in U-band to get 0.03 magnitude to get metallicity of 0.2 dex or something like this. So what is until which depth can you really use this data set to get the metallicity distribution, log G, and so on?
But you mean in the predictions?
Yes, in the prediction, yes.
So to train banjos, I didn't mention this, the main table, the main training set is based on spectroscopy, so those are bright stars. Normally you won't go fainter than magnitude 16 or something like that. So what we do is to use data augmentation, simulating all the uncertainties associated to J+ photometry, trying to reach deeper magnitudes. And then we train with that. Now, what I'm hoping is to have good DESI data of faint stars. But for the moment, you know, to validate, basically. Okay.
Sorry. All yours.
Okay. Okay, hello everyone. My name is Juan Antonio Molina. I'm doing my PhD thesis at Centro de Astrología, supervised by Jesus Maiz. And the title of my thesis is to create a massive census in the magnetic clouds. So first of all, I want to introduce how I define a massive star for my work. In my work, I define a massive star as a star with an initial mass greater than 8 solar masses. This is basically based on how these stars end their life. And this definition is important because it includes OB main sequence stars, and also red supergiants, blue supergiants, and so on. And I choose the magnetic clouds because they are a great laboratory, because we have low extinction to study these stars, and also high star formation rates. So it's very great to study this type of objects. So I want to introduce also to you what is the ALMA Luminous Star project, because this census will be the fourth version of this project. This project started in 2003 by Cameron Reed and was based on creating a catalog of massive stars in the Milky Way. Later in 2021 and 2025, Michelangelo make a cross-match of this catalog with using Gaia. And my work is basically to publish the fourth version that we want to go beyond and study the element C, the large magnetic cloud, and the small one, the SMC. We want also to include the magnetic bridge that a lot of people is studying right now. So what data are we going to use for this census? Obviously, we are going to use Gaia DR3 data. We are going to start with the Lurie et al. 2021 sample that basically takes the data from Gaia, from the LMC and SMC, and filter it by astrometry and photometry. So it will be our initial sample, and we are going to combine to make a cross-match of this sample with SIMBAD. This is also important because we want to take all the data from the literature, just to check that we have all the information and to avoid missing some objects that could not be found in Gaia, for example. And also we are going to combine all this data with ultraviolet photometry and near-infrared photometry to have more information, and also because there are a lot of young massive stellar objects with high emission in ultraviolet, so that's why we are going to use, for example, Tarski-Harris for the inner regions of the LMC and SMC, and SkyMapper, for example, for the outer parts. And infrared survey, such as VISTA and TUMAS, is going to be used also for detecting, for example, B stars with plain disk. And we are going to incorporate the variability data from MANIZA-PEYANI 2023. First of all, to remove non-massive Cepheids, but also to have more information if some of you study variable objects. Okay, so how do we select these massive stars? It's a complex process, but I'm going to resume this only in 3 steps. The first, as I said, is basically to make cross-matches between all the surveys I mentioned, just to see what objects are in some catalogs and not in other one. And the second step will be to make a color magnetudograms and color diagrams, because in this type of diagrams, massive stars are located in known parts. For example, in figure 3, we have a color magnitudogram of the Lurie sample, and the color the color points are the massive stars, but we divide this region in 2 parts. Like the upper one, what I call the certain region, because they are massive stars. But we have this central region that I call it the pentagon, because it's a region where you can find both massive stars and intermediate massive stars. And to remove these intermediate stars, to take only the massive ones, we are going to use the color diagrams by making a cross-match between the Tarski-Harris survey, the ultraviolet survey, and Gaia survey. And in figure 4, you can see the color diagram with extinction tracks for massive stars, and therefore we can check the massive stars in this region, which is the hardest to filter. The last step would be to check the literature to see that we don't miss any object and make a complete catalog. So at the moment we have around 35,000 massive stars in the LMC. This is a great number because, for example, in the third version of the AILS catalog collects around 16,000 massive stars. So they are like the double, and for example, the Magellanic Bridge we have around 200. And some preliminary results that I want to show to you. For example, in the figure 8 and 9, we have color magnetudograms. In the upper plot, we can see, for example, the B stars extracted by using near-infrared photometry. And in the bottom, we can see the color magnitudogram with the OB main sequence stars and with the blue loop. That we search it by using basically ultraviolet photometry. And this is all. The catalog will publish this spring, and I hope you are interested in using it. Thank you. If you have any questions, you can tell me.
Can you go back to the picture with the plot of the
This one, okay.
Sorry, one further.
Previous, this one.
The one that has the bridge, yeah.
Ah, okay. Yeah.
So the dark blue ones are the ones that are massive stars in the bridge that are.
Yes, this is like the raw data from Lurie, and by filtering the massive stars, we have the figure 6. So. Yes, all that points are massive stars.
Do you see like a slight sort of connection that goes down a bit?
Yeah,
Okay.
like one idea of the project is to define the magenic bridge, because in some articles they only study this region near to the SMC, and I want to reproduce all the bridges. Yeah.
Yeah, very cool. Thank you.
Thanks.
Okay, since we're almost 50 minutes behind schedule, let's thank Juan Antonio and go forward to Giuliano and try to stay in your time.
Okay, hello, I'm Giuliano Iorio from the University of Barcelona. And in this 5 minutes, I would like to highlight some interesting results about an intriguing subpopulation of RL-Lyra stars. Now, RL-Lyra stars are well-known classical variable stars. They are classically associated with all the matter population and have been used for decades to trace that population in the Milky Way. Now, thanks to Gaia, we have this very beautiful map showing all the 200,000 RL-Lyra in Gaia with this whole sky view. And they are all over the place. You see many of them are in the halo. But if you follow the colors, I show the metadicity of such object, you can see that there is a clear gradient of metadicity increasing toward the plane. It seems really like that there is a flattened distribution of RL-Lyra in the plane of our galaxy. Now, this population is a puzzling. It should not exist, or this star should be really, really old. And this is why this is shown by this plot, showing for a fixed, the different colors show a fixed amount of mass loss for the progenitor of the RL-Lyra due to winds, for example, and the trend shows the age as a function of metadicity. So in all the cases, we have these trends of metal-rich RL-Lyra that should be older. And if you look up to the gray band, that is a kind of limit value for the amount of mass that can be used on the red giant branch through winds, you can see that for the most metal-rich part, you don't even expect they to exist because they will be older than the Hubble time. If you look instead at their properties, like the kinematics, for example, you see we obtain something that is shown by these white diamonds and the red dots. That is, you see the opposite trend. It seems that the metal-rich RL-Lyra seems to be younger, and they want to highlight especially this red point because it's a very recent result by Cecilia Matteu of the detection of one RL-Lyra in an open cluster, this Trampler 5. So this is really young. And if you look to explain such trend, you need really a large amount of mass loss that is not really cannot really be reached with stellar winds. So what could be the solution? Well, in 2024, I with Alexei Bobrik, we proposed a model in which this mass loss is through binary mass transfer. So instead of a single star, we have two stars. The most massive one expand, start to fill the rush lobe, and you lose mass in a very effective way, much more effective than stellar winds. And among the outcomes, you can also have a partially stripped stars that can enter in the stability strip. We test this model with the meta simulation, and we obtain what is shown in this other plot. The blue points are RL-Lyra formed in this way, and they have the ages and metadicity that are consistent with what we see in the field. The problem, there is a strong prediction, is that they are today in binaries with period between 1,000 and 2,000 days, something that should be possible to detect as non-single source in Gaia. But we don't have any of no RL-Lyra detected as non-single sources in Gaia DR3, and in general, we have no RL-Lyra detected in binaries in general. This is a well-known feature or problem. And so the point is, if this is just indicating some tension with the models, or is just an observational bias because it's difficult to observe such system in binaries. I try to answer this question. Actually, I try to answer a more specific question that is like, given that we have zero detection in Gaia DR3, what is the maximum allowed, what is the allowed fraction of binaries that is consistent with zero detection? And I try to answer to this with a data-driven forward model combining a subset of RL-Lyra from Gaia, for which I'm quite confident that I can maximize the likelihood to find them in binaries. I have a theoretically motivated binary population model and a tool to simulate the Gaia observation that was made by, developed by Karim El-Badri. I updated it to include also the possible astrometric bias for stellar variability. And this matters a lot because you can see from in these results showing the posterior diffraction of binary given zero detection. If we don't consider variability, we have a clear tension with the models because at high metadensity we expect something close to 1, but this gray area showing the 3 sigma are much lower. When I include variability, it's more difficult to say something because these sources are intrinsically less detectable because of the variability. So, just to wrap up, the main message is that I think meta-rich LLI are a really intriguing population to test stellar and binary evolution models. We don't know how to form them, maybe in binary, but they should be detected in Gaia DR3. We don't see them. This can be because we have attention with model, but we are affected by, limited by this, the astrometric bias due to variability. Gaia DR4 can help, but it will be a bit limited, still a bit limited for this. And just I want to say that this tool that this Gaia mock with the update for variability is public available. So if you want to use it, you can just talk to me. Thank you.
If there are no questions, yeah, feel free to ask Giuliano during lunch or coffee, and we continue with Sayali.
Hello, I'm Sayali Kulkarni. I'm a PhD student at CEFCA. Today I'm going to talk about science case of RR Lyrae stars as pulsating tracers of Milky Way with Gaia DR3 and JVAR and J+ surveys. So, RR Lyrae are variable stars. They are used to study the structure and formation, mainly of the Milky Way halo. They are classified as RRABs, RRCs, and RRDs, depending on their mode of frequency or mode of variability. Here we have cross-matched RR Lyrae stars in JVAR DR1 and J+ DR3 with the Gaia DR3 variable star catalog separately. After cross-matching JVAR DR1 and Gaia DR3, what we get here is a Bailey diagram, which is amplitude versus the periods. The amplitudes and periods used here are basically, those are from Gaia DR3 variable star catalog. And the highlighted points that you see here are the JVAR RR Lyrae, exclusively. You can see 3 loci here, actually 2. Third is hidden. One is RRAB stars. The second locus is of RRC stars. And there are only 2 RRD stars, but they are, you can't see it. So this plot gives us an idea of the Gaia DR3 variable star catalogs, the data, and the JVAR's distribution, JVAR exclusively. All right, moving on. Okay. After getting this Bailey diagram, we created the light curves for about 315 RR Lyrae stars using Gaia periods and Gaia epochs. These are the light curves. And then we fitted the SDSS templates taken from the template library of from CSER for different band configurations. So you can see the data points here. They are making the light curve, which is magnitudes. So the colors that you see here are the 7 JVAR bands. On the y-axis you have magnitudes, JVAR magnitudes, and on the y-axis we have phases. So the light curves are nothing but phase folded data of the magnitudes. All right. Okay. So the fitted SDSS light curve, fitted SDSS templates gave us the best periods from the best fitted template. And those base periods are in good agreement with the Gaia periods. Those were inputted, to make these light curves, basically. Okay. Then we plotted all JVAR bands, their median normalized amplitudes of the 7 JVAR bands, as you can see here, the colors and the band associated with it. and it was expected to have or follow an exponential fit with the Gaia G band. Amplitude in the Gaia G band is, well, not lying or coinciding as exactly, but somewhere near, close by to it. So this result was as expected. Okay. So before moving on to the next slide, I want to mention that the JVAR DR1 plus Gaia DR3 is the cross-match catalog, and it is published. It is ready and it is available on Zenodo. I have put a link on the last slide. And a publication that describes this catalog is in the pipeline. Then, so this was the first project, and now this is the second project. I have cross-matched J plus DR3 and Gaia DR3 variable stat catalog. So what you see here are, they look like light curves, but they are not light curves. So the thing is, I want to mention that J plus is not, is a single epoch survey, and it cannot detect the variability on its own. So what you see here are mere arrangement of magnitudes according to their phases of the RR stars in different J plus bands. So there are 12 J plus bands, and you have 12 small figures. So each point that you see here is a separate, an individual RR star in different band. Okay. Then in order to find the trends of stellar variability with its physical parameters such as amplitudes in Gaia amplitude, metallicity, etc., we have included a color bar which for the amplitude amplitude in Gaia. So we can see two examples here: JVAR RSDSS band, which is common with the SDSS, and GSDSS band. We also have, I also have limited this sample for RRAB stars in both of the bands. So, and yes, clearly we can see the trends over here. I cannot comment much about it because we are still studying and exploring this data. In the next step, we will fit the Fouriers to this and other bands, I mean these figures and other results in other bands. And yes, we will see what we can get. In the future, we want to include Gaia epoch photometry data to create the light curves and to compare those light curves with the JVAR, these ones, and the JVAR and both JVAR and J plus light curves. And with the new data release, J plus DR4, we will get to study new data, new stars, or more stars. In far future, we expect Gaia NIR to help us to explore deeper into the Milky Way halo and the bulge. So JVAR DR1 catalog is available here. The publication is available here. The preprint archive is on the archive. And you also have the links for the CEFCAS and CEFCAS catalog portal. Thank you.
So I think we have to really rush because probably the minister won't wait for us if we're late coming from lunch, right? So I would, yes, please ask questions in the break, okay? So, okay, Adrián Hidalgo.
Hi, I am Adrián Hidalgo. I'm a PhD student with my supervisor, Andrés Del Pino. I am working at CEFCA. I'm going to present stellar parameters using G+, photometry, and Gaia parallax via PCA. Our sample is a cross-match between G+ DR4 with Gaia astrometry, where this is a sky map for our samples with more 5 million stars. This is its color magnitude diagrams with a deep up to 19 in air band, and we can distinguish between main sequence, Gillian branch, wide words, and we apply the principal component analysis to 66 colors plus distance modulus to obtain 9 principal components with more information, where with 9 principal components, we fit several polynomial to obtain several models for each stellar parameter. We use the training sample is a cross match between our sample with Lamos medium resolution DR10, and this is its color magnitude diagram, and we have a giant star and main sequence with a deep up to 50 inner bands, and we have 27,000 stars, and this is a representation for the first principal components with more information with each stellar parameter from Lamos, and we see as they have a high correlation with each stellar parameters, and this is a comparison between prediction and true value from Lamos for each stellar parameter, and we see as the most stars fall very close to line to ones, and we have good statistics in general. And here is the chemistry for our predictions with a sample similar to a training sample with a deep in bands up to 30, like training sample. And we see as the overall shape for both panels is preserved, as well as to this distribution for in theta galactocentrics. And finally, with our prediction, we can distinguish between halo, thick disk, and thin disk for the component from Milky Way. And we see the distributions in theta galactocentric, and we see that the solar metallicity is concentrated in the galactic plane and decrease with the theta, higher theta. The opposite range was observed with alpha elements, where solar alpha is found in the plane galactics, galactic plane, and the increase with the theta. So with this model, we can obtain a large samples of alpha-rich and metal-poor stars, which will facilitate the search for stellar strings by using clustering algorithms. And thank you very much.
Bueno, if there's, yeah, you know where to find them, no? Thanks, Adrian. And second to last talk of this session is by Javier Vanegas.
Thank you, everyone. I will try to be fast to go everyone to lunch. So I'm going to present you a work we're starting right now, leadership by Miriam Cortez Contreras, and with all the collaborators here. And this is a census of GKM and ultra-cool dwarfs. We started with a pilot study with a very low sample and of a BBX survey, and then cross-matched with Gaia DR3 to get the good astrometric parameters. And then we search for the effective temperatures available in Gaia DR3, and with those we don't have the temperatures, we computed using the BOSA of the Bio Observatory. So to show you the survey, we are using the VISTA variable in the Via Láctea Extended Survey, located in the VISTA telescope, and we are reproducing the work done by Patricia Cruz et al. In 2023. So this is another region, but the methodology is very similar. So this is the region that we are choosing. It's a very small region, but due to computational work, we started with a small sample. So we initially have around 360,000 VVX sources. We cross-matched using TopCat with Gaia NIR in 1 arcsecond. And then we get around 215 or so thousand sources. Then we applied some astrometric cuts, kinematic cuts. If you don't see the numbers, it's like astrometric cut leaves us with 70,000, and then kinematic cuts leave us with 3,000 or so. And then we calculate the reduced proper motion in the G band, and then apply a dwarf selection. And this has leave us with around 2,600, and then apply some color cuts. It's related in the Patricia Cruz paper. And then we leave with only the ones that are 500 parsecs or low to avoid excision problems. And then this is the plot of all the cuts represented in a color magnitude diagram. And then we are looking for temperature because we want to look up for the cool stars. So this is the temperature available in the Gaia NIR of around 30% of the final sample only has temperature available in Gaia. So we make use of BOSA. BOSA is a tool of the BOSA is a tool of the Spanish Virtual Observatory. We compute set fitting of the available photometry in VFAS Gaia NIR at glimpse. And then you use this model, taking into account that the metallicity is 0, because we are working with this preliminary study. So this is the difference between the temperatures. So we have like 700 new ones of the stars that BOSA produces with temperatures. The number is reduced from the initial number, that is 1,100, because we get only the fit is statistically correct. So we are gaining 700 temperatures for the stars, so we are making like 700 new catalog discoveries. So this is a plot of the relation between the temperatures calculated by BOSA and the temperatures available in Gaia. So to see the relation, this is a one-to-one line to see if this is related or not. So this is a preliminary study. We are just starting with the project. So the message to this presentation is we test a selection methodology combining VVX infrared photometry with the Gaia NIR towards the galaxy center. That is in the title. This is an assumption about the possibilities of the project. We take 3-degree pilot field, and we live with like 0.3% of the sample. And then if this is escalated to the whole VVX sample, assuming homogeneity in the survey, that this is not correct, we maybe get like 600,000 candidate sources. This is a roughly a number that this is only to show the numbers. And this is 65% will have new temperatures calculated that is not available in Gaia. This is calculated with direct extrapolation, so these numbers are now the current ones, surely. And then we are focused on developing more effective methods, because BOSA takes into account only a little amount of data. So we are making new analysis of new techniques and complementary studies that will improve this method. So thank you all.
Just stick to one. Yeah. What about interstellar extinction? How do you deal with it? What kind of map you use?
Yeah, right now the extinction is what BOSA takes into account with the model. So right now we are taking like the simplest model available. So the extinction is a real problem. So we are taking into account in the future. So right now it's like the simplest model possible to see if this is a good approach to a survey. So yes, I will talk to you in the future about this and we discuss.
You can come. Ah, yes. Okay. Where is the browser again? Okay, this was Jordi's. I think it's gone. Joder. Aquí. Aquí. No.
No, se fue.
Es que se fue mucho se fue. A ver, aquí.
Oh.
Vamos.
Easy. Okay. Easy peasy. Presentación. All right. Thanks for having me here. Particularly glad special thanks to the organizers for putting me after PhD students. That makes me feel younger. And I'm the last speaker before lunch, so I'll try to be brief. So what is a cataclysmic variable that I want to study using Gaia spectra and light curves? So we are speaking about binaries. I think I'm the first speaker speaking about two stars together. One is a white dwarf, the other one is a Roche-Loeb filling main sequence star. The material is lost through L1 overflow. It builds an accretion disk around the white dwarf if there's no magnetic field on the white dwarf, because if there's magnetic field, the accretion disk is destroyed partly or completely. So these stars can be blue, can be red, they can have an accretion disk, they may not have an accretion disk, they may have a H-alpha emission, they may not have H-alpha emission. It's fun to be working in this field because it's a mess. And because they have this very funny zoology, they're complicated to discover, and they are rare. They may not be as rare as symbiotic stars, where's Yaroslav, and they may not be as rare as X-ray binaries, but they are rare. So in 1.8 billion objects in Gaia, there's 4,000 objects there's 4,000 CDs. So this is how rare these things are. So normally, when you try to run some machine learning algorithm, you go like, I want a balanced sample. And you go like, no, not going to happen. And then there is another issue, which at some point I will have to speak about with my therapist, and there is these different types of imbalance. One is the different types of objects, right? So, as I said, we have 4,000 objects out of 1.8 billion, but then there's different features, and I'm going to show in a sec. If you may end up being dominated by the spectroscopic information that you have as opposed to the light curve information that you had in the data. So the bright thing is that there are some specific regions that try to show in the corner plot on the right here, where CVs are actually concentrated. I'm not saying that you can actually make a clear, clean cut and say, you know, in this region there are CVs and there's nothing else. So, as I was commenting with the White Wolf people last week in La Laguna, machine learning is not necessary, it's unavoidable. And so this is what I started trying to do for the past couple of years. And the first thing was, you know, you have the BPRP information in Gaia, you have the G information in Gaia, you have parallaxes. You go like, let's try to put this and let's ask for a, I think this was a random forest. And let's see what candidates fall as White Wolf CV candidate. And actually they fell exactly where they were supposed to fall, with, you know, decent probability. And you would go like, ah, so you wrote a paper about it? No, because I was like, can't be, this is too easy, right? If I did it and it worked at the first try, cannot be right. So took 1/10 of sky, no, actually 1/36 of sky, and got all the spectra, and for Michel's joy, I actually converted them to spectra. So this is low resolution spectrum, 300 points between UV and infrared, and in red is the stars, and in blue is, no, sorry, the other way around. In gray is the stars, and in red is cataclysmic variables, and you can see that most CVs are, as opposed to the normal stars, they are bluer and there's some H alpha. So you would say, you know, you can put this column with 300 points, and then you take some the variability statistics available from Gaia. Again, you do some machine learning. Since it's only a part of sky, I only show 2 points. Again, they fall exactly in the same point. So you wrote a paper about it? No. So now yes, Michel will be happy. I'm only using the coefficients, not the first one. We'll speak about it. And again, they fall in the right place. And they fall in the right place. Are you writing a paper about it? I think at this point I may have to. Everything converges that I'm actually doing it sort of right. And anyway, basically I'm here to speak to Michel, because otherwise, because basically he's the person to speak with. So thanks very much.
Cierra.
Vale, thank you very much, Alessandro. So let's close this session, and before we start leaving, 2 announcements. One, the reconvene time. So we should start at 3. So I know we are in delay, but Isabel Perez will be the first one, and she is in the steering committee of the MLA, and she only has this 15 minutes from 3 to 3:15, so apologies. But we cannot delay the start of this afternoon session, so we restart at 3. For lunch, there is a street behind the agency called Calle La Traviesa, where there are different options. Don't choose the first one. We do not all fit at the first one or the closest one. There are different bars along the street. Let's have a quick tapa and reconvene at 3. Okay, so tomorrow we will have more time, but today is like this. Okay, see you later. You can leave the stuff here. So as you see, there is a strict control of access to the building. You can leave the stuff here and, okay. Let's start. So let's now start the workshop on Gaia NIR and the engagement of the Spanish community. And we start with welcoming Isabel Pérez Grande, and she will give us a short summary of the ministerial meeting that happened in November, and with the focus on Gaia NIR, on the Gaia NIR mission. So thank you very much.
Thank you, Marcel. First of all, good afternoon, everyone. Good afternoon again. This morning I have already seen some of you. It's a pleasure for us to have you here in the Spanish Space Agency. I am currently the Director of Science, Technology and Innovation, and I am in charge of, let's say, taking care of the science community. And I also have to try to give you the best guidelines to achieve your, in this case, your goals. I have a very, very short presentation. Merce asked me to give you some notes about the ministerial in terms of science, of what happened there. And I'm going to show you a few slides, some of ESA, and I'm going to move to the, yeah, to the contents of my presentation. I will talk a bit about the ministerial. I think most of you will know about that and about the outcome. And just a slide about funding, because I'm completely sure this is one of your main concerns. If I am interested on participating in Gaia NIR, how can I get the funds we need to do that? So, starting with the ministerial, I think you will have seen this slide in different areas. You know that the contribution, the global contribution to ESA in last ministerial in November is about 22,000 million euros, so it's an amazing amount there. And the science program has about 17%. There is, they're down in the, I would say here in the laptop pink, there it's like orange or coral or something like that. It's more than 3,787 million. So it's a very significant amount. I think the ESA is, science is the backbone of ESA. In fact, it's together with a bit of technologies, the only mandatory program at ESA. So I think you will be familiar with this, but for those new in the field, a mandatory program means that all the ministers, all the countries agree on the global amount, and then the contribution of each country is proportional to their GPD. So the weight, you may be willing to put a lot of funding in science, but it depends not only on you, but also on the global amount. So what some countries have done has been to use other, that wanted to contribute more in science, has been to put fundings in other programs, in other optional programs like products. I will talk a bit later about that. But in the science program, that is the program where all the missions are, the science missions are chosen and the main decisions are there. The decisions are global decisions because it's a mandatory program. How much this amount I have talked about, how is it distributed and what does ESA think they can do with that? So the term they use to measure the contribution to the mandatory program is what they call the level of resources. And in this case, the level of resources, the proposal of ESA is to increase the previous contributions by first the inflation. So you first compensate the inflation that during the last period has been very high, so it's a problem. And on top of inflation, the proposal of ESA and what the ministers have approved is to increase 3.5% during the first 3 years and then flat for the next 2. It's not so straightforward, but in the mandatory programs in science, even though you commit during the next 3 years in science, in the mandatory program, you give numbers of the next 5-year period. So what they have put is 3.5 on top inflation, but from those 3 years, then it's flat. Okay, and then the exercise that ISA has done is, with that amount that the ministers have given me, what can I do in terms of our planning, or what? And this is the waterfall diagram. Maybe it's the PDF. There is not, but you can see it quite well. And there you have more or less you can see the temporal distribution of the developing of the missions. You see there well beyond the commitments of the ministerial. So we are talking that we reach 2028, 2030, if we consider the 5-year period, and here you can see up to 2045. So from this first part towards the end, new ministerial council will have to make decisions. So, but of course they need to have a planification to know what we want to do. It's the long-term planning, what they call. And since we are talking about Gaia NIR, where is Gaia NIR here, or where could Gaia NIR be here? It would be the L5, because it's a large mission, and you know that L4 is already selected or chosen, what all countries want to do. So we are talking to start the development of the mission at the, say, mid-next decade, more or less. It doesn't mean that ISA is not going to start it earlier. I will show you a slide later. But I mean, I'm talking about the developing phase of the mission. So that is different. There are many questions. We can talk during hours about this slide, what's the meaning of everything. But I think if you have any question, maybe later we can talk about that. Okay, so this is what they want to put there in the program, this amount of funding, and what does ISA want to do with this? So they consider to run in parallel two corridors. One is dedicated to complete the Cosmic Vision program. That was the program we were running up to now, or the planning, more or less. And then to start the new Voyage 2050, that is what, in this case, Gaia NIR is situated. I'm not going to spend time on this. You know, Cosmic Vision, we have to launch SMILE, Plato, Ariel. We have some missions already finished, like SMILE and Plato almost, and we have missions in development, and so. And the Corridor 2, there is this new Voyage 2050. In this case, they include there the M7, that you know that there are 3 missions now in competition. And also a new call, the M8, a new call last year, where they have included a new type of mission, the mini-Fs. It was an exploratory call to see if you, the science community, can propose ideas to do real interesting science with small missions with little money. That's it's a position to the L missions. Sometimes the problem is that the cadence of L missions, you have a lot of gaps between mission, and you need to feed the activities with smaller missions. Now I think I want you to have a look at this, because maybe the other slide was a bit discouraging when you have seen that the L5 starts to appear in the waterfall diagram at the end of next decade, and it can be a bit depressing. But you can see that L5 is already earlier there. It's the second line in this diagram. And I can see, okay, yes. So the decisions, the activity will start right by next ministerial in 3 years. So that's the important point. And they have there, okay, the developing phase will start by the end of the next decade. That is, in fact, it's just in 2039, but you see a lot of years before where you have to prepare this mission. So we are very far from that point yet, but what ESA considers now of an L mission, I've written here the numbers, is about 1,500 million euros for an L missions in economic conditions of now. So that means if you start to consider inflation, you have to increase that number and about 10 years of development time. Okay. I'm not going to spend time on the cosmic vision, and even if this slide is also old because Ariel has already been delayed, so, but this is more or less what we have on the table. And talking a bit more about the Voyage 2050, I have said before, the selection of N7, other type of smaller missions like the mini-Fs, and also these preparatory studies for the future L missions. So that's why we are going to start in 3 years' time at ESA, but we will, in this case, start, or ESA will start the development of the mission in 10 years, in more than 10 years' time. Okay. Okay, this is also a nice slide where you can see there the L5. Right now it's still gray, but it's there, so it's already there. And you have there Gaia NIR as a candidate. And the funding. It's just one slide for funding. So talking to the Spanish community, that is in this case what we have in our hands. The science community is funded through the national goals of the, up to now, the Spanish State Research Agency. From next year on, that goal will be managed from here, from the Spanish Space Agency. But for those contributions requiring industrial contracts, in that case, we will use the products tool, that is, in this case, an optional program of ESA, where in this case we have subscribed about 60 million for the next period. So we are, there is a bet for science in this case. And in the case of Gaia NIR, I think it's also interesting in this case for you to look at other options of funding. So mainly technology development. I mean, if you need new technology for those missions, that is what's happening now with the L4, maybe you can use other types of calls, like the GSTP, that are calls just to develop technology. So focused on that without necessarily a mission behind, but you need to develop this type of technology, you can go to those calls. But mainly, if you need an industrial contract for a system, in that case, you will have to use products. And I think this is all from my side. I don't know if you have any question about this, or I can offer you more information. I think this is a summary of the contribution, in this case of the subscription to the in this case for the next period in the ministerial. I think I want to stress, to point out that the science, in this case, I think most countries agreed on that they had to support it. So discussions were if we increase 3.5 above inflation or 4. But I think there was it was unanimous, the fact that all countries had to support science. So, and I don't know if you have any question. I think this is my last slide. I am right now attending upstairs in my office the Gaia Steering Committee, so I am in this case engaged with you. So. Any question or, okay. Perfect, that's good. So I hope that maybe you knew all these slides, but I think it was interesting to show you because yesterday when I was preparing the presentation, I realized that in the previous years there were more material, public material for the community. Now I think I haven't found too many slides related to science, just the global numbers, but I think it was interesting to show you this, and okay, it's a pleasure. Thank you.
Okay, let's see. Lola, do we have Frederic online? No. Okay. We were supposed to have Frederic Safa online, but he's not online yet. Let's do the following. Josh, can you start? And we give Frederic some more time to connect. So
yes,
I should
fine.
stop sharing. And hi, Josh. Can you
Hi.
try to speak?
Can you hear me? I'm speaking.
Okay, yeah, good. And now
Yeah.
you can share the screen.
All right.
Volume, please, can you put the volume a bit louder?
I will try. Hold on for a second.
Yeah, okay, it's better, it's better.
Okay.
So, okay, and we see the full screen. Okay, so Josh, you have your time, okay?
All right. Do you see my slides as well?
Yes. Not full screen.
All right, excellent.
No. Can you put full screen? Control L.
Yes.
Or Command L.
Command L. Better?
No. It depends on what you're sharing. If you're sharing the screen or the window.
The window.
Okay, maybe if you share the screen, you can do the full screen.
Okay. Yeah.
Okay. Yeah, good, perfect. Go ahead.
All right. So thank you for inviting me. I will spend maybe 10 minutes to tell you a little bit about lessons learned from Gaia, in particular for Gaia NIR. So to remind you, Gaia has been launched to reveal the origin and evolution of the Milky Way. The stellar positions and distances give information on galactic structure. The motions give information on galactic kinematics and dynamics, and the stellar parameters and composition and ages of objects give hints on galactic evolution. So this meets the science case of the mission. And Gaia has been implementing this mission using an optical all-sky survey comprising astrometry, photometry, and spectroscopy. And in its survey, it has taken roughly 1% of the stellar content in the galaxy, some 2 billion stars. So at the moment, the Gaia collaboration is in full swing for preparations of data release 4. And this data release will contain science-ready, calibrated, and validated data products, which will be extensively documented. As mentioned, this is the 4th intermediate release in a series of releases that started in 2016 with data release 1. And that will culminate not before the end of 2030 with Gaia DR5, which will contain all 10.5 years of data, comprising about 1 petabyte of data. And that will also constitute Gaia's legacy with a lot of new science. But in the shorter time, up to December or in December of this year, there will be the release of Gaia DR4, which comprises 5.5 years of data. A little bit less than 500 terabytes in volume with a significant number of new data products. And in particular, there will be the time series for all sources and all instruments. And if you're interested in more details or previews or content, you can go to the Gaia Cosmos homepage. And obviously, Gaia DR4 will enable a lot of new science compared to the previous data releases. So this is a major step in the Gaia timeline. So jumping to the lessons learned, after the end of spacecraft operations last year, a lessons learned exercise has been done. This focused on operations of the spacecraft and what I would call the daily operations within the science ground segment. And this exercise was not specifically focused on Gaia NIR, but it was more general for any future mission in ESA. This process is nearing completion, and a document presenting all the lessons learned will be published in the first half of this year. And then there will be a second round of lessons learned, which is more focused on the DPAC and the archive, so more on the cyclic data processing, the data releases, the archive. And that is planned for next year after DR4 has taken place. So what I have collected for today are just 2 more slides, and they are mine. They are personally or personal. They do not constitute a formal ESA view. And what I've done is I've presented selected issues from the 2025 lessons learned exercise that is not formally concluded yet, but that will be concluded in the first half of this year. And I've also been inspired by a few entries or a few lessons from the 2025 doctoral network tech workshop in Cambridge that took place last year. So in my presentation today, I will focus mostly on Gaia NIR. So the lessons have been tailored to Gaia NIR. And the 2 slides that follow will be focused on things not to be repeated and on things that went well, generally speaking, and that are to be repeated. So the bad and the ugly, and then the good to finish. So on the not to be repeated things, there's only 3 bullets. You could think of more, but I've tried to limit myself to major points. The first bullet links to, let's say, instrument or spacecraft issues. And I've put there stray light, the basic angle variations that we faced, contamination of optics, and microclanks. Now, all of these topics, they are huge, and I could spend lectures in themselves on every topic. But I will suffice here to just say that these were important elements for Gaia data processing. Not all of them are easy to prevent for future missions, but nonetheless, we have some kind of generic lessons learned for each of those. And as examples, you can think of, in case of stray light, to have 2 independent analyses from independent entities, could be two independent industries doing the same on the same set of requirements. One could think of having dedicated sensors and metrology on board to carefully monitor, for instance, the temperature of certain parts of the focal plane or of the payload. And for stray light, for instance, to collect extensive photographic documentation and AIT records. So these are assembly, integration, and test records of the on-ground test phase of the spacecraft. To record, for instance, how MLI has been fixed or how MLI has been wrapped around certain critical parts of the payload, to see if there could be potential light leaks that could lead to stray light. So more of this will be in the lessons learned documents that will be published later this year. Then the second bullet is quite generic, but I've summarized this in one sentence as what we should try to avoid for future missions is to do some kind of what I would call over-engineering of the ground segments and pipelines in the ground segments due to overly ambitions, and then I put perceived between brackets, needs. And then in particular, one area where I think for Gaia we went too far is, for instance, we thought or we were hoping to be really good in doing near real-time processing of data to feed the alerts pipeline. But in the end, there were a number of real-time issues with the telemetry coming down that really prevented us from doing this. And actually, in the initial data treatment, this gave, over a couple of years in the beginning of the mission, it gave a lot of problems to get the initial data treatment up to spec. with reality. So that's something I think where we have to put a strong lesson learned to well, not over-engineer and to not be overly ambitious compared to what is reality. And then the last lesson learned is not to be repeated, is to rely too much on mission-specific formats. And as an example, you could use GBIN, where obviously it is a very effective format, but it's Gaia DPAC consortium internal, and it has not really started to live its own life outside the DPAC. And with hindsight, it might have been better to adapt, let's say, a more uniformly and open data source format. And obviously, if you talk today, could be Parquet or even FITS or HDF5. And similarly, obviously, it's kind of a generic statement. One should not be selecting vendor-specific technologies. Could be for databases, could be for data formats, could be for software solutions. And I won't go into more details for that, but these are kind of the logical, not to be repeated lessons learned from Gaia for Gaia NIR. Then moving to my last slide, this is a fairly long list of things that went well, I would say, for Gaia, and that have immediate consequences or lessons learned for Gaia NIR. The first point is, I think it has been very important to not only collect astrometry, but to combine the astrometry with photometry. Could be either narrowband filter or could be prism like we had for Gaia, but also to have spectroscopy built into the mission concept. I would say a small lesson learned there is to optimize the spectroscopy not only for radial velocities, but also for abundances, but that's kind of a sideline. I think what has worked very well for Gaia is to have an all-sky survey from L2, so not a low Earth orbit or not some kind of Earth orbiting satellite, and to implement uniform revolving sky scanning, which is demonstrated to be the optimum way to scan the sky. Obviously, something we ignored or forgot for Gaia is to have this reverse precession phase of the scanning law in the baseline, but that's something we have learned, we have rectified for Gaia. And obviously, for future missions that do similar sky scanning, this should be baselined from the start as part of the nominal mission. Which worked very well and which will be a necessity for Gaia NIR would be to have orbit reconstruction, which is fed by both ground-based optical data. So something like a ground-based optical tracking will be needed for Gaia NIR as well. And also to baseline the delta differential one-way ranging from the Mission Operations Center as a default. This is something that came late for Gaia, but it should be baselined for Gaia NIR from the start. What has worked well is to have payload expertise at the Mission Operations Center, and that really expedited and really made the payload operations and normally investigations very efficient for Gaia. So that's something that should definitely be repeated for Gaia NIR. To have knowledge not only at the Science Operations Center, but also at the Mission Operations Center. Obviously, what has saved the day for Gaia was to have the basic angle monitoring device on board, and this should really be extended to Gaia NIR. And actually, a lesson learned from Gaia there will be that rather than have only 1 or 2 monitors in the corner of the focal plane, this basic angle monitoring device should be covering the full focal plane. And actually, it would be very useful to also augment this with high resolution thermistor data to follow the temperature evolution of the focal plane. In terms of timing of science data, I think Gaia NIR will have to rely on an atomic clock as well. And it would be very advantageous to have two-way clock synchronization implemented for Gaia NIR. Something that I mentioned on the previous slide already, for Gaia, we did realistic pre-launch end-to-end rehearsals of the MOC or the spacecraft to MOC and the MOC to SOC data flow. But what was not really apparent in that data flow was the anticipation of delays or gaps or out-of-order telemetry. And I think for Gaia NIR, that's something we should focus on right from the start, such that we can make the initial data treatment more robust against these real-time effects, which would then also benefit the science alerts pipeline. What has worked extremely well for Gaia is that we had a flexible design of the space segment, the ground segment, and the mission operations concept, so that in reality, we could immediately start benefiting from extra performance and improved science returns return once this materialized in orbit. And I think the biggest example there is that very quickly we were able to basically change the science performance or requirement from observing 1 billion stars to 2 billion stars. Because actually we were able to lower the faint end threshold. We were able to acquire the additional ground station hours without extra cost. And then basically we have been able, without many complications and without much added cost, to go from 1 to 2 billion stars. So this was all due to the flexible design of the 3 elements that I mentioned there. What has worked very well for Gaia, and which is not easy to put on paper in a requirement, is that there was a very collaborative and constructive link between the DPAC consortium, ESA, and the prime contractor in industry, Airbus. And it really worked extremely well to have this team of teams. Now, this is something more in the sociology of how people work and how projects evolve. And this is something not you can demand from people, but it's kind of the team building and the collaboration has been exemplary in terms of Gaia. And I hope that experience through the DPAC and the proto Gaia NIR consortium that will be erected in the future, I hope that team spirit can trickle through to Gaia NIR. What has been instrumental, I think most people would agree, for Gaia is to have the DPAC project office. A small team, but properly staffed team, fully integrated in DPAC and widely respected within DPAC. These people have been instrumental in safeguarding the interfaces in DPAC, in safeguarding the schedule, and in really making the glue between the different units in the DPAC consortium. That again is not easy to ask of people, because it depends depends on respecting people and on mutually agreeing and listening to others. So, but again, I hope that the good spirit that we had in Gaia will trickle through to Gaia NIR. And then what has been instrumental to make the DPAC work extremely smoothly is the adoption right from the start of a lot of DPAC common tools and workflows and work practices. And I mentioned a few of them. It was the adoption of Java as a common language. Obviously, Java should not be used for the Gaia NIR. It should be some other language. But the fact that we agreed early on to use a common language was instrumental. The use of Gaia tools, the Gaia parameter database, the main dictionary tool, or the main database and the dictionary tool, the LaTeX templates, the use of the Jira or LiveLink or Nexus or Jenkins, all of these were instrumental to make an extremely efficient DPAC consortium. So this concludes what I prepared, and if there's any questions, I'm here to answer them, or at least to listen and maybe provide an answer. Thank you.
Any question for Josh? David Hobbs is asking.
Hi, yes. One of the things you wanted to avoid in the future are the clanks, but I think that will be very difficult to do. It's a very minor point, of course, but we just have to be aware and able to model them very well. So, but I think we are now.
Yeah, David, hi. Yes, very much true. The clanks are a real life nuisance for Gaia, and they will probably stay so for Gaia NIR. I've seen some kind of idea to have stress sensors on board, but whether this is realistic or not, I don't know.
Another question? Okay, so let's thank Josh again. David, do you want to continue? And we just sent a reminder email to Frederick Zappa if he can join, otherwise we can allocate him when he's available. Thank you.
My slides?
Lola, you know what are the slides?
If you need the list of hobbits again.
Okay. But we have to share the screen first, right? Okay, thank you.
Okay, thank you all for this invitation to come here and talk to you directly about the Gaia NIR mission. In my talk, I was going to, because this audience is a kind of a mixture of scientists who know a lot about Gaia NIR and then also maybe industry people who maybe know less about Gaia NIR, I'm going to give a very quick review of why we want to do Gaia-like astrometry. And by doing that, I'm going to review a little bit of what Gaia has done. I'm then going to talk about the science cases for Gaia NIR, and then at the end, I'm going to go into more technical details about the kind of accuracy that we can achieve for the various instruments. So the Gaia mission, I started working on Gaia about 20 years ago, almost 20 years ago, and one of the first slides that I saw when I joined, and why is this not changing? There's a delay in the slide switching. But one of the first slides that I saw almost 20 years ago was this one here. The idea of this science slide was that basically it wanted to get across the message that Gaia was providing a very, very wide range of astronomical scientific return in various different areas like stellar physics, stellar systems, exoplanets, the solar system science, and in reference frames, but also with quasars, galaxies, and generally studying galactic structure, and even giving fundamental physics measurements like testing general relativity and so on. Now, all of these science objectives are very admirable, and today, if you look at what Gaia is actually doing, you will see that Gaia is getting more citations than any other space mission in Europe, even including missions from NASA, like the Hubble Space Telescope and so on, is outperforming all of them in terms of citations, at least, if you can use that to monitor scientific return. And the reason it does it is because the science cases are so extremely broad. And that is why Gaia is so successful. Now, Gaia NIR has to do similar things. It has to aim for very broad science return and a service to the entire astronomical community, but it has to do it on a much grander scale. To be an L-class mission, we have to totally outperform Gaia by an order of magnitude in many different areas. So this is quite a challenge to do because Gaia is already so successful. So trying to do better than Gaia is very difficult. Here's the overall design of the spacecraft. And you can see that Gaia has two main mirrors. These are the two primary mirrors which define two different viewing directions of the spacecraft. You're going to see that Gaia NIR looks very similar. On the bottom right here we have the outside view of the spacecraft, and you can see two slits in the spacecraft letting the light into these primary mirrors in here. Now, the Gaia focal plane is also very large. It had 106 CCD, large format CCD detectors. And you can see here in the bottom right are the basic angle monitors that Jos mentioned earlier. And this is clearly a problem just because they're in the wrong position. So they tell you what's going on at this position on the focal plane, but don't tell you what's going on in the rest of the focal plane. And that's made the calibration of the instrument much more difficult. You can also see the sky mappers, which detect the stars from the two different fields of view, the two different telescopes. We don't believe we necessarily need them on Gaia NIR, so there's something we have to design out and find other ways to do. The problem is that each one of these detectors is extremely expensive, so the more of them we have, the more expensive our mission becomes. So we have to be very brutal, basically, in trying to get rid of as many detectors as we can, but we also have to keep the monitoring. And the main instruments is this big grey astrometric field here, and then we have the photometry and low-resolution spectroscopy, and then we have the high-resolution spectrograph over here on the right-hand side. And the stars move in from the left and move across the focal plane, so the stars are always moving, so it means we have to integrate using detectors that can integrate the light as the stars move across the focal plane. A very important principle of Gaia is shown in this diagram. On the left here you see the old-fashioned way of doing astrometry. Basically, as the observer goes around the sun, then a nearby star will appear to move relative to the distant background stars. And that worked very well on the ground for hundreds of years. But it's not really very useful today when we want to go to extreme precision. And of course, the reason is that the distant background stars are also getting a parallax effect. they also have an apparent motion because of the parallax effect. Now Gaia, the principle is very different, and it's shown here. A parallax measurement is basically a shift of a star along a great circle towards the sun, and you can see that here. You see this little vector here for star 1. You see that that's a shift of the apparent position of the star along the sky, and what we actually measure in Gaia is the projection of that vector onto the spin great circle that we're measuring, which is this circle down here. So it's the projection of this vector onto this great circle below. And you can see for star 1, the projection of that vector would clearly have a measurement. You would get a measurement for star 1. But if we take a very special case, and this special case will occur from time to time, is that a second star on the other field of view, basically it will have a projection also because it has a parallax, but its projection just turns out by chance to be 0. And this means that the measurement of star 1 is then independent of the measurement of star 2. Now this is a special observation, but it occurs quite often on the focal plane for all of the stars. And these observations get added to the normal equations when we're doing the global solution, and they act on as constraints on the entire global solution, which means that we basically get absolute parallaxes for all the stars, basically. Our solution is consistent with absolute parallaxes for all of the stars. And that's an important principle, and that's why we use this kind of astrometry today instead of using the old-fashioned way of doing things relative to background stars. And it's a very powerful technique that allows us to construct a global sphere solution for the entire sky. And it's very useful. Now, in order to scan the sky, we have a scanning law, and I just want to do this very quickly, but basically as the spacecraft rotates, the precession axis of the spin axis also moves, and this is showing the movement here in this little red line over 4 days. And that causes then the great circles that are traced out by the telescopes to shift along, and eventually then we can cover the entire sky. And here, oops, oh yeah, I forgot, sorry, this little video won't work now, but by continuing this over 5 years, then we can map out the entire sky relatively uniformly. And the people who know Gaia know this video very well, but you can look it up online if you want to look at the Gaia scanning law. We intend to use basically the same scanning law as Gaia for Gaia NIR. There will be minor tweaks, but I would call them minor, and then the reverse precession could be designed in, as Jos also recommended earlier, into the scanning law. Now, data release 1, you can see traces of the scanning law. This was back in 2016. You can see these small lines. They're just about visible on the projector screen. They're individual scans, and when we only had a small amount of data, you could still see the effects of these scans with small gaps between them. But then as we added more data in data release 2, you can see the scanning law is no longer visible. When we make a density map, this is a density map of 1.7 billion stars, and also included in data release 2, we have color information of the stars. And then data release 3, we release 1.8 billion stars, and you can see, you probably can't see much of an improvement in this, but astrometrically, we have the data for all of the stars here. We have the positions, the parallaxes, the proper motions, and therefore we can actually move the stars as a function of time, so we know how the stars are moving on the sky. And when we have radial velocities, actually we get the full 6-dimensional phase space of the stellar motion, which is extremely important for galactic dynamics studies. That's a little video that won't play either. So now I'm just going to finish up with Gaia, but after data release 3, Michael Perryman produced this amazing science tree of Gaia, and this is why we have so many citations. In every area you can imagine in astronomy, we have results that are relevant to people, and this is why people are quoting Gaia science papers all the time, because the impact or the scientific return from Gaia is so huge. And this is the challenge that we have against us for Gaia NIR, that we have to do the same again, but do it an order of magnitude at least better in many, many different areas. So it's not a small task we're taking on, and that's why we have to have a large mission. Now I'll move on to Gaia NIR now and talk a bit more about the science cases for Gaia NIR. Now the science cases for Gaia NIR were presented in the Voyage 2050 proposal, which was written around 2019, if I remember correctly. In that we made 3 proposals. And you have to remember at this time we were still thinking that Gaia NIR might be a medium class mission, not a large class mission. So we cut down as many things as we could out of the proposal actually in order to fit inside the budget of a medium class mission. But the main science objective was to add near-infrared astrometry and photometry to probe the hidden regions of the galaxy, because clearly Gaia does very well, but it cannot see through the dust in the center of the galaxy and in the disk of the galaxy. And that's where the biggest science gain can be made. And we made some estimates around this time as well that we would see roughly 6 times as many stars as we're seeing with Gaia if we went to the K-band. If you imagine that Gaia NIR at the end of its life might produce up to 2.5 billion sources by DR5, then that would give us something like up to 15 billion sources, just if we go to the same magnitude. But our plan is to go to deeper magnitudes than Gaia. And if you go just 2 magnitudes deeper, if you multiply these 15 billion sources, then you're getting up towards 90 billion sources. But of course, crowding will reduce the numbers. So we think we would get 50 to 75 billion sources in total. Now, this is about 25 to 30 times more data than Gaia. And this is really problematic because how do we download that amount of data? This is going to be a real challenge, but this is something that we have to do. And if we could do this, then we would be getting something like 25% of the galaxy overall. So this would no longer be a survey of a sample of stars. It would actually be a physical map of the galaxy that really details a large part of at least the near part of the galaxy. So another major science goal of Gaia NIR is to combine the Gaia NIR measurements with the earlier catalogues from Gaia. So this would be with DR5, which we will not get until about 2030. And if we do that, then we would have a 20-year gap between the 2 missions, and then we would be able to get extremely accurate proper motions. And I'll give some numbers for those in a few minutes. And another point is that the Gaia reference frame and the Gaia catalogue itself will decay over time, and I will also show this in a bit more detail in a few minutes. By redoing more measurements, then we can stabilize the reference frame, or if you like, reset the reference frame, but also improve its accuracy by combining the different measurements. But also expanding the optical reference frame into the infrared is very important, because most new telescopes have infrared cameras on board now, and they want infrared reference frames also to do that. Now, on Gaia we had low resolution dispersion spectra for many of the stars. We also want to get those low resolution dispersion spectra for Gaia NIR because they're scientifically very important, and Gaia has proven that a lot of very, very good science can come out of the low resolution spectra that we have on board. But also for Gaia NIR, and something that we didn't have for Voyage 2050 was that we want to propose now that we include a radial velocity spectrometer in this. Because we're now a large mission, we basically need to try to get radial velocities, and our aim has to be to radically improve on Gaia's radial velocities. So it means we need to go deeper again, probably 2 magnitudes deeper than Gaia, and try to aim towards getting about 1 billion radial velocities, because Gaia will probably produce something of the order of 100 million. So we need to go an order of magnitude, or at least have the ambition to go an order of magnitude more in terms of radial velocities with similar precision. Now here I've listed many of the science cases for near-infrared astrometry. I'm going to go rather quickly through this because there's simply a large list of this. But you can imagine that once we have near-infrared astrometry, we can go deep into the bulge and bar regions, which are really the dynamically important regions of the galaxy. We can also probe the tin and thick disks and the spiral arms, and in particular we can try to understand dark matter in these regions of the galaxy. We can map the spiral arms, getting astrometry for billions of objects. We can vastly improve the rotation curve measurements, and we can also look at exoplanets in dusty and star-forming regions. and study the internal and bulk dynamics of clusters, which are often obscured by dust as well. And these are things that Gaia can't get at that well. And there's many other science cases, from brown dwarfs, M dwarfs, and so on, and cool white dwarfs, and free-floating planets, and by the time I get to the end of this list, I'm usually exhausted already, because there's so many science cases that we can go after. But that's the whole point of the mission and what I want to get across, not any particular one science case. There's a look at the galactic center, and you can see the problem we're really up against is crowding, obviously. Crowding is our enemy in the galactic center. And once we start doing the calculations for the number densities here, we realize that we have some challenges ahead of us in terms of how to do this. Now, joint solutions between Gaia and Gaia NIR are very important to get these catalogues of up to 2.5 billion stars. These improved proper motions are very important because there's many science cases that Gaia is now touching upon, particularly things like streams and dwarf galaxies, and their halos that are just about measurable with Gaia, but the accuracy is not very great because they're very far away and they're very faint objects. If we could get better proper motions, we could do a much better job with these. And this would allow us then to do another exhaustive list of very good science cases with these 2.5 billion stars. One of the things I want to highlight out of this long list are exoplanet and binary periods. If we have a joint solution, we have a baseline of about 40 years. And that allows us to detect very long period solar system analogues, basically, and that would be extremely useful. So Gaia has a mission duration of 10 years, and the exoplanet detection rate is optimal, therefore, at around the same period of about 10 years. But if we could push that out to 40 years, we could really look at solar system analogues, and I think that's a very strong science cases. But there's many others, of course. The solar system, for example, is perturbed very easily, so even though Gaia has measured large numbers of stars in the solar system, getting new measurements of those later on will let us see what's really going on in the solar system and maintain the accuracy for a very long time. And I'll let people read through the rest of the list just to save some time here. But what I wanted to do is just show you how we can combine these. This is the time scenario. So here Gaia launched around late 2013, but it started operations in 2014 and continued until 2025. We now are about here, and then we have a large gap between Gaia and Gaia NIR of about 20 years, depending on exactly when it launches. We're currently thinking around 2045. If Gaia NIR was to launch at 2045, it would be good. If it launched a little later, it would be also even better, actually. But we don't want to have it too late because all of the astronomers who have experience in Gaia will have all retired by then. And so somewhere halfway along this line, this gap period here, we have to be training in new astronomers, new young astronomers, and we already have some of them in the audience even already in the Milky Way Gaia network. Doctoral network, for example, we're already starting to train in young people to take over and continue this work because we have to retire in some period up here before the launch. What we're planning to do is to do this joint solution. How we do the joint solution traditionally is we use this first equation up here. I should try to show this. This is the quadratic sum of the positional uncertainties of the two missions divided by the difference in time, which is basically 30 years. It's the period between 2020 and 2050, the mid-mission epochs. And that gives us a combined proper motion error estimate based on the joint solution as well. However, on top of this, we also have the individual independent solutions from the two independent missions, the new mission and the old Gaia mission, which calling the old mission Gaia is a bit strange already, given that it's still ongoing. But if we do this, then we can get proper motion estimates that bring us into the nano-arcsecond regime. So we would get values of around 5 to 6 micro-arcseconds per year for the proper motion component. And that's really impressive because getting down below the 1 micro-arcsecond regime is a real aim of this mission. Now this would be 21 times better than DR4 in terms of proper motion, and it's about 8 times better than the estimated DR5 in terms of proper motion. But another nice spin-off of all of this is that we could do things very early on. So if we look at this timeline now, and we do an early solution, just as we did with Gaia, combining Gaia with the Hipparcos data. After just 6 months after operation start, we could do the first joint solution. And if we do that first joint solution in 2045.5, then we will get proper motion accuracies of about 2 microarc seconds per year for both components. And that would be done basically using the first equation over here. We could estimate using the positional uncertainties. We don't have enough data yet from Gaia NIR to get a proper motion solution for Gaia NIR. So this sigma mu n of the new mission would not be available, but after 2.5 years of operations, then we could actually do a joint solution, and then we would get down to the 1 microarc second level of accuracy. And of course, there would be subsequent other data releases after that, so we don't have to wait the whole 10 years in order to get the good proper motions. We can get them early on, and I think that's an important point to make, that you know, we might still be alive to actually see the results of this thing happening, and I think that's encouraging, at least for me. So the catalog aging, I've been updating these plots that we've had for some time, but here on the top right plot you can see the degradation in Gaia over time, and if you go out about 20 years, already the accuracy of the positions of the Gaia catalog have degraded quite significantly, and they continue to degrade with time. So that means that we have to do a reset of the Gaia positional accuracy. The reference frame itself is much more accurate because it's based on millions of quasars, so the errors are much smaller, but that also degrades, and we could also improve that. But if we look here in the bottom right plot, then if we do the joint solutions, you can see that we radically slow down the degradation of the catalog. So the catalog would then become stable for 100 years or more. And that would be a very useful service to science. And I should also mention that there are other missions which I skipped over in the earlier slides, but things like Euclid and Roman are coming along, and they will also provide early measurements that could be incorporated into joint solutions also. So we will probably end up doing even better than this, I think, once we incorporate all the data. So here's the current this sky distribution of 1.6 million sources, basically quasars in Gaia data release 3, and you can see that there's a hell of a lot of data missing along the galactic plane, and this is, we can't fully fill this in with an infrared mission, but we certainly can fill in quite a bit of this missing data, and this is where most telescopes want to look also, so having more reference stars along the galactic equator would be very, very useful as well. And that would be nice. So the question is, I've raised this already, is how do we get 1 billion radial velocities? And we've been thinking already about different things that we could do. Adding a radial velocity spectrograph is going to increase the costs of the mission significantly and the data rate from the mission significantly. So one of the ways to achieve this, I've considered 3 different options. One is a slower scan rate. We could slow down the scan rate and absorb more photons per detector, and that would allow us to go deeper with radial velocities. We could also have slightly wider detectors, and you will see in the latest design we already have that actually. We have the wider detectors, and we can also have lower read noise detectors, and it turns out that these detectors that we're going to use already have that as well. So we already have 2 of these things in place, so I'm not even sure that we need to slow down the scan rate of the mission. It may not be necessary. But it's clear that radial velocities, the lack of radial velocities is one of the biggest problems that we have when we do scientific studies. And we have to use all sorts of fancy statistical techniques to overcome that. Doing a deep radial velocity survey, I think, is one of the areas that will make this an outstanding mission, but it's going to cost money, and we have to think carefully about how to do this well. And I should say that we will have another talk in about half an hour or so on the radial velocity studies that are ongoing now with some of my colleagues. So we have many big science questions. I've summarized some of them here, but I feel that these big science questions are something that are somewhat personal, so different people will probably pick out different science questions that they feel are more important. So I won't waste a lot of time with this, but I just wanted to show you a picture from Hubble. And basically it shows the pillars of creation in the visible and in the near infrared using a wavelength range similar to the one that we're going to use for Gaia NIR. And you can see the difference between them, that we suddenly see thousands of new stars in the background, and that's exactly what's going to happen with Gaia NIR. And you should all think about what is your favorite science case for Gaia NIR. I think there are a great deal of them, and I'm a huge fan of many of them. So I've listed my own there for you later. So now I'll move on to the technical part of the discussion. So in 2017, we did a CDF study with ESA to come up with a design for Gaia NIR. This design was designed to be a medium class mission. So we obviously reduced as many things as we could to try and make it fit within the medium class cost envelope. And we came up with this design here on the top right. You can see that we have one primary mirror instead of two primary mirrors. And then to make the two fields of view, then we have these two flat folding mirrors at the pupil entrances. And this was believed to be a somewhat more financially optimized design than the Gaia design. Now this design I think is actually still quite good, and I think it is what we need. I call this design Gaia NIR small, but we're not going to consider it anymore because I want a bigger mirror basically, and I'll try to justify why that's necessary. So what we can do here in the top left here in the corner, I have some simple calculations of the resolution that we can achieve. Gaia had a resolution of 0.12 arc seconds, a theoretical resolution of this with a 1.45 meter mirror. If we have Gaia NIR, what I call Gaia NIR medium, that would be with a 1.7 meter mirror, a single mirror again for the primary. That would give you a resolution of 0.24 because we're going to longer wavelengths, and that's a problem because we're also going into the galactic center where we have even more crowding, and we basically need to increase the resolution. And to increase the resolution, a simple idea is to just use two primary mirrors side by side. So basically acting as segmented mirrors, just like the James Webb Space Telescope has segmented mirrors. We think this can work, and then the maximum size that each mirror could be would be about 1.7 meters. That would give you a total mirror of about 3.5 meters. And then if you do the resolution calculation, then you get back to 0.11 arc second resolution. Now, it may be that this is too big, and it's going to make the entire spacecraft quite a bit larger. And we may have to tone that down, but even if you reduce this total D value here for the mirror diameter to about 3 meters, you still end up with a resolution of 0.13 arc seconds. And that's not bad actually, and that would probably suffice for us. So we have some flexibility in this, but this design here with the 3.5 meter diameter mirror I called Gaia NIR large, and the one with 1.7 meter diameter mirror I called Gaia NIR medium, and then I do all the calculations. But we have to recognize we may have to adjust this downward somewhere in between the two to be realistic and to make everything fit on board. Now in terms of launchers, there's quite a few launchers available listed here on the top right. And you can see that the Ariane 6 has a diameter of 5.4 meters. The Gaia NIR primary mirror is 3.5 meters, but it also means a bigger torus. Gaia had two 1.45 meter mirrors, so it's almost up there at the 3 meter level if you add the two together. So it's not that much smaller. The Gaia was quite a bit smaller. It was 3.8 meters in diameter when stowed on the spacecraft. So we think that we can fit Gaia NIR into the Ariane 6, and we probably don't need to go into SpaceX's Starship kind of diameters, which are much larger. and probably we prefer to use a European launcher if possible. But we have to look carefully at this optical design and the torus design to see how much we can actually fit and include all of the optics in. Now for the detectors, there's an Italian-owned company called Leonardo UK, and they have been developing small avalanche photodiodes that have high frequency readout capabilities for many years. The APDs amplify and measure signals in photon-starved environments, so they're exactly what we really need for this kind of mission. And they have almost noiseless amplification of the signal, so they're really very, very good for our kind of astronomy applications. They have two variants of these detectors at the moment. They can go from 800 nanometers up to 2.5 microns, or they can go from 800 up to 3.5 microns, but we think that 3.5 microns is too far into the near infrared. We will simply see too much. But another important point is we would pick up thermal noise, and that would be very bad for the mission. So our current proposal is to go for the 2.5 micron detectors, and this helps us to avoid most of the thermal noise. Also there's a possibility of going to more into the optical, going below 800 nanometers, but that requires new technology developments, and we don't think it's actually necessary to do it. And I'll show you results showing that even with these detectors we can still detect blue stars. But there's studies ongoing in the UK at the moment, some of them funded by ESA and some of them funded by the UK, and they're looking very carefully at these detectors now to see what can be done. Leonardo make a range of different detectors. They make this largest one as a 2K detector, this IBEX on the right-hand side. And they also make an Ikapono, which is a 1K detector in the center, shown here. Both of those have 15 micron pixels. Both of these detectors have slow readout frequency, so they're not suitable for our application. So we need a high frequency readout. And actually it turns out we need at least 554 hertz, I think I worked out recently, in the readout. But this, what they call large Saphira, which is a 500 by 500K detector, is capable of up to 2000 frames per second, and that would be suitable enough for the integration of the light that we need for the Gaia NIR mission. Now this detector itself is still too small. We need one slightly bigger, I think. But I think they can develop that, and they can make ones up to 1K detectors, and I'm going to trying to ask them to do that now. So what we really want to do is we want to get a series of 1K detectors. I'll just jump up to this diagram here for the moment. We want to get these 1K linear mode avalanche photodiodes, and we want to connect 3 of those together in a row, and that would give us then something that's a little bit bigger than one of Gaia's CCDs. And we would have to integrate the light using frame stacking across all 3 of these detectors in order to get one readout, basically. Now that presents a bit of a challenge, but the UK is looking at that, and they've been introducing this module concept where they plan to connect together 3 of these detectors in sequence, basically. And then the star would move in from the left and move across the 3 detectors then to give a single measurement. Another point is that for bright stars, it depends on how they implement this solution, whether they do the image stacking in hardware or software. But bright stars, if you're using a software solution, then you can just handle the bright stars automatically. All you have to do is stop stacking the image once it saturates. However, if they come up with a hardware solution, then this may be more complicated. So we have to see whether that's needed or not. They also use a very large gain. They have a gain of a few hundred used on these detectors. And they also have a quantum efficiency of about 85% quantum efficiency for these detectors. So yeah, here is this. Each one of these detectors, a star will transverse across each sub-detector in 1.81 milliseconds. And that means that we need a readout frequency of about 552 hertz. But then we have 3 of these together, so that gives us a total of 3072 stages. Now, let me have a look, see, do I want to, yeah, another thing I wanted to mention is that we've been looking at optimizing the pixel size as well of the detectors, and we don't think we need to have 15 micron pixels. We can go a little bit larger. So the latest design, we incorporate 18 by 24 micron pixels. And this is important because the fewer pixels we have, the fewer readout electronics we need and so on, and the less energy we need to read the detectors out. So this will help a lot. And it also, especially in the cross-scan direction, we're not that sensitive in the cross-scan direction. So having 24 micron pixels in the cross-scan direction really helps to reduce the number of pixels overall on the focal plane. And it also means the pixels are larger, so for the same number of pixels we get bigger detectors, and we can also reduce the number of detectors we need on the focal plane, which would also save a lot of money. And the impact on the science performance is extremely small. So the latest focal plane design here is shown on the top right. On the top left, we have again the Gaia focal plane, and you can see. So the main difference now you can see in the Gaia NIR focal plane, instead of having 7 rows of detectors, we only need 6 rows of detectors, and that's a major saving in terms of cost on the focal plane. And in earlier designs, I had 3 by 4 sub-detectors in each detector. Now I only have 3 by 3 sub-detectors to make up one large Gaia detector. That also saves a lot, and plus the pixels are bigger. A few other things that we're looking at, you can see here we have the basic angle monitors are distributed around the focal plane, and that will solve this problem that we had with Gaia. But also this, we were planning to have an extra red filter for Gaia that was not a physical filter but just a calculated filter by subtracting from the N band from the the NJHK. But we're now discussing whether we should actually put a physical filter in here instead on the focal plane. So that's this column here, what I call N5 at the moment. And another issue that we're discussing at the moment is and the low dispersion spectrograph is whether we should merge the H and K bands together, and that would also reduce another column of detectors. So I should just emphasize, I forgot to say earlier, that we put the filters directly on the astrometric field. So we're making astrometric measurements while doing the filter colors at the same time. And that's important because it allows us to get the full resolution for every star that we can resolve. We can also get the colors. That becomes much more difficult if we try to do the colors on the dispersion, the low dispersion spectrograph, because the crowding issues and so on will impact that much more. So, I think I've covered most of this already. I've already discussed the changes to reduce the number of detectors. Essentially, the detectors are one of the most expensive parts of the whole focal plane. So the more we can reduce this while maintaining the astrometric accuracy, the better. And I think we're making progress on doing that. And I also mentioned here that we separate the filters and the low resolution spectrograph because for various reasons that we really want to get the color information for all of the stars while still contributing to the astrometry. So the final thing I will show is just the calculated mission uncertainties. We've been doing this now for some years, so we have a simple simulation where we can estimate for a number of different reference stars. I've recently changed the reference stars I'm using, so I'm using the Pickles catalog now for these calculations. And here's an example of some of the spectra that we get from Pickles, and we can pick a range of stars from blue to red, basically, and then we can assess how well they perform astrometrically. All of the parameters I'm using are listed in this table. You can look at them afterwards if you're interested. But now if we do a comparison, on the left we have Gaia NIR, on the right, in the middle we have the Gaia NIR medium mission, and on the right we have the Gaia NIR large variant. And if we look at the accuracy for Gaia, I can do simulations down to any magnitude, so I go down to 24th magnitude. But you can see we get this exponential increase here of the errors as we go to fainter magnitudes. And you can see here, if I take the limiting magnitude of Gaia, which is 21.8 7, then we get 0.6 milliarc-second accuracy for an M5 3-star in Gaia, which is a typical red giant, that a cool red giant that Gaia NIR would also be very good at. So this is one of the stars that Gaia NIR should do better with. And indeed, you see here, instead of getting 600 microarc-seconds, we get a result at the same magnitude of about 88 microarc-seconds with the medium size mission in the center. And if we go to the large design on the right-hand side, you can see then we get a result of about 70 microarc-seconds. But the interesting point is if we go to 24th magnitude, which is where we should be aiming, maybe, probably 23rd magnitude is our limit, but let's see, we can extrapolate down to that. The accuracy for this red star would be 200, and I can't read it now, 299 microarc-seconds in Gaia NIR large, which is exceptional. It means that Gaia NIR large will do much, much better at the faint end for very red stars. And this is because of the low read noise and low background noise that you get in these new detectors. They have much better performance. If we look at the joint solutions, the combined end of mission between Gaia and Gaia NIR, you can see that this is for the proper motions. The previous one was for parallax. We can see that the joint solutions here are the solid lines, and then the individual mission solutions for Gaia NIR are shown here as the dotted lines on these plots. And you can see that the difference between the curves between the blue, for example, for the blue stars is almost 2 orders of magnitude between a single mission and a joint mission. One interesting feature here is the red stars. At some point here, you can see, maybe I should point with the pointer here. For example, here in the right-hand plot, if we look here, we can see that the joint solution and the individual mission solution actually converge. And this is because what's happening here is that the sigma mu term from Gaia NIR alone is dominating the solution. It's becoming better for very red stars. This doesn't happen for the blue stars because the contribution from both missions is still very good for the blue stars, because Gaia NIR is focused more towards the red stars. And this is very encouraging, but we do extremely well. If you want to look at the relative improvement of the individual solutions, 10 to the 0 here is 1, and so this means if you look at the left plot for Gaia NIR medium, you can see the blue stars do slightly worse than Gaia. But if we go to the large mission design, the blue stars are almost the same performance as Gaia. But the red stars in both cases are always better for Gaia NIR. And that's an important outcome here as well. This I should emphasize you're going to get for 50+ billion stars if we can go 2 magnitudes deeper. This is really exceptional numbers of stars that we would get very good proper motions for. So, and if we then look at the improvement of the joint solutions, where we only have 2.5 billion stars, we're roughly a factor of 10 better in both the large and the medium design, especially in the large design, we're basically a factor close to 10 improvement in the proper motions in that case. And that's for 2.5 billion sources. So another thing we've implemented recently, and there's another talk about the photometry later today, but we can also do the photometry calculations in our simulator, and we can do that also for these. Here, the green line on these plots is the Gaia 10-year projected results. And you can see here that even for blue stars, the photometry can almost do as well. Yeah, here's the range of different stars, but for the very red stars, we can get much better photometry than Gaia can do for those stars. And I give it, on the bottom row here, I give an example for an M5 3-star again, which is one of the default ones I use for demonstrating this. So we can do the photometry calculations also in our simulator. The nice thing is that Josep's calculations here in Barcelona, we agree pretty well with his calculations, and he will give a talk on more detailed work on this.
later on also. So the star counts here is, again, I take this plot from Barcelona. They've done some stellar density estimates towards the galactic center. And the bad news is that we get something of the order of 10 million stars per square degree towards the galactic center. This is at 21st magnitude. And if we go to 23rd magnitude, we're going to be up around 60 million stars per square degree. And this is the kind of data grade that we have to now start computing with to see whether we can actually handle them. I did some very quick estimates the other day, and it looks like we can resolve these stars on average. But of course, the stars will be grouped in clusters and so on, so there'll be patches of sky where we can't resolve anything either. So I think I will just skip these last few slides and take questions now. I've probably gone over a bit too long. But I'll leave you just with the summary conclusions. But basically, I want to say that in principle, we can design a mission that can outperform Gaia. The problem I see now as being the most difficult problem is, can we actually process these vast numbers of stars on board, and can we download the stars? We need very fast high-gain antenna that can actually try to download this, and this is going to be a major challenge. Unfortunately, we may be limited by this, not by what we can do on the spacecraft itself. So thank you.
So any question for David? Jordi.
Actually, I have, thank you, David. I have a couple of questions. One is on these long baseline time, long timeline proper motions, whether you will even need to consider accelerations and so on when you go that long in the time and with those very high accuracies, like in binaries and so on, or even the galactic potential. I don't know if I'm saying nonsense. But
I'm not sure what you mean by separations.
I mean when combining Gaia and Gaia NIR with the combined solutions for the proper motions.
Yeah, yeah, here's the plot. So I mean, you need to have at least, you know, you need to have measurements at different epochs. I mean, so that gives you the long time baseline. But as you saw in the results for the very red stars, the Gaia NIR mission on its own dominates, just because it's much better. So it's about the statistical weights of the different measurements.
Yeah, but what I meant is whether we can safely assume just linear proper motions, or
no,
some sort of...
yes. I mean, in terms of going around the galaxy, a linear approximation is still very good. But if they're binary systems, then we of course get accelerations, and then we will have. But then we have to do binary solutions as well. So like exoplanet solutions.
So probably in Gaia NIR, the NSS unit would be even more important.
Yes, it definitely becomes more. So any acceleration. Well, I mean, we can do simple things where we take into account the acceleration in the solutions as well, and these are the larger parameter solutions, the 7 and 9 was it parameter solutions that we already do in Gaia, so that could be done as well. Yes.
Okay, very good. And my second question, sorry, on the radial velocity spectrometer, if we go that deep with 1 billion stars and so on, we will have hell a lot of blending.
Yes, and
quite challenging.
Yes, this is very difficult. Yes, and that's why we're doing these studies now. So there's a talk on that a little bit later. I'm not sure he's considered blending that much yet, but.
More questions?
Yeah, thank you, David. Great talk. I know all missions are about compromises, right? But one of the main goals of this mission will be to observe the galactic center. So my question is, what would be the minimum acceptable angular resolution for the instrument, given the fact that we want to be a medium-class mission, right?
Yeah, I don't think I can give you a minimum figure, but I think if we have a number about 0.13 or 1.4 arc seconds, that would still do a very, very good mission. We would have to assess what we can do, but I think we should start with what can we afford and what can we fit into the spacecraft, and then we look at the resolution and see then where do we lose scientifically, and we will lose, of course, in crowded regions for sure, but we should always try to do the max that we can afford, basically.
For Gaia, we have the astrometric model, which is, proper motions, parallaxes, accelerations, perspective accelerations, plus binaries, and so on. So, for Gaia NIR, and when we have this long period of time, do we have to consider as well as a kind of systematic study for all the stars or for many, the deflections and light blending by other companions and so on?
Probably, I mean, it depends what you mean. The light bending in the solar system, we also need models there that are more accurate probably than Gaia is, and Sergei, for example, is very interested in this and improving the current models. But you're talking maybe at the source level.
Yeah, at the stellar level, yes.
It depends how close they are together, yeah, but yes, I mean, but we will see the light bending if two sources get close together and one is behind the other for sure. But that we already see in Gaia. It'll be the same problem in Gaia NIR. I don't think it'll be really worse though. Do you think it would be? It would be the same, I think.
Yeah, well, I was thinking that being the accuracy much higher, that perhaps the effect will be seen for many more stars.
Yeah, the relative effect will happen more often, right? So we will have to have more sources that are more complicated processing, yeah, because many of them probably are in binaries, yeah.
Andres, just a comment on the Galactic Center question you asked before. I will show some preliminary calculations tomorrow about that. So with even 0.3, it's really, really good. And then I also have a question for you regarding the pixel scale that you expect for this kind of detector. How much will it be, more or less?
The pixels?
Scale, yeah, the pixel scale for this, because it's
at the moment we're using 18 by 24 microns for the pixel pitch.
Okay.
And then we will have, in the long scan direction, we will have 3072 pixels. That's the assumption.
Okay, because this will matter as well for the Galactic Center, because you need to avoid undersampling. So.
Yeah, I think we are undersampling a little bit, but so is Gaia. And I mean, it's a trade-off again. It doesn't seem to be, for the astrometry, it doesn't seem to be a massive problem to undersample, well, a little bit, for sure.
Thank you.
Okay. So let's thank David Hobbs again. Thank you. Okay, we have Frederick Safa online. He's the head of the Future Missions Department in the European Space Agency. Thank you very much, Frederick, for giving and participating to this workshop. You should be able to share the screen.
Okay. I have an echo.
Did we lose? No. Frederic, are you here? No, he's just lost him. Okay, let's wait a couple of minutes.
Okay, sorry, I had to
You're back,
disconnect.
yes.
I had to disconnect and reconnect.
Okay.
Okay, let me see.
Okay, we see your screen.
Okay, do you see the PowerPoint presentation?
Yes. So the floor is yours. Thank you very much.
Okay, thank you. Sorry for this delay. I have been asked only recently to join this workshop and explain how Gaia NIR would fit in the science program. I prepared rapidly a presentation. First, let me tell you where we are standing in the science program today. So we got a good increase, I would say. It's modest still. It's a 10% increase in budget in terms of purchasing power at the ministerial end of last year. And this is very good news because it allows us to complete the Cosmic Vision plan and to start the Voyage 2050. So I'll come back to Voyage 2050. And of course, Gaia in the infrared would be part of Voyage 2050. So just as a reminder, these are the missions we had in the Cosmic Vision plan. So most of them are either in orbit or in development. SMILE will be launched in 2 months, Plato early next year. So Comet Interceptor will be in 28. So I would say by the end of this decade, most will be launched, and what will be left is Ariel, Envision, and the 2 large missions, LISA and New Athena. However, both should be launched in the next decade. And the last 2 missions for which the development is to start are New Athena and Arrakis. So Arrakis is planned to be adopted hopefully in June this year. It's a small mission, fast mission, while New Athena is planned in 2027. So that's our current plan. And with that, once we start New Athena in 2027, we will have completed the Cosmic Vision plan, at least in terms of preparation and starting the development. So Voyage 2050, as you know, there were 3 themes for large missions. The first one was addressing the moons of the giant planet, and this is what we call L4 today. The mission has no name yet. And we have been focusing on this mission since the recommendations of Voyage 2020 committee, which we got late 2021. And we made significant progress here. So now we do understand what we can do. It required a lot of iterations and in particular to fit within the budget and the actual capabilities we have. So the next theme is L5. It's called this is not coming from me, these titles, From Temperate Exoplanets to the Milky Way. And as you know, we see Gaia in the infrared as part of this science theme, one way or the other. And it could be either L5 or a part of L5, or it could be an M mission addressing this theme. And then the last large mission theme is a new physical probe for the early universe. It's a kind of LISA follow-on, so we are just starting LISA. LISA will be launched in 2035, and we'll have to see what will be this follow-on. So I heard I listened to most of the speech of David Hobbs, and he mentioned the timeline needed. So I saw I was already connected. I have to say for L5, the timeline is more or less fitting what I have heard. I'll come to that in a minute. So, but before that, let me say that what we got at the last ministerial is allowing us to start Voyage 2050 seriously. So first we'll have to select the M7 mission in June this year. It's one of these 3. The 3 are just feasible today. And we will ramp up the technology preparation of L4. So L4 today is fairly well defined. It's a mission to Saturn, to the Saturn system, which will make a tour of the Saturn system and end up with a lander on Enceladus, a fixed lander with without a motion capability or a long-term long life possible on Enceladus because of power issues. It's not based on nuclear power, so we know how to do this mission today. The baseline is to consider 2 Ariane 6 rockets and to make an assembly in orbit because we need a lot of fuel for this mission. But the core spacecraft is not tremendously more difficult than JUICE. It's the next level, but it's not really an order of magnitude above JUICE. So it's a lot of mass, it's a lot of technical aspects to be dealt with. And of course, the lander by itself will bring its difficulties, but we see a safe path, I would say, if we spend enough effort, like we did on LISA and Athena, on New Athena, to be able to launch this mission in the 2040s. So the plan is to adopt this mission in 2035, 34, sorry, and to start the development in 2035. And this schedule is driven by the illumination we'll have at Enceladus. So in our mind, and L5 was coming after, so it all boils down exactly on what we will get also at the next ministerial. Because when we presented the budget increase request for the last ministerial in 2025, we explained from the very beginning that what we were after is a gradual increase over at least 2 ministerials and preferably 3. So what we have in mind is also an increase in budget in 2028. And I do hope the member states will follow us on this one because we really needed to be able to do all what I'm telling you. We are looking in the details now in the long-term implementation plan. It will be discussed with the SPC in June, in March already, but later on in June adopted. So things are still unclear, but you know things are always unclear and will remain unclear. The key point is that today we got a good increase and we are able to start the work on L4 and we are able to contemplate now to starting the work on L5. So that's the good news. However, we did not discuss yet L5 with the Science Program Committee, so I'll come to that in a minute. Now, in terms of timeline, we know by experience that it's better to avoid having large missions running in parallel in the program. This will stall the program, give or take. So what we see is L4 being adopted in 2034, the late 2034, for a number of reasons, and which will lead to a launch around 2043, something like that, maybe 44. L5 would be adopted in this scheme in 2039, give or take, starting the development in 2040, and so the launch should be, logically, before the end of the 2040s, in the late 2040s. So it's fitting, give or take. 2045 was mentioned. I think this one is too early, and I'm sorry to mention it. But somewhere between 2048, 2049 is perfectly realistic today, and will be consolidated if we get the increase. So now we have to keep in mind, we have in our plan also lines of collaboration with NASA. And one mission has been identified and selected by NASA since the Voyage 2050 committee, after the Voyage 2050 committee gave its recommendations. It's NASA HWO. It's also addressing the L5 theme, give or take. So this is in the picture also in terms of spending, in terms of science themes we can address with this mission. And the good news on HWO is that while the presidential budget request was pretty low on HWO. It seems NASA is recovering the initial budget they have in mind, and our understanding is still to be confirmed by the new presidential budget request that will be submitted shortly, that the work will start on HWO already this year. And a significant funding would be spent on that on other side. So if this is confirmed, it means that we will have to catch up and to spend some effort on HWO. And we would start most probably, I'm saying that with the minimum reservations, because we have not discussed all the details yet with the SPC, but we did discuss the overall approach. We will have a call for to open to the community on and organized with now involving NASA, of course, it's their mission at the end, but we would be providing at least one instrument, one of the main instruments of HWO, which is TBD today and to be identified, as we always do in the science program, through a bottom-up approach and open calls, and taking the best possible candidate given the constraints. So that's still TBC to begin with, because the NASA budget is still TBC, and it's still subject to the global discussion we need to have with the SPC this year following the ministerial. It's just starting now. Now, all this being said, I mean, how could we see Gaia NIR in the landscape of the science program? Based on what I have seen, I see a lot of things are being discussed, being said with technical details. So we are supporting the detector development. I think this is useful in any case on the long term, and is something to speed up as much as we can. And we do have Gaia NIR in the radar when we are speaking of that. However, on the overall mission concept, on what we can do for the mission, you know, I mean, you know, all of you know the Gaia story, and you know we'll have to cope with limitations in budget and in capabilities. So the difficulty will be really, as for any mission, as we had for L4, we spent 2 years before converging on a potentially feasible L4 concept. We'll have to follow a same approach and bring it to a point where we believe we can achieve it within the budget. And the budget earmarked for large missions is in the range of 1.5 billion euro, give or take, in current conditions, just to give you an order of magnitude. But you have to keep in mind this is the total budget, the cost of that completion to ESA. So the industrial cost you could have in mind, taking the LISA case, I would say, as a reference, would be at most today in the range of 800 to 900 million euros. And with today's condition and today's industry, you have to be extremely careful on what you can achieve for this budget. And that's why I have the feeling that probably what is important to do for L5, but we will discuss that more deeply with our science program committee, is at least to start a process where we identify the candidates. So it can be an open call. We will need an open call for HWO, I mentioned that. L5 theme can be connected to HWO. So it could be that we are looking at the globality one way or the other. And keep in mind that all our missions are in open call. So even if Gaia NIR was mentioned as a possibility, simply by the Voyage 2050 Science Committee, it was not mentioned as L5. So there will be a selection based on scientific merit and on technical and programmatic feasibility. And maybe we'll spend some time, like we did on L4, to find the best possible path. So on L4, at the beginning, people were a little bit depressed because they were thinking there is no way to do a very ambitious mission. At the end of the process, I think the scientific community is very happy now and do see the L4 mission concept as extremely ambitious and are convinced it should be feasible. So there is still a long path to go on L4, but we have started the work, we are starting the technology. So I think this work we have done on L4, which was done in 2022, 2025, should start now on over 2026, 2028. And we'll have to address, so assuming Gaia NIR goes through this process, we'll have to address the various technical concepts. So what I saw is quite ambitious. I don't know if it fits the budget envelope I just mentioned. So what you have to be prepared to is, even if Gaia NIR is connected to the L5 theme, to have a clear view on what are the top priorities scientifically and where we can, what are the adjustment variables, where we can play, what we can adjust to bring the mission in the feasibility domain in terms of cost and programmatics. And all this is assuming we are converging on the detector, timely converging and getting them at the end of the day at a reasonable price. Now, there is always another path, which was the one mentioned by David Hobbs on considering Gaia as an M class could apply to any opportunity for M. So the last one is running, it's M8, but we'll have another one for sure in a couple of years. I cannot tell you exactly when, but we typically have a call every 3 years. So that could be a possibility, but here the budget earmarked today for an M class is quite low. It's 750 million euros, everything included. So it's the cost at completion, and it means an industrial cost in the range of 350, but maybe we'll increase this envelope a little bit, especially if we have an increase in 28. But we will always be in the range of 450 maximum. And that's quite short in today's condition, given on what we can do for this amount of money. It's well below, for example, LISA or New Athena. So it means here require a significant descoping, but maybe it could be a path to ensure you have a follow-on of Gaia timely, because I heard the comment and it's quite true, that you need to have continuity, a minimum continuity to have, because people will move, people will also retire. So to have, if the top primary target is to have again, it's a matter of objective and strategy, is to have a mission in the 2045, 2050, what I heard, the range mentioned by David Hobbs, then I would not rule out this path, because if the first path does not work, you will have to consider the second path as a backup, but of course with lower ambitions, but you will have the capability to connect with Gaia and to have an excellent science case, I'm sure. But certainly not to have the impact you would have with the high performance you could achieve with a larger budget. So I think the difficulty on Gaia NIR is not specific, and any mission is like that. I would say you have a range of possibilities and you have to optimize within boundaries. And it seems to me that the first step that would help the community is to start having the ball rolling for L5. So how we will do it, I don't know exactly, because we have not discussed the details with the SPC, but I can tell you what we did for L4. It worked fine, and most likely we'll use the same ingredients. On L4, we have put in place a dedicated science expert team, I think it was called, with whom we had strong interactions and in doing system studies, looking at concepts, looking at whether it fits or not, coming back to the committee. And this loop happened 3 or 4 times, I don't remember, before converging on the right concept, which is now accepted and seen as the best solution we can dream of. So probably we'll have to do something similar for L5. Perhaps we can have 2 good proposals on L5, and we'll have to pursue them for a while, but not too long, because we cannot disperse. It would be 1 year maximum for me, this affair. I don't know. It really depends on how the discussions will go, what we will get, and what are the candidates. But I would say definitely Gaia NIR logically should have a place in the science program, given the front-running capability of Europe on global astrometry. And I think it's understood by all parties that it's a natural next step after Gaia. So the key question is how to get there and to start working on that and to start the technical assessment of possibilities. I would say if we do all what I have said, if we agree with the SPC on the long-term plan, we issue a call, we start addressing L5 theme, which would fit nicely what we did with L4 in 2021, 2022. Then I would think we could have these first technical evaluations discussion already starting in 27 and maybe concluded in 28. And then you would have a path which is clear to all and defining a roadmap, I would say, leading to L5 developments, pre-developments, or technology preparation or scientific preparation. So I'm afraid I cannot tell you much more than that, but I told you basically all what I could with today's knowledge. Can you still hear me?
Can you hear me? No, not.
Yeah.
Yeah?
Yeah.
Okay, so thank you very much.
I was wondering if you listened to me tomorrow.
Yeah, sure, yeah, we did. Any questions from the audience for Frederic?
Ça va, Frédéric? Très bien. It's a short question about the potential extra funding that you mentioned, HWO. I suppose that there is no competition for the same sources as Gaia NIR, because I suppose that this HWO comes from the budget of the NASA participation, which is usually at the bottom of the plot of the funding. Thanks.
Yeah. It's correct. HWO is more a decision whether you want to work with NASA on this flagship mission. And I think we are far in Europe of developing, of having the capability, simply financially, not technically, but at least financially, comparable to HWO. So I think there is consensus we cannot miss this opportunity. And that's why we have this line in the long-term plan on HWO, and we have a line on L5. But what is still open is the weight you put on each line. I mean, HWO can be a 500 million contribution to NASA mission through an instrument, or can be a little bit more. It can be a 1 billion contribution. Keeping in mind that the size of the mission, as stated by NASA, is in the 10 billion class. So if you are a partner, you have to invest at least 5%, I think, to be a credible partner. So these are the figures being discussed, but everything is open there. And it's in this sense that you may have a crosstalk, I would say, between the two lines, because at the end it has to fit the global budget. That's a must-have. And the schedule is not the same also for L5 and HWO. So there are things to put in place and to see what is the sweet spot and the optimum scenario for L5 and HWO. And maybe we cannot answer this question before having run the process I have mentioned, which is issuing a call, getting the ideas, and understanding what is the landscape of the possibilities.
Thank you. Any other question? Okay, so thank you very much, Frederic. We make a stop now, a break. We're running late, but I think it has been a very, very interesting first session on Gaia NIR. I think we can resume in 20 minutes. We think we all need a break, and let's resume at 5:20. Okay. Thank you very much for all the people contributions online, and see you soon.
relatively technical. First one, Jordi Portel, Barcelona. I have to share the screen. So first we escape here, and then we go to Zoom, and then share a screen, which is here.
The full screen, I guess.
Share. Now we are sharing, and we go here, and Control L.
Control L.
O Command L.
No, control L, igual no te lo ha pillado, pero igual está haciendo eso. No, el toque no va muy bien, haz un clic aquí a ver si te lo pilla. Ahora. Okay, back to work. I guess that we all are tired, it's a bit late, so I will be quick. This is like Gaia, but better. Thank you. Okay. No, now seriously, it is, I think that this screen of Zoom is a bit annoying. I don't know if the others also see this. Well, never mind. So it is about the data handling and data processing for Gaia NIR. I have to say I apologize in advance because I actually started this talk yesterday because I have some products deadline tomorrow. So bear with me. I will try to do my best here. But overall, it is just to show you the kind of challenges that we will be facing when trying to and when achieving to process all the huge amount of data that we will get from Gaia NIR. So is it really that difficult, you may be wondering, because at the end you may know or you may have heard of many Earth observation satellites or many other satellites that you just kind of plug and play, you just follow kind of standard interfaces, algorithms and so on, put the button and that's it. No, in this case it's much more difficult. We have these special measurement techniques that we carefully designed for Gaia, Gaia NIR, Plato, Euclid, and whatever. We have large amounts of data that especially need to be processed with tailored algorithms and software. So yes, it is difficult. The first step that David has already mentioned is that we need to carefully design how we will acquire the data on board, which will be our measurement technique, not only the scanning technique and everything, but also the data acquisition method, whether we get full frame images from the CCDs or CMOS detectors in general, or we get some small windows of pixels around the detections, if any, on board of stars, like this one, or just one-dimensional profiles, which is the vast amount of data that we get, from Gaia, or these dispersed images for low resolution or high resolution spectra, and so on. So we need to, this zoom thingy. Yeah, no, even I couldn't read this. Okay, we need to carefully design the approach, as I said, to make sure that we get all the necessary science, but being realistic with downlink capabilities, of course. One thing that those of you that know me, you know that it's my favorite topic on data compression. I really suggest that we take into account compression in early stages and at least think of some prototyping, some basic ideas, even some testing on how will it perform, because it may avoid surprises. I have seen more than 1 and 2 cases where people at the end say, oh, it's too late, we can do any development, data doesn't fit the downlink, we will just downsample or quantize the data that we are acquiring, and therefore losing science or losing some data from data products from the satellite. On the other hand, maybe it will help us in simplifying the measurement techniques or the measurement approach. Perhaps with the many stars that we will get from Gaia NIR, it may even be more advantageous to get the full frame images with some smart compression techniques. I don't think so, but perhaps, depending on some cases in very crowded regions, one may consider that. In any case, data compression specifically in Gaia NIR will be very complex. Again, as in Gaia, we participated in the TRP study with ESA to design the onboard compression algorithm for Gaia, and it was quite complex, and in Gaia NIR it will be the same. We had a compression ratio requirement of 2.5 lossless, because otherwise we lose science there. So one curiosity, some initial studies were not able to compress at all the data with some realistic simulations because of prompt particle events, some statistical outliers that were breaking completely the algorithm. So it's good to have realistic simulations ASAP. Then we also need to consider the onboard data handling to have the proper resources to process the data to be acquired on board. For example, in Gaia, we had to handle typically 800 stars per second with peaks above 6,000 stars per second and leading to an average of 50 million stars per day, or transits of stars per day. Despite we had 21 power PC processors on board, 7 times 3 for redundancy, we couldn't cope with some scenes. So for example, this is in Omega Sen. You see, it's quite a nice image. You see the few CCD strips going through, this is real data from Gaia, going through Omega Sen, the global cluster. And you can see that here you have some dark regions. These are basically 1 dot per detection on board. And it indicates that the video processing units on board Gaia were not able to handle all the detections that were arriving from the CCDs. And Gaia NIR, the same will happen most probably. So we have to fine-tune and size the onboard resources adequately. Of course, we can consider graceful degradation on board, for example, progressively deactivating some elements of the pipeline, like the incorporation of larger data elements into the star packets, like BPRP, RBS, RBS, that's another packet, deactivate compression even, because that's quite time-consuming, things like that. In Gaia NIR, it seems that we may go to ARM-based processors. That makes sense. They are quite powerful and not too much energy consuming. But in any case, we should be careful on including enough power for these requirements. I found this figure somewhere. I don't know if this is more or less up to date. This 150 million stars per day, maybe even more in some cases. We'll see. And all this, just remember that it will require to track all the detections on board, send the commands to the hardware elements to acquire the data if needed, compress the data, create the data package, and so on. Of course, we need to consider onboard data storage because I don't think that we will have continuous downlink from the satellite. That's very expensive. In the case of Gaia, we had typically 8 hours a day of downlink. So the data had to be stored on board before downlinking. And in some cases, because we didn't scan and we will not scan the sky in a perfectly uniform way. In some cases, you may know, we were scanning the galactic plane perpendicularly or tangentially or so on. And in some short periods of time, a few days, we were generating much more detections on board than on average. And in those cases, we suffered some data deletion on board because the downlink was not able to download everything on time before the PDA-Geo, the onboard storage, was getting more data, and that was getting full, so something had to be deleted. Overall, we downlinked 36 gigabytes a day. Euclid, for example, can manage 100 gigabytes a day, if I'm not mistaken. Gaia NIR, perhaps something in the middle, maybe closer to Euclid, things like that. So even nowadays, it seems feasible. This is the phased array antenna, by the way. But yeah, we need to be really careful about that. And of course, data compression will play a significant role here. It is advisable that we design a multi-priority downlink scheme in the sense that we prioritize the download of the most interesting or constant or whatever you want to call that measurements or the data, so that you can get the basics to make the minimum product, of minimum scientific product. And all the rest, download that if you can, if you have enough downlink channel. This worked really well in the case of Gaia, so I strongly recommend to do that in Gaia NIR as well. Overall, we have downloaded 140 terabytes in 10.5 years, and I presume that much more in Gaia NIR. Moving from on board to on ground, Josh has done a very good talk, of course, on the lessons learned and so on. I will also tackle a few of the lessons learned from Gaia towards Gaia NIR. I think that the approach in DPAC has worked really, really well. Many things can be improved, of course, but the idea of having, first of all, one science operations center doing the critical things to make sure that the essential part of the mission was working well, it was very good, because at least the L0, the first level of data products, was arriving fine and was being processed fine. And then all the rest, well, actually, SOC in this case was part of DPAC somehow, but all the rest was defined, as you know, in different units. More or less, each one doing a different thing. I have heard, or I have seen in some other missions, that there are some redundancies or repetitions of tasks in different centers. I think that in LISA they do something like that. But here I think that it worked quite well, just to spread the kind of tasks to be done. So yeah, as I was saying, the absolute priority in the daily near real-time processing is to make sure that the basic raw data, the lowest level data, is promptly received, processed, and stored in some self-contained or correctly arranged format to make it easier to be processed afterwards. It should be data-driven so that you promptly trigger the processing tasks as soon as some given data type arrives. And then this would be for the essential data, and the secondary, so to speak, priorities would include some initial processing, like getting some initial image parameter determination, like the centroids, the flux estimations, the cross-match of the several observations to the starting catalog of sources that you would have, and creating additional sources when you don't find them. All these could be considered secondary, because we found that we suffered this in Gaia, that in some cases we had to deactivate some of these things because the systems, the on-ground systems, the cluster, was not able to cope with the throughput that was arriving. So we better prepare for that just in case. The first look system, you may have heard about that in Gaia, was a very good idea, because it was even generating a first daily astrometric solution with quite nice accuracy. And it's also very interesting, so that you get a deeper verification of the correct operation of the satellite and of the meaning of the data that you are getting, so that you are sure that the onboard instruments, the way you have configured the several detectors, data handling and so on, is correctly fine-tuned, and is not, you are not losing some of the data quality that you are expecting. And all this near real-time processing also allows, of course, for alerts of solar system objects, new asteroids, new objects, transients, supernovae and the like. So all this is quite interesting. I was mentioning before this multi-priority scheme in the downlink. This was some initial design, some proposal that we made for the IDT system in Gaia, this initial data treatment. It was designed so that we were assuming that in each contact of the satellite with the ground station, we would be downloading first the higher priority data, then the medium, then the low priority data, and so on, processing them as it was arriving. This was the theory, and this was the practice. So we did quite well on this regard. This is a real diagram of the several tasks that were triggered in this system. You can see here the different contacts with the spacecraft and the several data inputs that were arriving from the spacecraft into the daily processing system, and then the progressive processing of the data that was arriving later, that was requiring more computing load on ground, and therefore, yeah, it was quite well designed, we think. So going quickly into some lessons learned. All this is written here in text for your pleasure whenever you want to download the PDF from the website. I think that it's good, as I said, that we define several units, each with a clear goal and separated between different centers and so on. Sometimes we have faced that politics, like spreading responsibilities between different countries, were not in perfect agreement with the know-how or expertise that some groups may have. It's good to try to harmonize these and do a more meaningful spread of the tasks. Reference systems and conventions, this is highly recommended to define this as soon as real work on the satellite starts. And then one just small comment that some people some time ago was joking about, oh, but in ages in the core astrometric solution, you live in a bubble. You imagine that everything is ideal data arriving into your system. Yes, that's okay, that's fine. It's a very difficult system, just this core one. So many systems, it's fine that they are created and defined to create this bubble, to isolate the core solution from all the instrumental effects. Technical lessons learned, it was already said, to define common processing language, tools, and so on from the very beginning. It's really practical. Perhaps Python will be a good choice for Gaia NIR, I don't know. Test-oriented development, so you first define the tests and then you implement the software so that you are sure that you're fulfilling your requirements. Cyclic development, so that you do incremental releases of your software. It's a very good idea. Implement realistic simulators as soon as possible. We did that, Eduard, I don't know, where are you? We did that like 14 years before launch Gaia, so that brings us to 2030 for Gaia NIR. We should have, we should start doing a good telemetry simulator, the data stream for Gaia NIR around that time. Would make sense. Define an adequate file format, as it was already said. GBIN was fine, but maybe better or something like Parquet or something like that. Right computing approach, right framework approach, avoid these proprietary schemes that I just mentioned. Ensure consistency in the data. There are some ideas which were very nice for Deepak, like a solution identifier to make sure that you embed the solution that you have worked on in the data. That's really convenient. Also some other identifiers like the transit or measurement identifier, the source identifier, these kind of things. And then, well, just all these technicalities, I will not spend on these. This is really a wonderful thing. I cannot stress enough how this thing has helped us in Deepak, the dictionary tool, to centralize all the data model and the interfaces that we have used in Gaia. And I really, really insist on using something like this for Gaia NIR and for any scientific mission. This is just wonderful. And well, yeah, licensing approach, code repository, long-term support of common tools, define adequate services for the people working, that will work in the mission, and take the human dimension into account, with some welcome packs, with some things well defined for the people that will need to work there. Don't postpone too much your tasks. One Jira a day keeps QA away. And take the truth that some key people will leave the project in the worst possible time. So get planned for that. So yeah, just the summary, that many decisions that you will take for the onboard systems will define your Gaia NIR selection function, the completeness, how the completeness degrades on the sky region with the magnitude and things like that, the kind of objects that you will be able to observe depending on the scan angle, these kind of things. Acquisition, downlink must be feasible, and on ground, just have a look at the lessons that I listed.
Merci, Jordi. He only started last night.
Imagine what he can do in 1 week.
I like the sentence, astrophysicists are not software engineers,
Yes.
nor vice versa. Time for one question.
So actually, I like the sentence as well. I was going to say it. And Julia instead of Python. You commented this multi-priority downlink, but you also commented on the importance of the energy on board of the spacecraft. So how much energy, how much computing power does this require?
Nothing.
Okay,
No.
it's done.
It's storing depending on some attributes of the measurements into one file or the other.
Oh,
That's
pretty-
it. It's more thinking than computing. It's just designing that properly.
Yeah, designing that properly. Okay, cool. Thanks.
Sí, sí. John Apot Mesaros, are you there?
Yes, can you hear me?
Yeah,
Hi.
we cannot hear you.
Oh, can you hear me now?
Now, yes.
Okay.
You will have between 18 and 19 minutes, okay? And I'm very
Okay.
interested in what you will tell about the radar velocities.
Thank you.
The floor is yours.
Okay, so thank you very much for the invitation. My name is Szabolcs Mészáros, I'm from Hungary, and I will talk about the radial velocity and atmospheric parameter calculations for the Gaia NIR spectrograph. So the general goal is to select the wavelength range for the spectrograph between 800 and 2300 nanometers. And in order to do this, we use synthetic spectra from the BOSS database. So I generated 10,000 random synthetic spectra with 4 different resolutions, with random TAF, log-G, and metallicity. You can see the TAF, log-G distribution of this random sample here with blue dots. The yellow ones show you what apogee observed. And I shifted all of these randomly generated spectra with a random radial velocity. And I also applied a random Gaussian noise to each of these and re-derived the radial velocities of these random spectra. And I used 150 nanometer wide regions in 5 nanometer steps and basically mapped the entire wavelength region between 800 nanometers and 2300 nanometers. So if you add all of these numbers together, that means that I did 22 million cross correlations. So basically brute forced the entire thing. And at the end, I examined the scatter and the 95% and other things, other statistics of the differences between the derived radial velocity and the original assigned radial velocity. And I also calculated some initial temperature and log-G metallicity precision estimations for selected windows that I'll talk about a little bit later. So how does this look like when you plot this as a function of central wavelengths? So on the top panel, you can see the logarithm of the scatter and the 95 percentile as a function of the central wavelength. Here, the width of the window is 100 nanometers, and the resolution is 10,000. And both of these statistics follow the same pattern. So from now on, I will just use the scatter for simplicity here. So on the bottom panel, you can see the logarithm of the scatter of the radial velocity differences as a function of central wavelength. And the different colors shows you the different resolutions. So as you can see, there are spikes here, and these spikes usually correspond to a strong absorption line appearing and disappearing from the window. But you can see that there are several wavelength regions where the estimated precision falls below 1 kilometer per second in the entire sample. And this scatter here is dominated by the low signal to noise, high temperature sample, by the way. So there are multiple windows that we can select from here, and I highlighted where Gaia and Apogee have observed. One of the most important conclusions from this test is that we cannot really go below resolution 10,000, because if we do, we cannot really reach or go beyond 1 kilometer per second estimated precision. So having a 10,000 resolution as a minimum is basically a must. And we need that, by the way, for the abundances as well. Now, what happens if I split this sample into different type of stars? So on the top panel, you can see the scatter of the radial velocity differences as a function of central wavelength for the hot stars. So anything that has temperature larger than 7,000 Kelvin. The second panel, the blue one, shows you the F and G type main sequence stars. The panel below that is the GK giants, and the last two is the K and M dwarfs and giants. So out of all of these tests, out of all of these samples, you can see that there are different regions where all of these samples show relatively low scatter. So one of them is where Gaia right now observes. In fact, out of all of these tests, it came out that the calcium triplet is the best region to get radio velocities from. But of course, that's where Gaia Gaia observed before. Now, another region lies around around 1200 nanometers. That's this region here, where all the samples provide low scatter. And this region has a big advantage compared to Gaia because it does not have almost any molecular absorption lines. So quantum normalizing the low temperature stars is pretty easy from this sample, but it has the disadvantage that the wavelength is not sufficiently longer than the Gaia spectrograph. So the reddening is not really much lower than in Gaia. Now, I selected the Apogee wavelength in order to have some synergy with Apogee here. But as you can see, in the Apogee wavelength, and the blue side of the H band, the scatter is not really low at 10,000 resolution. So the H band really starts to shine only if the resolution reaches about 20,000. And below that, the radial velocities are not really precise. And this is because there are a bunch of molecular absorption lines in the H band that blend together at lower resolution. So you don't have those well-defined absorption lines in the H band. So I'm actually considering to go a little bit bluer, just below the H band. You can see here, this region, where we have stronger absorption lines that can be used to get precise radial velocities. So I actually want to go into the lower wavelength region. And the last one is basically the K band. So in the K band, around 2 microns, there is a narrow region where there are strong calcium lines that appear in the spectra, and these can be used to get good radial velocities. And for cool stars, which will be the kind of star that Gaia NIR will mostly observe, this precision is on par with the shorter wavelengths. It's actually almost on par with what Gaia has at 900 nanometers. But with increased resolution. So that's basically these are the 4 different regions that I selected based on the radial velocities tests, and then started to experiment with narrowing down this wavelength region. The problem is that having a 100 nanometer wide region is too large to fit the spectrum in its entirety on the detector. Here you can see an example of spectral range, a main sequence, and the red giant stars, and I highlighted where these 4 different windows were selected initially. So I use this very simple equation to estimate the maximum resolution that can be achieved in a window where the lambda c is the central wavelength of the spectrum, the NP is the total number of pixels that are available on the detector for one spectrum. The ON-R is the number of pixels per resolution element, which is always 3. So I set that to 3 in every single calculation. And the lambda R is the wavelength range centered around the lambda C. So if you plug in the numbers for the Gaia spectrographs, this gives you 13,500, which is the maximum resolution that can be achieved. Now, in reality, the Gaia spectrograph has lower resolution, so keep in mind that every single resolution that you will see from now on actually means a maximum possible resolution that can be achieved. So we have to count for some degradation in the resolution at the end. So based on this, I started to downsample these four 100 nanometer wide regions. So in this plot, you can see these 100 nanometer wide regions with a resolution of 10,000, having a sun-like star, a red giant, and the red dwarfs. And the grayed areas show you what I initially selected. And in this table, you can see what kind of pixel sizes, what kind of window sizes I used to estimate what resolution can be achieved. So, for example, if the mission decides to use a spectrograph at the wavelength of Gaia, then there are two options: increase the resolution or increase the wavelength range. So here I went with an increased wavelength range, but that also meant that I had to increase the window size. Now, the 1300 pixel window size is what basically Gaia has used, right? They had 4 pixels fewer, but I just rounded numbers here. So the 1300 is basically means a Gaia-like mission. And as you can see, for an increased wavelength range around the calcium triplet, 10,000 resolution cannot be achieved. And this is the same with around 1200 nanometers and even in the H band. But in the K band, even with the Gaia-like mission, having a 74 nanometer wide region could achieve a resolution of 10,000 at least. So, but this is with the assumption that we have more pixels available for one spectrum. So this is a problem because of spectra will blend together on the detector. So we need to think a little bit more about this. So before I do that, I have 2 plots to show you. On the right side, you can see the delta radial velocity as a function of effective temperature and signal to noise in my tests for these 4 down-selected windows. And as you can see, we can, in the K band, we can get good radial velocities up to around 7 and 8,000 Kelvin. And above that, the radial velocity precision will suffer because almost all absorption lines will disappear from the spectrum, and there will be just one hydrogen line that you can use to get radial velocities and nothing else. And something similar happens in the H band, by the way. So I have no points or very few points above 8,000 Kelvin. And that is because almost all points are above this plus minus 7 kilometer per second that I used to plot things here. So this means that going to longer wavelengths will mean that we will lose almost all hot stars above 7 or 8,000 Kelvin for radial velocities. So I can show you some initial estimates of the effective temperatures. Sorry, I forgot to say that the precision, the estimated precision below 7,000 Kelvin on these plots is around 200 to 500 meters per second. Depends on temperature and window size. But we are well below the 1 kilometer per second precision here. So here you can see an initial estimation of the effective temperature and the delta log G as a function of effective temperature and log G itself. So you can see that the Gaia wavelength range or the extended Gaia wavelength range provides good temperatures up to 10,000 or even higher temperatures. But every single other window that are at a longer wavelength will degrade the temperature estimation for these hot stars. So, for example, in the K band, we will lose almost all stars above 8,000 Kelvin because we'll have just one single hydrogen line to estimate the effective temperature. So, this really means that going to long wavelength will result in pretty bad radial velocities and temperatures for any stars above 8,000 Kelvin. So I have a very preliminary panel showing you the estimated precision of the radial velocity as a function of wavelength. in these 4 different windows. The 4 different colors denote the 6 different colors denote the 6 different type of stars that I selected. So red dwarfs, red giants, FG stars, and A and F type stars. And as you can see, for example, so in all of these 4 windows, we can get pretty good radial velocities across these stars. So this is consistent with the previous plot. So the very left plot, the very left dots denote a Gaia-like mission. So anything that is below, anything that is higher resolution than 10,000, or anything that is on the right side of these dots, mean that we use a larger window size on the detector than Gaia has used. So the problem, we have another problem. So if we want to derive abundances, we really need a higher resolution in the K-band, because lots of these lines are blended together. So 10,000 resolution in the K-band is not really enough to get abundances. So we could get basically iron and calcium and maybe magnesium, and that's it. So we need to go higher resolution. Now, if you go higher resolution, we need more pixels in the detector. Then the blending of stars might be a problem. So in order to reach higher resolutions, we really need to narrow down the wavelength range even more so we can manage the window size on the detector. So now here you can see an updated window selection that I just made last week. I started to chop up these 60 to 70 nanometer windows and have narrower windows around 30 to 40 nanometers in each selected 4 different wavelength ranges. Now, when I select these wavelength ranges, I make sure that I keep all the strong lines in the spectrum to preserve the radial velocity precision. So I still need to explore what the radial velocity precision is in these narrower windows. And the main question that I would like to answer is that is narrower, smaller wavelength range and higher resolution better than a wider window with a lower resolution? So this is an important question that needs to be answered. And I would like to explore what happens when we use only 800 to 900 pixels in the detector, and what happens there, what kind of resolutions we can achieve, and what kind of radial velocity precision we can achieve with those. So what about abundances? So this is a plot that shows you which wavelength region is sensitive to which element. And the top panel shows you the response of change to 0.1 dex in the abundance, and the bottom panel shows you the response to an 0.2 dex change in abundance. And this is a red giant star, 4000 Kelvin log G1. So you can see that in the K band, we can really measure around maybe 7 to 8 elements, the abundance of 7 to 8 elements. And this is with a resolution of 15,000, so not 10,000. The 10,000 is obviously worse. So really, if we want to have good abundances, we really need to increase this resolution to around 15 to 20,000, which means that the wavelength region needs to be narrowed down in order to fit on the detector. So the question is, how much radial velocity precision can we sacrifice to get abundances? So this needs to be explored a little bit more. So overview, so I made this test, and based on these tests, I actually tend to recommend using that region just below 2 microns, because it's overall, it looks like that's the best we can get good, precise radial velocities. You know, the extinction is much lower than at shorter wavelength, and we can probably measure abundances around 7 to 8 elements if we can bump up the resolution to be high enough. Now, the backup option could be the region around 1500 nanometers. But there are other good options between 1 micron and 1.6 microns. So that is all my talk. Thank you very much for listening to me.
Sonam Szabolcs, there is one question, and it will be on early high temperature stars.
Thank you. Jose has read my mind as I expected. So yeah, that's exactly my point. Just ask a favor. Please, whenever you do this, consider that there are stars that are significantly hotter than 10,000 degrees Kelvin, for which most of what you have done is not significant, and that they are of high interest to a significant number of people. So please try to include, I don't know, I mean, something that would have been useful, for example, when designing the Gaia window, which is trying to find some helium lines, right? And not basically select a part of the spectrum which only has hydrogen lines, or something that is valid for later types. I know that the answer is going to be that there are a small fraction of the stars, and that we're a small fraction of the community, so you will give me a polite answer, but essentially you will pay no attention. But I just wanted to say this, so that my students, of course I will be retired when Gaia NIR works, but my students will complain about this, and at least I'll be able to tell my students, well, at least I asked a question.
So, yeah, so we'll explore what kind of lines available in these 4 selected windows for the hot stars. So we can go higher than 10,000 for those line identifications, right? So, but unfortunately from this plot, you can see that, you know, above 10,000 Kelvin in the infrared, you pretty much lose almost all lines from the spectrum.
Jesus says that there are helium lines in that region.
So the question is where those helium lines are. So and they need to be fit into those 100 nanometer wide wavelength regions that we select. So if you can send me the list of helium lines that you have in mind, then I can start think about it.
He will do it.
Okay, thank you very much. That would be great.
He's preparing the email.
Okay, thank you.
Thank you very much, Savox. Please stop sharing. Thank you. And now, Josep Manel.
No, this one, Control L, something like this. Okay. Yours. Thank you. Well, first of all, I must say that now I understand why the rain in Sevilla is wonderful. It's the only option I had to have a crowded room the last talk of the day. So thank you very much for remaining here. I will be talking about the photometric system of Gaia NIR in the status it is designed now or thought now. First of all, I add this sentence with this slide. We know that Gaia NIR will be very useful. We will be seeing the infrared domain, and some targets, for instance, these white dwarfs, are better separated in different compositions, better in the infrared, in this red range, than in Gaia domain. So Gaia NIR is very interesting, and we need to measure the fluxes in these ranges. No? And this is the focal plane proposal that David was mentioning before. Here you see that we have some columns, some strips of CCDs devoted to photometry. These ones here for the astrometry, these for having the colors, the photometric filters, one for the whole range as in the astrometry, and the others in specific ranges. And here the spectrophotometry, and here the radial velocity talk in the previous talk. So here you have the summary of the data of this. I will start with this part, the photometric passbands, the filters. And the main purpose of the filters in astrometric mission is to measure the centroid of the stars. The centroid of the stars will depend on the color. You see here an illustration of that. The centroid will change if the star is red or if the star is blue. And this
this is not enough to know the color of the source once during the mission. You need to monitor the color during the mission because we have learned, well, we knew already, that the color of a given source can change significantly. You see 1, 2, 3 magnitudes, depending on the type of variability. You can have a significant color change. So this is mandatory to have for all the sources that we want precise astrometry, so need to be included. The purpose is this that I mentioned and others, very similar to Gaia. I will focus on this. I will shorten the talk in this way. So we will have better signal to noise having photometry instead of a spectra in comparison. So all the stars will be detected because of that. As we don't have dispersion, in the previous talk it was mentioned that the spectra will impose larger crowding, so we will have better angular resolution, and this is very important in the infrared, as David mentioned. We will have less pixels to read, less readout noise. We will have less contamination due to this PSF. This is what I illustrate here. When we are using some filters, we select to be detected in this part of the picture only the color range that we are interested in. So if in this figure is green, all the green light will be measured, and only the green light. Instead, if we are using a prism, a spectrophotometry, for instance, then we will have a mixture of colors because one given wavelength will not always fall in a given pixel, but also contaminating the neighboring pixels. So this is a much more clean information using filters than using spectroscopy, and also the data reduction is more simpler here than in the spectroscopy option. These are the passbands chosen in the previous slide. You see here some stars overlap the spectra, the spectral energy distribution of some spectra, different temperatures here also for the whole BT settle library. And you see here in gray the 2 mass filters. Suspiciously, one of the limits of the 2 mass filters coincide with the current design in Gaia NIR. And this is not very suspicious, it's because it coincides with the bands for the very red sources. Okay, so we have these 3 options for Gaia NIR. It's funny to notice that the large, the meaning of large in the 90s, it's now meaning small. So we are using Gaia as the small design for Gaia NIR. We have also a medium design and a large design, as David explained. The difference is that for Gaia NIR medium, we increase a little bit the mirror, and we double this large mirror in the case of the large. So trying to simulate the photometric performances, I use this detector in the infrared. I don't know if it would be exactly the same, but anyway, I define the limits of the passbands and cut this response 80%, as David mentioned, response subtraction. And also, we have an extra passband. We also measure, I didn't mention it before, we only have J, H, and K, and in the current design, we don't have DR, but it could be derived by subtracting these fluxes to the global flux. So this is the scenario here that I'm considering. So using these simulations, I can provide some transformation. In this way, we can, from 2 mass, for instance, or from Gaia, or from Euclid, predict what Gaia NIR magnitudes we can have for a given target, okay, depending on the color of the target. So here you have some polynomials that are fitting these color-color relationships, and then you are able to predict in different photometric systems. I could add others, these ones here. If you are interested in those, I can derive it also for you. Also, with these simulations, I can derive the 0 points, and these 0 points they can be shifted to the limiting magnitude. In case of Gaia, we had a limiting magnitude of 20.7. Then in case of the medium Gaia NIR passband, this, with the same detector, will provide a magnitude of 20.2, something like this. In the large, 21st magnitude, something like this, and different in the other passbands. Okay, so we are not able to, in principle, with the same kind of detector as in Gaia, it will be different, to observe a fainter source than this 20.2 and 21st in N. So this means that depending on the color, here you see the magnitude of Gaia NIR, depending on the color, J minus K. And you see here that there are some sources that follow above the line of the limiting magnitude in these two designs, the large or the medium, okay? So in the large, 21st, in the medium, 20.2. So what are these sources? These are unreddened sources, zero reddening or very low reddening, and here you have it. The sources in this circle here are plotted in color in this right panel. So you see that for magnitude 0, you are starting to lose sources hotter than 6,000 kelvins, which is quite significant. For the large mission, 14,000. So maybe you are happier now. Anyway, these hot sources will be reddened. Some of them will be reddened in the formation, star formation positions. So in this case, with large reddening, none of them will be lost, okay? So these hot stars will be there in Gaia NIR. So with my simulator, I can use the same formula that we use for Gaia and apply it to get the uncertainties. What is the photometric precision as a function of the magnitude in Gaia NIR? And again, remember that the R flux is derived from the subtraction of J, H, and K from the N. So that's why the R passband has a larger error. Okay? So if we want to have similar performance as in the other passbands, maybe we could substitute the R, add some column of CCDs to detectors to measure this R. I will mention it later. So this is this was the uncertainty against the Gaia NIR magnitude. By now we have only the Gaia magnitude, so here I change the x-axis, and here you have for different type of sources, different temperatures in color, what is the precision that we can get for N, J, H, and K. For a non-redundant star in the Gaia NIR medium design, of course, if we go to the large design, then we decrease the errors, okay? So I will go fast with this. Anyway, this is absorption 0, unreddened sources. If we have reddening, of course, these sources will have, by the same magnitude, will be having larger flux in the infrared. This is the same plot as David was showing, just for having the comparison with Gaia that I didn't provide, and you have it. Studying the interstellar absorption, the advantage in the infrared is that we have less absorption than in the visible. So for the N band, we have 34% of the magnitude in Gaia G, and in the others, well, progressively better for redder filters, for R, J, H, and K. So this is the advantage. Now, I have been talking about these columns here, these strips. Now, the spectrophotometry, okay? We have 3 proposed. And again, the purpose is very similar. We add the redundancy to have photometry and spectra. In case one of them fails, we have the other. And the advantages is that it's cheaper to, instead of having many columns, just use one of these columns and a prism that disperses the light, and you have all the colors at once. So it's cheaper, occupy less space in the focal plane, and could provide better spectral resolution. If you are interested in a band, then it's better seen. We could repeat the same design as in Gaia. put in some prisms, these are the prisms in Gaia, in front of the detectors, and then these prisms disperse the light, and then you get these 2D images seen before, and then from these 2D images, you derive the 1D spectra. The drawback is that the resolution is not as good as in the radial velocity, so the resolution is smaller than 100 in case of Gaia, and not homogeneous in all the wavelength range, you know already. But Josh was mentioning that the spectrophotometry in Gaia was very successful. A lot of science has come from it. One of them is the synthetic magnitudes. For instance, I know J+ have been using this spectrophotometry to synthesize the J+ passbands and then calibrate J+, and the other way around. We have used J+ for Gaia purposes. And also you can synthesize any other passband on ground, RGB, or any other filters in Strömgren, and for a given cluster, then using only these synthesized filters, you have better color magnitude diagrams than from ground, of course. You have space-based information. So spectrophotometry can derive distance, extinctions, the stellar parameters, the photo redshifts, alpha abundances, the chemodynamical structure of the Milky Way. So it's very useful, so include it in Gaia NIR. In case of Gaia, you see here the comparison of Gaia and Gaia NIR. In case of Gaia, the width of BP and RP in wavelength range is this type. We are measuring this spectra in 40 pixels. If we divide all the range by 40 pixels, every pixel, it's not homogeneous, you have seen, but in average, it's something about 6-7 nanometers per pixel. In case of Gaia NIR, we have a wider wavelength range, and for the same size of a spectrum, then we will have less resolution for Gaia NIR than for Gaia. Although we increase the resolution or taking more pixels, as it was mentioned, but it's not optimal. You lose more stars in this case. Okay, and just to end, this is the focal plane that you have seen. We are still working on it. So another option is, as I was mentioning in the talk, to substitute this column by one R filter. So instead of only 3 passbands, we can have a 4th. Okay, so this would be for astrometry, full color, and full spectrophotometry. This is a possible design, but maybe you are worried about renouncing of this column here, and I then make an analysis here. This is the option of having 5 N strips and no R strip, only measure from the spectrophotometer. So you have here the performances with respect to Gaia magnitude for the case of N and for the case of R passband. The R passband comes from the quadratic summation of all the other uncertainties, so it's quite large, the performance that we can have. If instead of that we renounce to one of these strips and have the R passband, then we have this change. You see here that the one in the left doesn't change much. We get a larger error in N, but reasonably equivalent. But on the other side, in the right panel, we are decreasing quite substantially the R uncertainty. So my option is to bet for the inclusion of this filter, because we are not losing much in here, but we are gaining in the R. And the advantage is that we would have this R color for all the sources, and no crowding and perfect calibration, and it would be nice for astrometry also. And finally, this for a sun-like star or a 3000 Kelvin star, what is the performance? Using 5 strips and no R, or substituting one of the N by NR. So you see that for a sun-like star, I was saying that we are losing the sun-like stars. We will get good uncertainties for these types. And for the M-type stars, instead of having significant large uncertainty, we will have similar uncertainty as the other fast ones. So that's it. Thank you.
Excellent, Josep Manuel. Very good.
If you have questions.
Yes, at least one.
I was curious. About a month ago, there was the release of the data of SphereX, which basically is all sky narrowband filters. And since it's all sky, one can start playing around with types of stars and spectra. So I was curious if you tried, or if this data set can be useful for the design of the photon or the low resolution spectroscopy, mostly.
Yeah, sure. I have to have a look deeply. I didn't have time yet to do it, but it's true that the access is a pain.
Indeed.
Okay, so I will let you share your data with me.
Wait, Jesus. Wait, Jesus.
It is a peer. Espera. No, my only comment was that it has a spectrophotometry, so it's even more useful for you.
Yeah. Mm-hmm.
We have a last comment, but before that, applause to Josep Manuel.
Okay, one last thing before closing today. No, two things. The picture will be tomorrow in the coffee break after the round table with in the industry. So, without coffee, I'm not going to comment on this. At the break in the afternoon, okay? And the second thing, somebody has asked us for a room to make a meeting or a telecon or something like this. It is on the first floor, just above the auditorium, so take the elevators, turn right at the end of the corridor. The room should be open for you to use, okay? If you have any trouble or you have problems accessing the first floor, please contact us, okay? So see you tomorrow at 9:30. Minia, you will be the chair of that session, okay? 9:30, okay. So thank you all.
One more. I have my car in the parking lot there, and there are 3 empty spaces, and I will go to the Hotel Occidental Sevilla. If somebody is interested, I'm here. See you tomorrow.